Günaydın. Good morning, everybody. It's time to begin the session of today. I'll just need your attention if you wish to. Hello, my name is Musa Bahar. I'm the one of the managers of the TCIP, and we'll be beginning the second day. Distinguished TCIP board directors, distinguished representatives of the insurance and reinsurance sector, and distinguished academicians. Welcome to the second day of the International Earthquake Risk Management Workshop. We had a good start yesterday, and today, a very enjoyable, but it will be a busy program for us today. I would like to invite Mr. Professor Erdik to the podium to share the schedule of today and make a speech titled Loss Modeling and Insurance Pricing Related to Earthquake Risk.
Thank you. Good morning. Our numbers have reduced a bit, but I think that the audience is much more dedicated. And then this is the second day of the workshop, and today we will deal with the CAT modeling and the pricing as well, with excellent speakers. You can see some of their names here, but I'm sure that you'll enjoy their presentations as well. I've been giving the task of essentially introducing the concept and the scope of today's deliberations, and I will go for that. But I'm not going to take too much of your time because we are already somehow late. The building of sustainable and resilient communities against the earthquakes is a very critical question, and obviously an earthquake, unexpected earthquake, can break the system, and then return to normalcy can take a long time. So in that regard, earthquake insurance is important because it functions as pre-disaster funding for that limits the economic impact of the post-disaster recovery individuals, business, and government by transferring the risk to other markets. In this connection, obviously, the CAT modeling is of very important. Well, we will soon hear that the CAT modeling is an integrated process of conducting numerical simulations of the earthquake occurrence, ground motion prediction, and final losses. Obviously, you need the inventory and the database. You have to be able to characterize the hazard. The vulnerability assessment is a very important part, and estimation, and the insurance portfolio analysis, and the insurance pricing as well. The pricing is one of the outcomes of that, and we will see the approach that has been taken by the TCIP in that regard. Today's deliberations will deal most of with these issues. There is the components of the CAT model, which is the event, damage, and the loss. The type of losses can be direct, indirect, and there's also a loss amplification issue. That some of these issues we will also deal in the panel, which would be end of this session. And what are the metrics for that? I'm sure we will hear about those metrics. Those are accident probability, AAL, and the probable maximum loss as well. Potential use are a lot, and they keep increasing. The biggest ones is the insurance pricing, and which is rate making. Then there's the underwriting and the risk selection, the management of exposures, loss mitigation strategies for the government mostly, reinsurance and risk transfer analysis, and the final solvency for the insurance companies as well. The two of the loss estimation methodologies that we will discuss today, they have been very well developed by the GEM, in fact, that constitutes some of the basics of the OpenQuake program, and that's the deterministic event-based loss calculation and probabilistic event-based loss calculation. Most of these things mostly use the Monte Carlo procedures. I don't want to go to details because you will hear a lot about those things. This shows the complexity of the uncertainties in loss estimation. I'm not going to go on each and every one of them, but you see lots of lines and connections and everything, so that change or uncertainty in one factor influences uncertainty to others, and the progression of the uncertainty is a tool by itself. I mean, you don't add up the uncertainties or sum them up or convolve them, but you have to use certain approaches and regulations so that to manage the uncertainties. In fact, the management of the uncertainties is much a bigger tool than getting the median results. The uncertainties reflect always, obviously, they result in the assessments. This is a figure taken from Daniel's thesis from Karlsruhe, which shows on the vertical axis, it shows the observed economic loss of an earthquake, and on the horizontal axis, the calculated economic loss. If we were able to calculate losses properly, then the black line in the middle would be the correct way of showing things. So this line, if we were able to do that. You can see that especially with losses, with not that high losses, the scatter is high. And then as the losses increase, the scatter may normal, but then again, we don't have too many data. This, obviously, the loss calculation in this case may not be as precise of the CAT modeling, but then again, it shows the amount of dispersion between the calculated and the true losses, and I'm sure that will, what we will try to do in the next years is that to reduce that variability between them. The uncertainties loss estimation, they arise either in part of the scientific knowledge, which is less knowledge or the probably knowledge, that's epistemic uncertainties, and we have aleatoric ones. And then they show the aleatoric uncertainties affects loss distribution and exceedance curves. Epistemic uncertainty and aleatoric variability in the intensity measure distribution maps. The mean damage ratio is highly sensitive to cost ratios assigned for each damage rates, so that means consequence relationships. Loss correlations can also have an influence on the aggregate portfolio risk, and then as we discussed, that these end up with the uncertainties in data, but we are in a good position to estimate the uncertainties and to manage the uncertainties, and then I think this will be discussed in detail. Today's program, I will leave the floor in a while to Sinan, and then we have several excellent speakers and the excellent presentations, starting with Pete Stafford, Sergio Lagomarsino, Helen Crowley, then Sinan will talk, and Paolo Bazzuro, and Fuat Bendemerat, Ismet Güngör, and Charles Scawthorne. And then at the end of today, we'll have a panel session. This panel session will mostly attended by the vendors and the reinsurers that have a stake in the loss assessment, CAT loss, and they have their own models. So we will discuss essentially what we have learned and what's in the future, and then that will be open to questions both from the audience and from the panel members and from by myself as well. So with this, I will leave the floor to Sinan. Thank you.
Thanks to Professor Erdik for his speech. The floor will be Mr. Akkars, Professor Akkars. We have been working with him for a little while since the preparation of the new Turkish earthquake hazard map project, and which is followed by the projects of new compulsory earthquake insurance tariff and modeling. The floor is yours.
Good morning once again. I'm going to make a very short intro about the morning session. We will be listening to eminent researchers, professionals from Europe today in the morning. But before that, what I would like to show is the context of morning sessions talks. All right. So earthquake loss modeling and pricing is going to be the overall topic that will be covered in the morning session. And as you all have already heard many times yesterday, given an earthquake hazard and an exposure which could be residential buildings, industrial facilities, and so forth, the question posed is how to come up with a loss as a function of ground motion intensity. And then the loss will lead to insurance pricing, essentially. You can have some functions from observations to describe the loss, or what you can do is you can use fragilities and consequences to get the loss or vulnerability. Fragilities will tell you essentially the damage probabilities, and the consequence models or the consequence functions will in a way quantify the damage with its probability to get the loss. And essentially, you convolve the hazard, the earthquake hazard, with the vulnerability to get the risk, to assess the risk, and the risk will essentially lead to insurance pricing. Well, as Professor Erdik has already indicated, if all of these boxes are actually like really known, maybe the answer is going to be only this solid box. But because there are lots of uncertainties involved in each one of these boxes, which are controllable due to modeling or uncontrollable due to nature. We have ups and downs or scaling. The insurance pricing or risk can be scaled up and down, the way how you consider these uncertainties. So essentially, the talks addressed this morning will be mostly covering these, say, topics. And our first speaker is Professor Peter Stafford. He will be talking about risk-oriented hazard modeling, significance of non-ergodic assumptions in hazard modeling for portfolio risk. So he'll be explaining these concepts in his talk. And then Helen Crowley, Dr. Crowley will follow Professor Stafford. She will be presenting, sorry, I forgot my glasses. I cannot even see the screen from here. The elements at risk, fragilities, and consequence functions, and then vulnerabilities, and essentially the development of exposure and vulnerability components for European seismic risk modeling. She will be talking about her group's experience about these components while establishing the last seismic risk model for Europe. Then Professor Lagomarsino will follow Dr. Crowley. He will be talking about empirical fragility and vulnerability of regional building stock in Europe, and then development of microseismic vulnerability and its implementation to risk. And I'll be talking more on the modeling aspects that we have been conducting together with TCIP and Turkish Insurance Association. I'll be trying to show you the progression of uncertainties in the modeling components in vulnerability to loss. And then Professor Basuro will complete the morning session. He will be talking about the CAT modeling application to insurance industry, and so essentially he will be addressing the unknowns and possible sources of bias in pricing, the effects of common modeling assumptions that eventually contribute to bias in pricing. So without further, say, explanations, I would like to invite Professor Stafford to give his talk. Peter, you can sit after a while here, or you can go to your place anyway.
Okay, so thank you very much. So as Sinan mentioned, I'm going to talk about a few things primarily related to ground motion modeling that largely reflect developments that have occurred outside of risk analysis, outside of that domain, but to demonstrate how they can have important effects once they're mapped across into portfolio loss estimation. So first of all, I'll start with the general context to put in place what our primary objective is, talk about what we need from ground motion models and from correlation models, and then talk about this issue of the ergodic assumption, okay, and what impacts that can have on risk estimates once we relax it. And then ultimately, I just want to talk a few things about how these issues relate to risk assessments for sequences of events, particularly aftershock sequence or clusters of events. So if we just start by looking at what we need to do for a single building, a single site, not worrying about a portfolio initially, then generically we have some sort of source model. This is just some region that has a bunch of faults, okay? So it could be Istanbul and Sea of Marmara, etc. And in principle, what we want is to say that for each earthquake that occurs inside that source model, or that's created from our source model, that we would have a whole bunch of region and site-tuned ground motions that we could pass directly through some structure. Okay, and once we did that, we can estimate the demands on the structure, and we can calculate damage measures and consequences from those things. Okay, we never do this. Okay, we never work at that level because it's computationally too intensive to do so, and we can't really generate the ground motions properly at the moment anyway. Okay, things are moving in that direction, but they're not there yet. So what we do instead is to say, let's take a bunch of ground motions that are representative of the types of ruptures that will come from our source model and use those ground motions to generate ground motion models and to derive correlation models. Okay, and once we have those, then for each sort of level of hazard that we will be generating from our calculations, we can develop targets of what we would call intermediate intensity measures, so just some measure of, say, peak ground acceleration or whatever we want to look at. And then from those, we derive the demands on the system using a far, far smaller suite of records. Okay, and the objective is to try to make sure that the distribution and the response we get from our structure going through this intermediate step is going to be the same as what we would have got had we generated all those ground motions initially and passed them straight through the structure. In reality, we don't just pass those motions through directly. What we would do instead would be to take some sort of prototypical buildings or some simplified model, and we would run a whole bunch of time history analyses, generate distributions of response conditioned on some single measure of the ground motion, and from that we can then derive the consequences. Okay, so the key problem here is that we have a whole bunch of ground motions that are extremely complicated, that have very special features that are local to the region, and we're going to choose to characterize those intensities by a single measure of the ground motion, just some PGA or whatever we care about, and then use that to predict the demands. Okay, and what we have to make sure that we do is that the distribution of responses we get should reflect all of the properties of the ground motions that haven't been directly considered in the hazard calculations. Okay, so once we go to a portfolio, we collapse this down to basically saying, let's have a source model. From that source model, let's generate a whole bunch of ground motion fields. Those ground motion fields have to replicate the characteristics that would have been possessed by all of the time histories that would have come out from the source model. Okay, and from those fields of ground motion, we could derive a hazard curve if we wanted to, and we can effectively convolve this with some fragility or consequence models in order to determine the risk. Okay, so these are all the same problem. The first three slides are relating to what we do for a single structure, and the final one is saying, okay, how do we approximate that result for a portfolio? And the issue that we have to deal with is we actually want all of these methods to give us the same answer. Okay, we want to make sure that even if we're using a much simplified method where we go through some intermediate intensity measure and we use some fragility functions for prototypical structures representing a building class, that ultimately the results are the same thing. Okay, now there are some reasons why that won't be the case, and I want to talk about some of those today. Okay, what I'm focusing on in particular is what do we need for the ground motion models? How do we make sure that the fields of ground motions that we simulate with the appropriate variability and correlation structures are trying to replicate what would have happened if we had used time histories directly? Okay, so firstly, the requirements that we have for ground motion models themselves. What normally happens is that we have some rupture scenario, so it's just a magnitude on some fault with some geometry that we know about. And given that we have that rupture, we want to say what's the distribution of all the measures of intensity that describe the effects of that earthquake on our building portfolio. Okay, and the way that we would normally do that would be to say let's have a multivariate normal distribution of intensities that require some median prediction of what the expected levels of ground motion would be, and then some matrix here that says what's the distribution of all the different intensity measures for that rupture. So, as Professor Erdők mentioned earlier, we have these ground motion models that provide some sort of median prediction. That's all encapsulated in this prediction here. I'm not going to talk any more about that. That's what 95+% of all the effort in ground motion modeling is devoted to. What's arguably more important is how you represent the variability and all the correlation structures against the intensity measures. So that's what we're really going to be focusing on in this talk. What's the variability, what's the appropriate amount of variability, and what's the interaction between the different intensity measures that should exist. So yesterday there was some reference made to how we can think of ground motions being made up of two basic components. You would have the sort of median prediction, but then you'd have some systematic effect at the source that would reflect the fact that for a given magnitude earthquake, a particular event might be slightly higher or lower than average in strength. And then on top of that, you would have spatial variations of what we would call the within-event residuals that vary across position, okay? Now, sometimes usually we would go directly to the surface and make this prediction for a portfolio loss model. There's no reason why we can't replicate what we do in other studies, where instead you have some prediction at some deeper horizon, okay? And then we explicitly account for the site-specific site response effects in the near surface, okay? We could do this. It just complicates things slightly. What I want to talk about is what are the properties of these event terms, so the between event term and the within event term, and what are our requirements for these. So these two are essentially independent components. One's normal, one's spatially varying, and we can talk about the total variability coming from these two components, okay? Variations from event to event and variations from site to site within a given event. And we know that, this is very well known, that if you have larger values of the overall standard deviation, the ground motions, that the level of hazard will increase, and consequently the level of risk will increase. Okay, so larger sigma or overestimated sigma values lead to overestimated hazard and risk. We also know, and we saw this again yesterday, that the correlation of these within event terms, so how much spatial variation you have across a ground motion field, influences the risk estimates that you obtain. So at extreme, this is a particular case of a consequence on a transportation network, but if you have no ground motion variability at all, then you have this case here. When you have ground motion variability, but you ignore the possibility that the variability is clustered or is correlated in space, you are here, and once you account for spatial correlation, you have these higher levels of risk. Okay, so more significant consequences for the same return period. So if we have stronger spatial correlation, we would also get higher risk estimates in general. So one thing I want to sort of bring up today and to discuss is, do our current approaches that are based upon this ergodic assumption, do they systematically overestimate the sigma? And the answer is yes. And do they also influence in a biased way what the correlation structure should be? And the answer again is yes. And typically in both cases, the consequence will be an inflation in the estimate of the risk. Okay, so we want to look at these two components. So when we're looking at the correlation cases, the reason why we need to worry about spatial correlation and also correlations between different measures of intensity is that we're working with a spatial region where our portfolio exists, and we don't work at a building by building level, and we aggregate up structures into different spatial regions, and we aggregate buildings up in different classes. So these schematics just show the typical correlation cases you might consider. On the left here, we just say there's a spatial region, there's some regional cell here, it might be a postcode or whatever you're working at. And if you have a whole bunch of buildings from the same building class, then you model the demands on that set of buildings by making a prediction at a particular location. Okay, and the typical modeling assumption in this case is that there's no reason to have any correlation because they're all the same buildings, they're all at the same nominal location, so all the ground motions are fully correlated in that cell. If you have the same buildings, same building class, but with some spatial separation, then the typical modeling approach is to assume that you can represent spatial correlation between these 2 points, but that you have the same dependence for the structural type because they both depend upon the same measure of demand. And then there are other variations where you have different buildings in the same cell, and you have correlation without spatial effects or cross correlations in here. Okay, now these are the typical approaches that are taken in normal loss models. So you either have no correlation, purely spatial correlation, purely inter-intensity measure correlation, or a cross correlation with both measure of demand and spatial effects. Now the problem is that none of these sort of assumptions are strictly true. We obviously don't have all the buildings actually at the same point, so we should account for that fact in the correlation structure. And you can see the other effects. Okay, so it's not the case that we have this modeling assumption replicating what we see in reality, and we need to adjust the correlation values that we obtain in order to reflect what the actual situation is. So if we look at these sort of two special cases of these, the first thing to note is that when you're modeling the correlation between, say, two different intensity measures, so this is on the left here showing correlation between two response spectral ordinates, so think about it as being the correlation and demands on two different building types, so T1, T2 being the two periods representing those building classes. You have this correlation that reflects correlation assuming that those buildings are at the same point. Okay, so correlations and ground motions is a single location. Then if you look at spatial correlations, you can say, given a separation between 2 points, how does the correlation vary with distance? And this is a model for pure spatial correlation. What we would normally do is assume that the overall correlation for the intensity measure and space can be found by saying, what's the correlation at a point between the intensity measures, and then multiplying that by a spatial correlation that reflects one of those intensity measures. And that's the standard assumption that we adopt. So if we want to look at what's the effective case, if you have a bunch of buildings that are in the model at the same location, but in reality are spread across space inside some cell, then we need to reflect the fact that there is spatial correlation inside that cell that affects the true correlation. Okay, so if we look at some generic region and look at possible combinations of position inside the cell, we can calculate sort of the effective correlation that's accounting for how big that size is and how much spatial variation we have across the cell. And if we do that, we'll get a reduction in the effective correlation. So typically we would assume that because everything's at the same point, that this upper blue line here would be the true correlation between two building classes with different periods. In reality, it won't be that case because you will have a reduction in the correlation by virtue of the fact that these buildings aren't at the same location. And the reduction depends upon how big the spatial cell is. So if you're working at a relatively high spatial resolution, so this is a grid of, say, 100 meters versus a 5-kilometer grid, then you can get quite different degrees of reduction in the effective correlation at a point. Okay? And this effect is normally ignored in modeling. In addition to that, because you have this variation across the cell, there'll be some additional inflation of the variability. Okay? So you predict the motions at a single point for the cell, but you're actually trying to replicate what would happen across that spatial region. And so there's additional variation that comes from the fact that you don't have the full correlations. Okay? So we would be slightly underestimating the variability, and we'd be overestimating the correlations. If we look at the spatial effects, it's a similar thing. If you look at two spatial regions that are offset by some distance, again, we would have the fact that in the model, you assume that the buildings are all at the same two positions, but in reality, this building could be here or here or here or anywhere else inside that cell, and this building could similarly be anywhere inside that cell. Okay, so you need to reflect that fact, and you do a similar sort of a procedure, and we see that depending upon how big the cells are and how far away they are, determines what the actual degree of correlation is between any two locations. Okay, and again, this is also usually ignored. This part doesn't have as big an effect as the inter-IM correlation, but again, it depends upon how big the spatial cells are. Okay, so that's sort of what we need. We need to have models that reflect these sorts of correlations, and we have to account for the fact that we work with a discretized domain. And so what I want to talk about now is this issue of the ergodic assumption. What we really want is to have, a fault, and for that particular fault and particular site combinations, we want ground motions that reflect those local characteristics. So the features of the source at that location, the particular features of the travel path from the site, from the source to the sites that we care about. And to do that, we would need to have a big database of records that reflect those characteristics, okay, to properly calibrate the ground motion models. We don't have that anywhere in the world, and what we also want to have is a ground motion model that's robust for all the scenarios that we need to make predictions for. Okay, so what the ergodic assumption is really saying is that at the target site that we would care about, what we really want is a long history of empirical data reflecting all the ground motion characteristics just for that region or just for a particular source-site combination. Okay, and we can't get that. So what we do instead is to say, let's take a whole bunch of different sites that are roughly similar and take all of that data and compile it into a big equivalent long history and assume that if we were to wait for a very long time at our site, the statistics we obtain from compiling all the data across different sites would be the same as what we actually want. Okay? And so this is what we call the ergodic assumptions, where we trade the lack of temporal information, we supplement it by using spatially distributed information, and we assume that the variability that we get for this sort of composite chain here is going to be the same as what we actually want. Okay? Now, the reality is that it's not. Okay? So what we would have in the more sort of non-ergodic framework is that we have our median ground motion prediction, just a normal ground motion model. We would have a dependence upon a particular location. Okay, so depending upon whether that earthquake is in New Zealand or Japan or Turkey, etc., you would have some systematic effect that reflects the specific properties of that region. Then within a region, you would have the between event variability. Okay, you would have systematic site effects. So even if you have a site with the same, say, VS30, the velocity structure below that site determines what the actual amplification effects are. And there are repeatable systematic site effects that vary from point to point. Okay? And when you're bringing in data from different regions or merging it from a composite data set, what you're really doing is bringing in a whole bunch of region-to-region variability in the source effects that shouldn't apply, and you're bringing in a whole bunch of systematic site effects that also shouldn't apply to your target region. Okay, now the consequence of this is that when we look at a traditional ground motion model where we just have between event variability and within event variability, that corresponds in the non-ergodic framework to a situation where we have both the location variability and then the within location variability all being grouped into this delta B, and the systematic site terms and the within event site terms all being lumped into this within event term here. Okay? And the problem is that our variability estimates are reflecting both of these components when we're working in the ergodic approach, and this part here shouldn't apply. And when we're working with the site terms, this part here shouldn't apply. So if we move to a non-ergodic approach, we have to make an assumption that we can estimate what the actual location-specific source effect should be, and we have to estimate what the location-specific site effects would be. Okay, but provided we make that estimation and account for the appropriate uncertainty in what those estimates are, then we can cut out these components of variability from our ground motion models. Okay, and this has a significant reduction on the amount of variability. And we saw before that when you have a lower sigma value, you have a lower hazard and you have a lower risk. Okay? It doesn't come for free. You still have to then make sure you account for the fact that when you estimate the region-specific effect or the site-specific effect, that you account for how well you know that. Okay? So you have some epistemic uncertainty in saying, you know, for the Sea Marmara, what is the systematic offset on that fault? Okay, is it higher than average? Is it lower than average with respect to my ergodic model? Okay, and the uncertainty on that could be quite large, but it is an epistemic uncertainty. Okay, so to show you examples of where this can happen, this is in Christchurch. These are the results of physics-based simulations where you've got the Darfur earthquake and the Christchurch earthquake shown by these faults in here, but then roughly 150 odd events where the source characteristics in each event is the same, but when you propagate it through the 3D crustal model, the velocity model in this case, you'll get systematic deviations in the relative source strength that depend upon your spatial position. Okay, so we can reliably say that the properties of the crust and the faults in this region here are such that if an earthquake occurs in this region, then it typically has a lower than average source strength. If it occurs in, say, this region, it has a typically higher than average source strength. Okay, so once you can compile this sort of information then we don't need to account for the full variability or all this range at every point. Okay, we can say we're in this region, so we're typically up here somewhere, and we don't need to sample all the rest of the variability. And the same thing, if you look at the systematic side effects, there are some regions where you'll have systematically lower than average site response, other regions where it's systematically higher than average. Okay, and once we can estimate these effects, we can start to remove the ergodic assumption and reduce the variability. This has impacts on correlations. So this is some examples of correlations, this time between a different measure of ground motion, but strongly related to response spectra. These are between event correlation models, between site correlation models, and what you get afterwards in terms of interfrequency correlations of just the within event terms once you've removed the systematic event and side effects. And normally what you assume is that all the correlation in here from the systematic side effects is lumped into this bottom panel. Okay, and what you see here is that once you take out the systematic site part, the actual remaining interfrequency correlations of the within residuals is actually much, much lower. So this maps across into response spectra. Once you remove the systematic side effects, you reduce the interperiod correlations in the response spectral ordinates. For the spatial correlation, you have a similar or another effect. I mentioned before this study, Jerram and Baker. This is adopted quite commonly. They use an exponential correlation model that has this sort of form, so you have some separation distance from point to point and some correlation length R. And when they look at data from around the world, they find that there are differences in what that correlation length should be, depending upon whether you have sites that have, or regions that have clustered site conditions, or regions where the soil conditions are quite varied. Okay, so this is a correlation length. The blue corresponds to cases where there's quite a lot of clustering in the soil conditions. Red when there's basically limited clustering, but this really reflects sort of California and Taiwan largely. Okay, and you can see that the correlation change with distance varies a lot on that correlation length. Now, if you look at their framework, they're working in a fully ergodic framework, so they don't take into account the fact that each location has systematic site effects. If they did do that, then what they could obtain would be a correlation between within event residuals that reflects contributions from the actual site adjusted within event residual and the correlations corresponding to the systematic site effects and how they vary in space. Okay, so if I just show you some conditions where I have a site-specific systematic offsets from my regional model, and I look at what's the correlation structure of those, and then look at what's the correlation structure of the ground motion field once you account for the systematic side effects, then you can have these two separate correlation models. Okay, and we can just look at some conditions of these. So this is the overall correlation. When the correlation lengths for the within event or the site stuff is at different levels, then we get quite different correlation behavior. Okay, so in the case where you have perfectly correlated site response, then you have this upper red term here, and when you have essentially no correlation in the site response, you're down at this level here. Okay, so what the Jerram and Baker paper is really saying is that they've looked at a couple of particular regions. Those regions have particular systematic side effects, and they have some implicit correlation structure in those data sets. And so then when they fit their models, they obtain curves that reflect those characteristics. What I'm saying here is that we can estimate for any region what the systematic side effects would be, and we can look at the correlation structure of those side effects for your region, and that would tell you specifically where you should be, whether you're at the red for a lot of correlation or whether you're down here with the blue correlation. And Professor Erdős showed yesterday that in Istanbul you have a very good VS30 map. Using that VS30 map, you can get a good model of what the systematic correlation should be in amplification functions, and look at what the correlation structure of that would be, and that would allow you to have a region-specific correlation structure that reflects your appropriate soil clustering. Okay, so how would you actually get that information? This is something I wrote last year, a couple of years ago, just to demonstrate how we can continuously make use of information as it arrives. So if you look on the left-hand side here, this is reflecting what we normally do with ground motion models. So we've got the flow of time down the board here, We've got each event coming in, event 1 down to whatever event we have. And what we do is every few years we stop and we grab all the data that's been compiled and we derive a ground motion model. Okay? Then we wait a few more years, all the new events that have come through, we stop again, derive a new ground motion model. Okay? So every few years in each region you have these distinct updates where the models change, and they might jump around quite a bit depending upon what's come in the interim. But if you do it in a Bayesian framework, what you can say is that you have a ground motion model that has some parameters, and then every time a new earthquake comes in, you take that data and you update the parameters. Okay? And you can do it in a way that it just continuously updates. Okay? So this is what we've done from looking at, say, a global database, and to say, let's systematically estimate what the systematic site terms are and see how they vary in time. So every vertical bar here is a new earthquake. Okay? And when that new earthquake comes in, it will have an impact upon your estimate of the site terms. So you can be progressively updating your site estimates with every new earthquake that comes in, whether that's an independent main shock or whether it's within an earthquake sequence. Okay? So this is something that's actually computationally very easy to do and could be done in the future. So the only other thing I want to talk about is how we can account for this non-ergodic concepts within sequences of seismic events for effectively aftershock risk analysis. So to do that, I'm just going to look at a case from New Zealand. So these are all the sort of crustal earthquakes in the New Zealand catalogue where we've got strong motion data. And I'm going to look at it in a non-ergodic way where I'm going to say there's some location-specific effect, but there will also be some cluster-specific effect. Okay, so if you have a particular aftershock sequence, there'll be some systematic pattern associated with that sequence, and then within the sequence you'll have variations from event to event. Okay, and these terms here will collectively represent the overall earthquake effect, but their variability will be quite a bit lower than what you have for a normal ergodic sequence. Okay, so identify using just a declustering algorithm these two clusters here, and I show you the effects of these. So this is the Canterbury sequence. This is the main shock. It sort of migrated to the east and then came back a little bit in the west with event size and the dates here. But if I look at the total database for New Zealand, these dashed lines here and here, as well as here and here, represent what the overall between event variability is for that whole data set. Now, if I look at just the event terms for the sequence, which are the red dots, these are the event terms for that sequence. And what you see is that the variability is significantly lower than what you have for the overall model. So the within sequence between event variability is very low, and that there's a systematic offset. Okay, so you can be progressively calculating this as each aftershock comes in and refining your loss estimates for that sequence as you come through, rather than using a generic ground motion model. Similar thing happens up in Marlborough, an overall systematic offset of the event terms downwards, which is the location and cluster-specific effect, and then lower within event variability. Okay, and if you look at that, this is the blue is the total data set, and then there's the sequences across different response periods. It's significantly lower for those sequences rather than across the whole data set. Okay, so the ground motion models need to try to replicate the characteristics that you would have from a far more complicated process where you are simulating or using a real ground motion series. We can't do that, but we need to make sure that when we are calibrating the degrees of variability, the amount of correlation, we're trying to replicate what that overall effect is. That applies to both the ground motion models, but also in terms of the ground motions we choose to use to calibrate our fragility functions. Okay? And at the moment, we probably aren't getting that interface handled as well as we should. When you're working with ergodic models, what you're effectively doing is inflating estimates of the variance and potentially biasing the correlations. This can lead to inflated risk estimates, but we also need to make sure we account for the epistemic uncertainty. Okay, so you don't just switch off the variability terms and get lower risk estimates without also considering how much additional uncertainty we have in what those actual location-specific effects should be. Where we are right now, we know that we don't have a big variation in sources and different crustal types. We know that this hazard and risk is dominated by very clean or very clear scenarios. Okay, so we should have a significantly lower event-to-event variability in that case. We don't know what it should be, whether it should be higher or lower, but we know that given it's higher or lower, the variability should be much lower. And we should have very clean paths and very clean source characteristics. So you should be able to invoke quite a lot of non-ergodicity for this region. Okay, and for a sequence, you can also account for this as well. Okay, so probably run over time, but thank you.
Thank you very much, Peter. It's an excellent talk about the importance of ground motions in risk assessment. We can receive one question from audience due to lack of time. Yes, please. The mic is coming. Bakın orada. Bakın.
Thank you for this very informative presentation. I was wondering, what are the critical aspects when we're coupling these hazard estimates or event scenarios that takes into account this systematic correlation while dealing with the calibration or empirical fragility or vulnerability generation aspect of it? So I guess we should not directly use the available fragility models with these with the ground motion fields developed using these approaches you presented. Is that right? Or in addition to that, how then we should progress into the fragility generation that takes into account properly this correlation aspect so that we don't double count the related uncertainties in our loss estimations?
Yeah, so one of the problems that often in projects you have situations where you're independently working on the hazard and the fragility at the same time, and so you don't have a lot of chance to interact. But in principle, when you're driving a fragility function and you're making a condition on a particular intensity measure, like say spectral acceleration at some period, then that's only one characteristic of the ground motions that are going through the structure. So what you want is to reflect all the properties of the other features that haven't been accounted for in the hazard analysis in the selection of your records that are then passed through the fragilities. And those other characteristics can vary from place to place because they depend upon the earthquake scenario and other things. So in principle, we should have some idea of what the hazard is for each level of hazard, each level of each return period. We should figure out what's the appropriate properties of the scenarios that dominate that level of hazard and choose appropriate ground motions that reflect that for the purpose of deriving the fragilities. And that would be a region-specific endeavor. That's rarely done. It takes quite a bit of extra effort, and it's not always clear what the appropriate scenarios are because we don't have a single site. Okay, we need to derive this model for a portfolio with many different spatial locations. So on the aggregate, we try to get it roughly right, but it's hard to know for a specific case whether we have done that. And the alternative of going, cell by cell and deriving fragility curves for that cell is tricky because then you need to have in that cell what are the characteristics of the prototype buildings just for that cell as well, and that's usually beyond what we can deal with. So it's important to get the consistency right, but it's easier said than done.
Thank you, Peter. The next speaker is Dr. Helen Crowley. Yeah. I'll bore you when it is like 30 minutes.
Yeah, thanks. Oh, no. That's not me. Where's Sergio? We decided to swap around the presentations of Sergio and myself because I'm going to talk a little bit more broadly about vulnerability models, and then he's going to go more into the details on vulnerability model development. So. and that's his presentation. I mean, we can put Sergio up first if you. Okay. Thank you. So Sinan asked me to give a presentation on elements at risk, fragilities, consequence functions, and vulnerabilities. And I decided to focus on the state of the practice in each of these components of a seismic loss and risk model, focusing a little bit on the research that we're doing to develop a European seismic risk model. And I'll be highlighting some of the challenges that we've faced in the development of these components of the risk model and where we might focus some of our research efforts in the future to address these challenges. So beginning with the elements at risk, so what we really mean here is the exposure model, the exposure. So we typically develop exposure models that describe the spatial distribution of the elements at risk. They might be buildings, but they might also be transportation networks, critical infrastructure, schools, hospitals. And we want to describe their key attributes in terms of what are their seismic performance attributes, what are their characteristics in terms of how they're going to perform under strong ground shaking in an earthquake, what's their value, how many people are in the buildings, how many of them are there spatially within our region. And we're doing this for the whole of Europe. We're developing a European exposure model for all of the buildings in Europe. Within the insurance and reinsurance industry, you typically have your own exposure portfolio. You have your assets that you're calculating the seismic risk and loss for. But comprehensive exposure models of all of the buildings can still be of use to estimate the ground-up losses as a benchmark, perhaps also to provide some information within a given country on what are the typical building classes within that country for that certain type of building, because perhaps you don't have that information in your portfolio. So as I mentioned, within this, it's a SERA project. It's a European project being funded within the Horizon 2020 European Commission framework, and we're developing a European risk model. We're describing the spatial distribution of buildings. We're focusing on residential buildings, but also commercial and light industrial warehouses and buildings for 46 European countries across the European continent. We're describing the buildings in terms of how many there are, how many people are in them, and also what is their total replacement cost, where that total replacement cost includes the structural, the non-structural, and the contents. We want to make all of these models available, so we're putting them in this web platform called the European, the European Seismic Risk Service, and over the next 6 months we will be releasing more and more of these models across Europe. We are only using public and open data to develop the models. We are then assigning Creative Commons open licenses. And we're also, not only will we release the models through a web UI, as you can see here on the screen, but also developing web services so that you can bring those models into your own tools. So for example, into QGIS or ArcGIS or whatever tools you're using, you can bring in all of the models and the data locally. So this is just to give you an image of what the exposure model currently looks like. We continue to update it, and we will be, as I say, releasing it April next year. We have 145 million buildings currently within this exposure model for about 45 trillion euros of replacement cost. This is showing the spatial distribution of the number of buildings on top of the European Seismic Hazard Map from 2013. And so as you can see here, we are in Istanbul. We have both a high level of hazard and also very high exposure to that hazard. The majority of the buildings in terms of the building count are residential, but when we then look at the replacement costs, obviously the importance of the commercial and industrial buildings is seen. So how are we putting together this European exposure model? As I mentioned earlier, we're using public and open sources of data. The first place that we go to is the census, the latest national housing and population census for each of those countries in Europe. This will tell us typically about the dwellings, the number of dwellings and how they spatially vary across the country, the built-up area. Some cases, in some countries in Europe, there is actually a building census, not just a dwelling census, so we also have directly the number of buildings, but in many cases we need to map the dwellings into buildings. We also look at the population, socioeconomic indicators such as labor force, floor area per employee. Oh, keep getting this wrong. Okay. Per economic sector, which will help us also to spatially distribute the commercial buildings. We also look at other European projects that have dealt with the building stock. One project is the Tabula typology approach for building stock energy assessment, where they weren't looking at the buildings from their seismic performance attributes, but from energy assessment, but still they were classifying buildings across Europe into different classes. World Housing Encyclopedia is an effort where they've asked a number of experts across the world to document the characteristics of the buildings, the seismic characteristics of the buildings. And there's also the PAGER effort where a global exposure model was developed for the whole world. Eurostat is another source, a good source of data where they've already collected the statistics of various census in the European countries. We also look at academic publications. There are a number of publications where the building surveys within different cities in Europe are documented and described. Lots of studies on building classes, on seismic performance of buildings in Europe. And then finally, we have to bring this all together, and this is where a large amount of judgment and local expert feedback comes into the process. We need to estimate what is the average replacement cost per meter squared, what is the average area per dwelling, what's the average number of dwellings per floors when we need to go from dwellings to building count. We also need to describe the distribution of different building classes in terms of their seismic performance. So what is the distribution of the reinforced concrete moment frames of 6 stories, of 5 stories, the unreinforced masonry low-rise wall buildings. This information is not in the census. This is the information we get from the local experts, from the publications, and we need to somehow map, excuse me, we need to somehow map the information that is in the census, which might just tell us the year of construction, the number of floors, and whether it's a single or a multi-dwelling, a family dwelling, or into those building classes. So a lot of the challenges that we face are related to this large amount of judgment that we have to put into the project, into the process. We don't have access to proprietary data. We're only using open and public sources of data. And even in some countries, the census is not publicly available, or the public data that is available from the census is not at a high enough resolution for our purposes. Reproducibility is an issue. There's a lot of judgment in the process. We are trying within the European project to document all of the different assumptions that we're taking so that someone can take the raw data from the census and follow through and reproduce our European exposure model. We think it's very important that there is reproducibility there. But in many past exposure models, that's not been available. And the uncertainties. We don't typically account for uncertainties in the exposure models, but we should be. Those assumptions on the average replacement cost per meter squared, the average number of dwellings per building, all of these uncertainties should be documented and somehow modeled and accounted for in the risk model. Much like the ground motion models that Peter was just mentioning, it's a very static process. We do this every few years. When the census was released, perhaps once every 10 years, we put together all the information and we produce an exposure model. It's very static, it's very time-consuming. It's not very easy to update these very large regional exposure models. So how might we address this going forward in the future? Well, quite similar to the ground motion modeling, we're thinking more of a dynamic process where things are getting updated more frequently and making use of all of the large data and technology that's currently being put into buildings. So, for example, we might use the OpenStreetMap buildings. So this is an effort to crowdsource footprints of buildings across the world, and it's not full, the coverage is not full, but there's a lot of buildings in Europe that have been mapped. So we might integrate that with our more traditional statistics-based exposure model. We might look at using satellite imagery and using semi-automatic algorithms to extract the footprints of the buildings from the satellite images. We might even use machine learning techniques where images of the buildings are used to identify where are the buildings, where's the floor, and counting the number of the stories, or also extracting the footprints. And then low-cost sensors. So within the RISE project, which is another European project which has just started, we're looking at how we can develop this dynamic exposure model, putting very low-cost medium quality sensors. They're about 20 euros each into buildings. They're accelerometers to get data from the buildings. Perhaps we can get from ambient noise, vibration, the dynamic characteristics of the building, the period of vibration, and we can start to use this structural health monitoring data and store it within an exposure model. So it can tell us about the characteristics of the buildings before earthquakes, but also after earthquakes. What is the structural response of that building as it was subjected to ground shaking? So we need to start to develop the process to bring all of this big data and technology together in an exposure model. The software, the web services, and the tools that will automatically extract and integrate these various sources of data. So this is our plan in this RISE project over the next 3 years. So moving on to fragility models, fragility functions. We've heard these mentioned a few times today. So fragility functions tell us about the probability of exceeding different levels or different states of damage given conditional on a level of ground shaking input. And although there have been various methods used in the past to develop fragility functions, from empirical methods to expert judgment-based, the current state of the practice is to use analytical-based modeling of the buildings. This allows us to account for the specific characteristics of the buildings within a given region. We can count specifically for the design codes that were used for the geometrical material properties of the buildings in a given region. We can also bring in hazard-consistent or appropriate ground motions, as Peter was mentioning, so we can produce different fragility functions in different places considering the characteristics of the ground shaking. And we use nonlinear dynamic analysis. There has been a trend in the past to use static analysis, but now it's very easy to implement dynamic analysis rather than trying to estimate what is the dynamic response from a static method. So what we're doing in Europe is to, together with putting together this exposure model of the different building classes, we're looking at the evolution of seismic design across Europe. So within each country, we are identifying when was the first time that a seismic design code was introduced in the country? When was it updated? So temporally, when did we see different types of design code? And we have 4 different design codes. No seismic design, so just gravity design. Low code, medium, up until what we call our high code, which would be a Eurocode 8 type of design. So considering capacity design, ductility requirements, so on. So not only are we looking at that temporal evolution of seismic design, but also how seismic design developed spatially within a country. So in this example in Croatia, when the first code was introduced in 1964, there were 5 different zones identified, and so you would have to change the amount of lateral force to which you had to design the building as a function of where you were in the country. So we look at the design codes that were introduced over time, and we look at how the lateral force coefficient was calculated in each country, and we try and estimate spatially how this varied, so both with time and spatially. And so then we can put that information also into our exposure model. So we have, as I said, 4 different design classes, and then we call it beta. Beta is just the percentage of the weight that was applied laterally in the seismic design. So we can have different values of beta from 0%, where it's just gravity load design, up to about 30% of the weight. So then when we're developing our fragility functions in our European model, as I say, we're using an analytical approach, and we try to represent the variability of the building characteristics. So looking at past data collected on buildings of that specific building type, for example, reinforced concrete moment frames, we can vary the story heights, the geometry, the layout of the buildings, and then we can produce a number of random buildings within that class. Then for each class, we do a simulated design. So we go back and say, for each of those 4 different design codes, for each of those values of lateral force, we can design the building, and then we can produce a model of that designed building, do a pushover analysis to get an understanding of what is the lateral strength and deformation capacity of that building, of those different buildings that we've simulated under the different design conditions. And then we transform that multi-degree of freedom system into a simple single degree of freedom system, or we might have 2 single degree of freedom systems for each direction of the building. And then we run, as Peter was showing in his presentation, an analysis where we take a number of different records, We subject that single degree of freedom system to those records, we look at the response, and we apply a regression to relate the input ground motion we're putting into our representative single degree of freedom system with its response. As was mentioned previously, in a European, in a large regional model, it would be difficult to select hazard-consistent ground motions for every single location, every single country, within each country. So we're not currently doing that, but the framework is set up so that you could replace the ground motions with hazard-consistent ground motions at the specific site that you're considering. But we're considering more a wider range of ground motions because we're just developing a single set of fragility functions to be applied across the region. And then once we have this regression, we need to identify when is it the damage is reached in terms of displacements. So we have a model to identify when is the threshold, the displacement threshold to different levels of damage, light damage, moderate damage, extensive damage, and so on. And then putting these two components together, we can calculate for a given level of ground shaking, what is the probability of exceeding those different levels of ground motion, and that's our fragility functions. So there's a lot of existing fragility functions out there. There's a lot of empirical functions, analytical functions that have been developed over the years, and you can find them within the Global Earthquake Models Vulnerability Database. And we will be putting our European models in this database. We're also going to put some more models that we've identified from European research into this database and have a European version of this vulnerability database. So you can select the region of interest, maybe the material, the lateral load resistant system, and then you see the various fragility functions, and you can see them and then go into more detail, find out exactly how they were developed, what methodologies were they using, what uncertainties were they modeling, and then get exactly the values of the fragility functions so that you can use them in your risk calculations. So one of the challenges of, for example, such a database or all of the different research that's been carried out on fragility functions is that not all of the methods are considering the same uncertainties. And the question is, what are the predominant uncertainties that should be modeled when developing a fragility function, and how should we quantify them? So the main uncertainties, I'll just run through the main categories of uncertainties that are considered. So building variability, I already mentioned before, both within the building and between buildings of a given class is typically modeled. Something that's often not addressed is modeling uncertainty. So we've decided to use a specific modeling approach. We're going to use maybe fiber element or plastic hinge modeling or finite element modeling for our structures, for our multi-degree of freedom structures, or for our single degree of freedom models. And the uncertainty of choosing one approach as opposed to another is often ignored. Also, once we've selected a given approach, we need to identify and model the uncertainty on that approach. So let's say for a given plastic hinge model, the uncertainty and the parameters of that model needs to be accounted for. I showed you before those different thresholds to when damage occurs. There's obviously uncertainties and what is the displacement at which damage is occurring. And then ground motion variability, putting in the records with the different characteristics and accounting for that ground motion variability when modeling the fragility functions. And I've seen a few different papers that are inconclusive. I'd say that the research is inconclusive on which is exactly the most important of these uncertainties to model, or what's the relative importance. Most authors agree that we have to get the ground motion variability in there, but is the next most important the variability of the building, or is it the model uncertainty? I think probably most of the research has tended to underestimate modeling uncertainty, has not accounted for modeling uncertainty, which could skew some of the conclusions on what the most important certainties are. So let's talk a little bit about modeling uncertainty. There's more and more access to experimental results, tests on components, on full-scale buildings in the literature. And so if we're going to model a given class of buildings with a given modeling approach, we should use that literature to test, to calibrate our numerical modeling approach. But even if we take a selected modeling approach, we test it as much as we can against past experimental tests, we do see from many blind prediction exercises that even if our model is plausible, there still can be a large variation between what was predicted and what's actually observed in these blind prediction tests. So this is an example from a blind prediction contest for a simple concrete column. You're seeing there the different levels of the earthquakes to which it was exposed, and then the variation in the responses given by the different teams that applied to this blind prediction exercise. And while I'm not saying that all of these models were necessarily plausible, there may have been some modeling errors in those results that we see there. At least between the winners, there's actually a wide range of response predicted for that concrete column. So even if you have tested your modeling approach and calibrated against past tests, you still should try and attempt to include sensible variations of that model when deriving fragility functions. It's difficult to do. It's a lot of work if we're already looking at 20 different building classes and we've got to calibrate each building class to each experimental test and then vary the modeling uncertainty as well as the building variability and the ground motion uncertainty. It starts to become a very time-intensive task. So maybe we could use past results or other people's studies to try and put that modeling uncertainty back into our risk model through engineering judgment, but we still need more of these studies on what is the dimension of modeling uncertainty so that we can account for it. But once we have some idea of the modeling uncertainty that's going to give us this variation in our fragility functions, we could bring it into the risk assessment, perhaps with the logic tree. Logic trees are used frequently in the modeling of different ground motion models, in the hazard assessment of the risk model, but often we don't account for the epistemic uncertainty in other components of the risk model. So we might take and reduce this modeling uncertainty to a few different fragility functions and assign different weights to them and take them from the full modeling uncertainty to make this more manageable within the risk assessment. Just coming back, I just wanted to say something again about sensors in the buildings. So if we are putting low-cost sensors into our building stock and we're getting some data from those sensors, that can also be used to help us to reduce the modeling uncertainty. We may get the frequency characteristics of the buildings, the dynamic characteristics of the buildings, and we can use that just to test against our numerical model to make sure that we constrain our numerical model for that specific building or those specific buildings for which we have sensors. And then this came up also yesterday that if there is an earthquake and we have sensors in the building, then we have the actual level of ground shaking to which that building was subjected. We may also have the response if we can put some sensors also through the height of the building. And so within the assurance activities, this could be used to give us a very rapid estimation of the damage or loss to which that building has been subjected. If we already have a calibrated numerical model for that building, then we get the response of that building. We can very quickly assess what was the damage, the likely damage of that building. This could help us to prioritize the post-earthquake damage inspections by going first to those buildings which our models are telling us are likely to be the most damaged. Oh, and also parametric insurance triggers, I assume will come up in the discussions maybe later today. And rather than basing those on shake maps, they could actually be based on the data coming from the sensors of the buildings. So the last thing I wanted to talk about was vulnerability models. I just have a few slides on this. As has already been mentioned, the vulnerability tells us of the probability of loss conditional on the ground shaking. And so by first developing analytical fragility functions, we then need to combine these with consequence functions to get our vulnerability models. Typically, consequence functions are heavily developed and derived using empirical data from past earthquakes. So the consequence function tells us about the probability of loss conditional on the damage state. So we can collect data, as we saw yesterday in Marco Di Ludovico's presentation, all the data that's being collected in Italy now to produce a new consequence function for the repair costs for Italian building stock. This is actually an older model from 2006. So we can have both deterministic models. We could just have a single value of what is the mean ratio of cost of replacement to cost of repair given the damage, or also more realistically model that as a distribution. But it's not just about repair costs. We can also produce these consequence models for injuries, for fatalities, for downtime, and so on. So in the same platform that I showed you earlier, there are some existing consequence models, or damage to loss models, as they are termed in this database. And there are also a number of vulnerability functions. And so as before, you can select for the given country, the vulnerability model, and then get exactly that data from the software. But one of the main issues, I believe, with such a database with lots of different models from around the world, from different authors, from different studies, is which should we be selecting from such a database? Which ones should we be using in our risk models? And so, as was shown also earlier by Professor Erdig, we can test our models using past earthquake events. So we should be carrying out systematic verification of our consequence models, also our fragility functions, and when they're combined as a vulnerability model. So if we estimate the damage or the losses from past events, for example, by taking shake maps from those past events, which are maps of the spatial variation of the ground shaking from that event, constrained by recordings that may have been made of the ground shaking in that event, we can put it together with our exposure and our vulnerability and estimate the losses today. We just need to make sure that we adjust the losses from the past events to today's, where there's also uncertainty in that adjustment. We need to be mindful of that uncertainty, but we want to at least make sure that there isn't significant bias in our model and that results we're getting, it's a sanity check, that they're reasonable. And so potentially I was thinking that in that previous database I showed you, tools could be set up to do this automatically. So once you've selected a number of different functions, they would run through a tool to take the shake maps, run the analysis of the damage and the loss, and then make comparisons to make sure that it's a reasonable set of models that have been selected. So some of the challenges is that there really is limited open or reliable data for developing vulnerability models, so on the consequences from past earthquakes. In particular, when it comes to injuries and fatalities, there are quite a lot of databases, detailed databases on the damage to different building classes, but not on the injuries or the fatalities of people within specific buildings that is openly available. And so future efforts to standardize these sort of open databases and make them publicly available to the research community should help to improve the models and the risk models that we're developing. And just in that direction, I just wanted to say a few words about these types of research infrastructures. So another outcome of a European project was to set up the EPOS, which is the European Plate Observing System Research Infrastructure Consortium. It's a very long name, very complicated, but mainly the main objective is to develop services tools for accessing and integrating open data. So there's metadata associated with the data, Creative Commons license, DOIs, and so on. And within, EPOS is a big organization, but within EPOS seismology, a consortium has recently been set up, which is the European Facilities for Earthquake Hazard and Risk. And the main objective of the EFAIR consortium is to maintain services and data related to seismic hazard and risk. So all of the data and the models that I've presented to you today, so the European exposure model, the fragility models, they will all be made available through the EFAIR consortium. So even when the SERA project finishes, it doesn't mean that model stops. There will be funding to continue to develop and improve those models. And as I showed you earlier, these will be made available through this European Seismic Risk Service website. And so I would be very keen to talk to you about your needs of such a service. You're all stakeholders of such a service. So what are your needs, and do you have any ideas also on how we might maintain the future costs of sustaining these services and data? Okay, thank you.
Helen, thank you very much for this timely presentation and very nice, interesting. So Helen, in a way, summarized the global European perspective of risk modeling. I think much of the effort has gone to fragilities and trying to, I mean, in my talk also I'll try addressing more or less the same thing, but for Turkey scale. Any questions for Helen A question could be, yeah, please. Yes, please.
Hi, Helen. I would like to basically comment on your very last sentence on your slide. So what are the needs? So I'm wondering about your exposure model that you're going to create in the SARA project. You mentioned that in the industry we will basically work with our own exposure portfolios, and let's say the reason why you're building this exposure model is more for, let's say, economic loss, ground-up estimations, things like that. But to be honest, I mean, the portfolios that we have in the insurance industry are pretty far from perfect, I would say.
Yeah.
So I was wondering, could we use such a model and feel confident about it when we have, let's say, incomplete client data, or sometimes I would call them suspicious client data, because if they maybe don't know specific exposure characteristics like the building type, you might see some bulk filling and everything is suddenly reinforced concrete with shear walls. So could we use such a data set to first of all test our client exposure, or in the case of incomplete data to do something what we call data enrichment? Would the granularity be good enough to do that with without having too much of a bad feeling with it?
Okay, I think I mentioned this actually on my first slide, that I thought that that could be a use of such a database, that when your portfolio of assets, you don't have the information on the building classes, you could look to such a European exposure model, and because we will be separating residential, commercial and industrial buildings, you could then look at the building classes and the distribution within our European model. One thing that we will do is that there is a large variation in the quality of the data in our European exposure model across Europe. As I showed you, we are mainly using census data. Some countries have a very good building census. Other countries do not focus much on the census, and the information is mainly just on the dwellings and the population. So we do also want to, together with the exposure model, I forgot to mention, but also provide some sort of qualitative index on the quality of the data, considering the sources and the assumptions and the judgments that we made. So that would help you to understand if it is better or just as good as the data that you have. But if there are any specific tools that we can do, we can think about that to help you extract what you need from the database. But as I said, this data will all just be openly available, but maybe we can think about some specific tools that will allow you to compare and things. Yeah.
Just a very short follow-up question. Are you aware of any similar projects for other regions in the world, like Asia or Latin America?
Well, the Global Earthquake Model has been doing these efforts to develop the exposure models in many regions where there wasn't already. So not in the United States, for example, because there's already good data for hazards, but yes, in Central America and South America. And so they released, GEM released their global seismic risk model in December last year, but they're using this year just to make sure to test and calibrate, I think, before releasing the exposure models. But we can look into what's currently available. I know that they have released, I think, in Africa and maybe even Central America, some exposure data already.
Thank you. Professor Scalthorne?
Thank you very much. Helen, thank you very much for a very interesting talk. Very quick question. Perhaps I missed it. What was the resolution of the European exposure model?
Okay.
Is it building, or is it on a grid, or postal code, or what?
Very good question. I should have addressed this. So each country, we collect the information from the census at the resolution, the highest resolution at which it's available. So it is varying across Europe. What we want to do, or what we will be doing in the European risk model, is to then try and disaggregate that data onto a higher resolution grid using proxy data sets like World Pop or other nighttime lights and other sources. Yeah.
Thank you.
Just a quick question from, yeah, the mic, please. Yeah, it's coming.
Thank you. There is an effort in Asia at Nanyang Technical University,
Singapore, right?
Singapore,
Yeah.
to develop exposure database for Asia. So that's additional information. I have a question for you. How do you estimate the height of the buildings, which is an important parameter?
Height of the buildings, how do you...
Height.
Yeah, so how do I expect it to...
How do you estimate it?
Oh,
How do you come up
estimate
with
the
an
height?
estimate of the height of the building? Since
So-
you're not using remote sensing,
Yeah.
how do you do it?
Yeah, so this is coming from local experts where they will tell us the most likely distribution of the heights of the building as a function of their use. If we have from the census that it is a multi-family dwelling, then we know it's more likely to have more stories than if it's a single family dwelling. Some of the census do provide the number of floors, data on the number of floors as well. So in some cases we have the height. But this is the reason that each country has different levels of details of attributes. That's why we need to provide also information on what we have inferred and what we actually do know.
Why did you elect not to use remote sensing, at least for sampling, maybe?
So this is where we're going. So the future is to start to use remote sensing. Yeah, that's where we want to go.
Thank you very much, Helen.
Thank you.
Thank you very much. Thanks. Okay, so let's move to next talk. Professor Lagomarsino will be presenting, again, European perspective for vulnerability, regional vulnerability. Professor.
Thank you, Sinan, and good morning to everybody, and thank you for inviting me to this interesting workshop. Okay, my presentation is related to fragility. So in the previous presentation, we have a comprehensive view and perspective of hazard and not only fragility, but exposure. But I will deal in particular with fragility curves, looking at different issues related to what they represent, what do they depend on, how are they can be obtained, and how can be used. Let's start with what the fragility curves represents. You know that vulnerability is a component of the seismic risk and loss assessment. So you have, in order to evaluate the losses, you need to know the hazard in the area and the exposure and the classification of the building stock and the population. And vulnerability and fragility represent the correlation between the seismic intensity and the damage, and with consequence function you can move from damage to loss estimation. So this is a process that is intrinsically probabilistic and can be evaluated through a convolution integral, well-known convolution integral, in which the the expected rate of losses in a given time, and the losses can be of different type, obviously. This loss is due to damage that occurred in the building, so a structural damage that can be correlated with performance of the building and then losses. And it is necessary to establish this correlation, which is the fragility between the intensity and the damage. Only few slides just to summarize what is the input for the fragility. On one side, the hazard is represented by a hazard curve that can be obtained by probabilistic seismic hazard assessment and gives the annual probability of exceedance of a selected intensity measure of the earthquake in a given point of the area under investigation. And starting from this, you can perform different kind of seismic risk analysis, a time-based analysis in which you evaluate the convolution of all the contribution of all possible earthquakes that can arrive in the site with different return periods. but also an intensity-based analysis in which you evaluate the losses with reference to a specific earthquake intensity associated to a specific return period, or even another conditioned risk analysis is related to a scenario-based analysis in which you consider a specific deterministic earthquake with a given magnitude, epicenter location, and so on. So in that case, you have an idea of the earthquake in the region and the attenuation. Rather, in the case of using a probabilistic seismic hazard assessment, you can consider in a big region the unconditioned scenario. Obviously, you can perform risk analysis at different scale. You can perform for the whole country, and I will show an example of analysis that we performed last year for the Civil Protection Department related to the seismic risk assessment of Italy. But you can concentrate on a specific region, a smaller region, or even a single municipality. But the problem is that fragility curves must be related to the exposure and to the characteristic of buildings. And in this case, you can analyze building stocks, in particular residential buildings, that are usually, and data in this case are aggregated in sub-areas, so the resolution can be the municipality or even smaller areas, or building portfolio related to a group of single structures, for example, schools, strategic building, and so on. But in all cases, the aim is to have a picture of the losses and risk to at the territorial scale, not to the single building, because model that we adopt for this analysis, in particular fragility curves, are related to the behavior of a typology of building, not of a specific building. And for this case, as I will mention in the next slide, many uncertainty and dispersion have to be considered. So in order to deal with the exposure, and in particular the characteristic of the building stock, you have to classify structures. So it is important to define a taxonomy. Taxonomy means that you have to select the attributes that influence the seismic behavior of the buildings, and then classify your building stock by grouping buildings into groups with specific combination of tags of the taxonomy in order to that are characterized by more or less a similar behavior. The problem is that taxonomy and classification must take into account the available information. So, for example, this is a taxonomy proposed by GEM some years ago, in which a list of 13 attributes are present, the material, for example, the 8 of the buildings that can be grouped into classes of low, medium, and high rise, for example, the irregularity in plan, in elevation, and for all of these attributes, you can have different possible options. So if you combine all these attributes, you end up with a huge number of classes, but you cannot define at the end the fragility for each subclasses, and also most of these subclasses have more or less the same behavior. So it is important to combine in a proper way these these attributes and define properly the classes. For example, using the data from the ISTAT, from the census of population in Italy, we have data at the resolution of a municipality for all Italy, disaggregated in terms of population, number of buildings, number of flats, and size of the flats, and in terms of attributes for the vulnerability. We have only information on the material, if the building is masonry or reinforced concrete, the number of floors. In particular, we can group buildings in terms of low, medium, and high-rise buildings, and the age of construction. So the subtypes of buildings for which we need to define fragility curves come up from the combination of these attributes: material, building height, and age of construction. It is clear that define for each combination a fragility curves, a set of fragility curves that are good for all Italy is a problem, because we have a regional characteristics of the buildings. So in this year, we are working together with other research units within the ReLuis project to regionalize fragility curves, so identify sub-regions in which fragility curves are different. For example, if you look in the table, if we consider two regions in Italy, for example, Emilia-Romagna region, which is in the north part, and Abruzzo region, which is in central Italy, and you look to the distribution of buildings in terms of characteristic of masonry, brick masonry or stone masonry, or characteristic of horizontal floors, if they are vaults or timber or steel or reinforced concrete diaphragms, you can see that the characteristics are very different. But in the census database, we know only that there are masonry buildings and reinforced concrete buildings. So we can perform some surveys on small areas, but statistically representative, and define specific fragility curves in order to refine the assessment. If you go to the level of at urban level, the definition of fragility curves should consider more in detail the characteristic of the buildings. I don't have time to go into details, but this is an example of a research that we performed in Lisbon on a specific district where we defined we identified the different type of buildings and specific structural details, and we performed a logic tree by considering the combination of different possible characteristics, analyzing by nonlinear static analysis the behavior by pushover analysis, and grouping these branches into 8 different types in order to have a more accurate analysis. But let's move to the definition of fragility. In order to define the fragility curves, we need to define the damage metric. Usually, we consider damage as a discrete parameter in terms of damage levels or damage states. We can refer, for example, to the 5 grades of the European microseismic scale. But these can be also, if you use a mechanical approach, referred to performance level and correlate these damage levels with the engineering demand parameters like the interstory drift or displacement, roof displacement. So at the end, fragility curve represent, as Ellen mentioned before in the previous presentation, the probability of occurrence of a given damage state as a function of an intensity measure that can be, for example, the peak ground acceleration. So what do they depend on? So which are the uncertainties that are involved in fragility curves? Fragility curves are usually defined by a log normal distribution. So for each damage state, you have two parameters that are the intensity measure, the peak ground acceleration, that the median value of the intensity measure, so the one that has a probability of 50%, and the dispersion beta. This dispersion represents the slope of these fragility curves and is related to the intensity measure of the 84 and 16% quantiles. This dispersion is really important and depends on many parameters. First of all, the effectiveness of the intensity measure that you are using, but also the homogeneous behavior of buildings in the class that you are considering. So you can consider that this dispersion is given by at least three contributions. One is the record-to-record variability, because fragility curves is defined by an intensity measure, but it is clear that this intensity measure is not a complete description of the input, the seismic input. So you can have for the same intensity measure different records and different response pattern and so on. You have a dispersion related to the capacity, which is inside the building, because you really don't really know the parameters, mechanical parameters and properties of the building, but in particular in risk analysis, when you work with a group of buildings, you have a dispersion from one building to another building within the same class. So you have to consider this, and there are methods to take into account this uncertainty. And you have also a dispersion related to the definition of the damage levels, which are discrete damage level, but must be related to a damage which is actually a continuous process of increasing damage. So at the end, the fragility of a building stock is represented by a set of curves that may be defined, for example, by the intensity measure, median value of the intensity measure of one of the damage levels, for example, damage level 2, and then the dispersion, and the distance between this intensity measure related to the different limit states. So with this group of parameters, you can define a complete set of damage levels, of fragility curves. Once you have a set of fragility curves, you can derive for a given intensity measure a damage level histogram. So by considering, for example, for this intensity, you have a damage histogram. That means that due to the uncertainties, you cannot associate to a specific intensity a specific damage level, but you have a distribution of this. Let's look at the influence of the dispersion in the evaluation of the damage. This is a specific case in which you have, for example, a dispersion equal to 0.6 and a set of fragility curves. If you enter, for example, with a PGA of 0.2 G, you have this distribution of damage, and with 0.4, it is evident that damage increase. But with the same values of the intensity measure associated to the different limit states, so the 50% is the same in these two cases, but the dispersion in this case is increased to 0.9. For the same values of the p-ground acceleration, you obtain a very different distribution of damage. In particular, if the dispersion increases, the distribution of damage is more scattered, so you have an increase of dispersion in the damage levels. On the contrary, if you keep the same values of the median intensity measures, but you reduce the dispersion, you obtain a distribution of the damage states which is more sharp. Another parameter that influences the damage estimation is the ductility, that is the distance between the different curves. In this case, the dispersion is the same, but here you have a bigger ductility. That means that if the value for intensity measure for damage level 3 is the same, in order to have collapse, you need a higher value of the p-ground acceleration. So in this case, you can compare again the distribution, and you can see that if the ductility is bigger, you have a more sharp distribution of the intensity of the damage level. So move now to the methods for deriving fragility curves. There are many approaches. In particular, Ellen showed the possibility of mechanical-based methods. There are also empirical and observational methods, or expert-based methods, and also hybrid methods. This is an example of deriving fragility curves from empirical observation after L'Aquila earthquake for reinforced concrete structure. Due to a systematic survey of damage after the earthquake, and considering the shake maps, it was possible to define the empirical fragility curves for low-rise, medium and high-rise building. And this is the same analysis, but for masonry structures, considering irregular and regular structure with flexible floors or rigid floors and so on. The size of the dots are related to the number of buildings from which this statistic was performed. But as you can see, as you can see, empirical data are not always very regular, and so the derivation of fragility curves only from empirical data is tricky. For example, there are cases in which for low intensity measure, you can observe usually a higher damage, and this is because often in an area where the intensity is small, the damage survey is not complete. So you don't have all the data, and data that are missing are without damage. So you should reduce this value that here you can see that sometimes you have a sudden increase of damage with a small increase of intensity. Regarding mechanical based approach, there are different options: analytical simplified methods, numerical methods by nonlinear static analysis, numerical methods by nonlinear dynamic analysis, and mechanical-based methods are really powerful because you can take into account the specific structural features of your buildings. You can take into account the dispersion, the variability of material parameters and structural details and so forth. But a problem is the model uncertainties, and in particular the bias that sometimes these mechanical models has. So sometimes, usually from mechanical approaches, from models, numerical models, you obtain fragility that are on the safe side with respect to the one that derive from observed data. Another option is to consider the expert judgment. This is an example of an expert elicitation made some years ago during the World Conference of Earthwork Engineering, Lisbon. But as you can see, the dispersion provided by different experts for classes of building is very huge. A method that can be classified as expertise-based or heuristic is the macroseismic model that was developed by myself and Sonia Giovinazzi many years ago. This is a method, vulnerability model that derived directly from the European macroseismic scale, which implicitly contain a vulnerability model because define the intensity through the damage observation. So you can derive from the intensity the damage that is expected to occur. In this case, the damage is defined exactly in 5 damage states, and the vulnerability is associated to different classes. Classes, as you can see, are not related directly to building types because it is stated that each building type, for example, unreinforced brick masonry, can behave in a different way depending on many other parameters. And at the same time, different types of buildings, both masonry and reinforced concrete, may have the same belong to the same vulnerability class. I mean, they behave in terms of correlation between intensity and damage in the same way. So this is the building typology matrix of the European macroseismic scale that define 6 different vulnerability classes, and each vulnerability class represents a correlation between the intensity, the seismic intensity, and the damage, and associate these vulnerability classes in different way to different building types. So the idea is to start, we started from this definition of the European macroseismic scale that is incomplete and not defined in quantitative term. We complete this building with damage probability matrix using the fuzzy set theory and using the binomial distribution. At the end, we obtain curves that give you the mean damage grade for each vulnerability class as a function of the macroseismic intensity. and you obtain different damage levels, increasing the intensity. And this is the relation as a function of two parameters that are this vulnerability index and another ductility index. I don't have time to go into detail. So this method was used in the literature a lot in the last 15 years, but was directly derived by the macroseismic scale without a real validation by observed data. Last year, thanks to the ReLuis project and the Italian Civil Protection Department, we had the opportunity to use the DADO database, which is a database that contains the damage survey after many earthquakes in Italy since Friuli in 1976, and we have data on more than 300,000 buildings. So with this database, we have a correlation between intensity and damage, and we performed this validation. I have no time to go into details, but it was not a simple task because, for example, damage is defined in terms of damage levels in each single element of the building, so it is difficult to define an average damage level for the building, and this influences the damage distribution. But at the end, we observe that the binomial distribution is good to describe the damage distribution, and that increasing the intensity, you have more or less a clear path of increase of the mean damage grade. It is also evident from this data that, for example, the vulnerability of masonry buildings decreases significantly with the age of construction. This is the mean damage grade from the L'Aquila earthquake for buildings built before 1919 and up to modern masonry building that has usually very low damage. These distributions are very scattered because are related to different intensity. But if you go into take into account the intensity, we validated this curve, changing a bit the formulation, and also using the DADO database, it was possible to define modifiers in order to refine the vulnerability depending on the type of masonry, quality details. I go quickly because I want to show you the results at the national scale. So what is important is that with this macroseismic model, it is possible to derive by a correlation between intensity and peak ground acceleration, to derive fragility curves, set of fragility curves in an analytical way. So you can obtain directly the peak ground acceleration for the different limit state as a function of this vulnerability index that was derived by empirical data and using some coefficient related to the correlation between intensity and peak ground acceleration. At the end, the idea is to implement fragility curves for the vulnerability classes, and when you have a specific group of buildings, define the vulnerability index and combine different vulnerability classes. So, for example, if masonry buildings built before 1919 of low rise has a vulnerability index from damage observation, which is 0.95, as this is between class A and B, this means that you can consider that 80% of the buildings of this class are in class A and 20% are in class B. And this is coherent with the definition of the European macroseismic scale. So the fragility curves are only the one related to the vulnerability classes, and for each group of building, you simply define a vulnerability index, and from this you can derive how to combine this set of fragility curves. We tested this method with the scenario of L'Aquila. This is the simulated scenario, and this is the real data. As you can see, the results are quite good. You should see that here the data from the DADO database produce a lot of damage, but as you can see here, okay, I finish my time. Sorry. In these municipalities, the survey was not complete. So this is the problem of empirical data. And this is the comparison between damage scenario in different municipalities after L'Aquila earthquake, and a comparison between the observed in red and the estimated in blue. Finally, the result by the national risk assessment made last year with IRMA platform that was developed by EUCenter and they use OpenQuake as an engine for the calculation of the risk. These are typical results of IRMA. We have consequence function to derive casualties, usability, and economic losses. And this is the last slide in which the results obtained by different groups within the project, the results obtained by different groups in terms of casualties, in terms of cost, economic losses in 1 year. You can see that the median value is 2.1 billion euro as expected annual loss in Italy, and this is compatible with the value that Stefano Pampanin showed yesterday of 120,000 in 50 years. And the range obtained by the different groups is between 1.2 and 3.2, so not so big. Also, the number of casualties was more difficult to estimate, but it is compatible with the one observed in the last 50 years in Italy, that is more or less 100 per year. Okay, with this I thank you for the attention.
Thank you, Sergio. A very good presentation about the assumptions in developing fragilities, how they are affected, the loss and vulnerability. Any questions for Sergio from the audience? Professor Erdik?
Thank you, Sergio. Very good presentation, and the subject is very valid. The question I'll be asking, in fact, I should have asked to all the other presentations as well, that we don't hear much about the consequence relationships. So how much money is to be paid for a given damage level? I mean, you have conducted any study in Italy on those bases?
Yes, this is a critical point, the consequent function, and we are working in the Reluis project also with Marco Di Ludovico on this topic this year and in the next 2 years in a new project. The results can change dramatically, changing the values in this consequent function, but also it is important to look at on how you integrate, you make the convolution of risk. Because, for example, I had no time to show this, but we observed that the contribution of low-intensity earthquakes is very important, as you know, because these earthquakes produce small damage, but has a high probability of occurrence. But in this case, fragility curves, log-normal fragility curves, may be not accurate and not validated for low-intensity values. So we observed that if you integrate the total risk starting from very low values of intensity, you add a lot of contribution that probably are not physically realistic. So in the case of the project I mentioned, we started from a threshold under which we assumed that there is no damage and no cost for repairing. This is very important because otherwise we obtain billions of euros, but they are not realistic and they depend mainly on this part of the fragility course.
Okay, thank you very much. Unfortunately, we have to move to complete the session, morning session in time. If you don't mind, I'm going to spot myself over there because I have to see the screen. So what I'll be presenting you is actually the basic steps we followed in developing the sort of risk model for 2 projects, namely the TCIP project and the project that is granted by Turkish Insurance Association. So the most important points or the modeling, say, perspective of ours, I'll try to describe them to you here. But before that, again, I rather prefer starting with some basic definitions because these are important, I believe. So the earthquake risk modeling actually is the way how we measure the rate or probability of an undesirable outcome, which can be described as structural or non-structural damage. It could be collapse, total collapse, or it could be loss, such as repair costs or downtime payment and so forth. The components of risk modeling, again, has been described many times this morning, or talked about the seismic hazard, which is the measure of rate of ground motion intensity level we are interested in, we're using in our calculations. The fragility functions, they measure the probability of a damage state conditioned on the ground motion intensity we are using in our calculations. And then we have these consequence functions that relate the damage state with a consequence of interest, as I told you, like repair costs or downtime payments and so forth. So when we combine the fragility functions and consequence functions, again, described by many speakers this morning, we get the vulnerability model, which is some sort of measure of loss conditioned on the ground motion intensity we are using. Essentially, when we consider each one of these components contributing to risk calculations, it is easy, oops, sorry. Oops. Okay. It is easier, the calculations are going to would be easier if you have a single seismic hazard curve, single fragility function, and then a single consequence value. But this is not the case, again, addressed by many of the speakers this morning, all of the speakers this morning. So instead of a single seismic hazard curve, essentially you have a band of, say, hazard curves or a suite of hazard curves describing the upper, lower, upper, and central trends in the hazard. And then you have, again, not a single, you don't have a single fragility function, but a band of, say, fragility functions, again, describing the lower, upper, and central tendency. And of course, in terms of consequence functions, you don't have a single point, but again, a band of, say, consequence, say, values like replacement cost ratio. So then you have to consider the interval to really account for your uncertainty in the risk assessment. All right. Okay, so the objective of this talk is actually very limited. I'm going to present you a loss estimation model only for residential building content, for large building inventories that can be used in premium calculations, earthquake premium calculations. So this is going to be the real topic of my talk. And the emphasis are going to be set in these 3 bullets here. So I'm going to describe the model uncertainty in fragility and consequence functions, and I'm going to show it to you through Monte Carlo simulations because the idea is very simple. I'm going to describe you the development of content fragility functions that are sensitive to different building types. This was one of the challenges in the project that I mentioned to you by considering total probability theorem, but the theory up behind it is very simple, actually. And then I'll try to show you the progressive influence of fragility and consequence modeling uncertainty on the loss, the result. All right. So before into the details, I have to acknowledge the support by many researchers here and also the entities. So firstly, Turkish Earthquake Foundation, Turkish Catastrophe TCIP, or DASK as we call, and Turkish Insurance Association. These entities really provided the grants for us to run this project. Professor Mustafa Erdik as project coordinator and also a, say, real mentor for risk modeling contributed a lot to these projects. Dr. Cüneyt Tüzün and Dr. Can Zülfikar, they were responsible of compiling content database and then content fragility literature. And Dr. Özeray and Professor Altuğ Erberik, they were responsible of building fragility models for us. And then Dr. Mine Tümsa, she was responsible of seismic hazard and GIS-related work. Professor Ufuk Yazgan, he was really responsible of risk modeling, and he's here, yeah. We had tremendous hours of discussions about risk modeling. And then Dr. Merve Çağlar, she was also responsible of risk modeling and software development. So this is sort of the team we have in these 2 projects. So this is the basic modeling strategy we followed. I mean, nothing really interesting after hearing all the talks we had this morning. So we established building-sensitive content fragilities by making use of total probability theorem and Monte Carlo simulations, because now the computer, say, power is enough for running millions of Monte Carlo simulations to account for model uncertainty in building damage and content damage, conditioned on building damage. And then we establish our consequence functions. We partly use expert judgment, and also we use, again, the simulation, again, to account for model uncertainty in replacement cost ratios conditioned on content damage. And then when we use these two components, we establish content loss for building types in the inventory conditioned on ground motion intensity. And then we combine these two and get the loss, average annual loss ratio for the entire country. So while running the whole thing, because we had to make some simplifications, we assumed that seismic hazard is just the mean hazard. So we didn't really focus on the uncertainty involved, modeling uncertainty involved in the seismic hazard. So we just accepted seismic hazard as is, and we used National Seismic Hazard Study in this case. So what I'm going to show is actually mainly the modeling uncertainties affecting our calculations from these two components. All right. As for the seismic intensity, we chose macro seismic intensity, MMI. There are pros and cons of using MMI. Firstly, let me summarize the advantages of, why we picked MMI as our ground motion intensity measure, because we have a well-compiled fragility database in terms of MMI. We augmented that database with those of analytical studies. And also, though it's speculative, but it is suitable for large building inventories because essentially it is building period independent. So in that case, it provides some sort of easiness in the calculations. The disadvantages of ground motion intensity measure, essentially, it would not really directly reflect the important ground motion features, such as, say, directivity or directionality. You don't have a full control on such ground motion features if you use MMI scale. And also, it may not fully reflect the content damage because you see there are different types of contents we are dealing with, and then some of them are acceleration sensitive, some of them are drift sensitive. So microseismic scale in that sense is a bit really like a coarse scale to describe the content damage. But anyway, you'll see with the assumptions you can overcome some of these disadvantages. So firstly, I'm going to talk about more on the building sensitive content fragilities. I'll give a brief, say, background about its theory. So what we are doing is actually we are decomposing the content damage probability into its components. This is really by Professor Yazgan, Professor Erdik, and by myself. We discussed about this, and we came up with this type of, say, procedure. So essentially, oops, let's see. Yeah, okay. So say that the rows here describe the content damage, and the columns here describe the content damage, and the rows here describe the, say, structural damage. And now each point here, or each cell here, describes the content damage, the probability of content damage, and the structural damage, all right? So say, for example, if I'm here, for example, this cell here describes the probability of structural damage at level 1 and the probability of content damage at level 2, all right, whatever. So if you can describe this probability, if you use conditional probabilities, you can describe this probability as content damage conditioned on structural damage times the probability of structural damage. So each one of these cells here can be described with this conditional probability term here. So essentially, for a specific content damage, say content damage, say this one, level 1, the probability, using the total probability, say you have to account for all these probabilities, all right? So essentially, you have to account for content damage given no structural damage, content damage given structural damage at level 1, content damage given structural level 2, and so forth. All the ones, only for, and also the content damage when there is no structural damage. So when you add up these probabilities, you have to come up with 1. So essentially, that's the basic, say, theory behind it. What we know here is the damage probabilities from structures. We know them, but with some certain level of uncertainty, as I'm going to show you. So, though we know them, we used Monte Carlo simulations to account for that modeling uncertainty. What we don't know is these conditional probabilities, content damage probabilities conditioned on structural damage. So again, in our procedure, we used Monte Carlo simulations. We used Monte Carlos just like some sort of expert opinions to come up with these unknown probabilities. But then why do we have to do that? Why did we have to pick such a sort of not very complicated but a tedious way? Because when you consider the literature, the only well-systematic study on content fragilities that are functions of MMI, macroseismic intensity scale, is this rather old document, ATC 13, which is a publication from 1985, all right, and done for California, actually. And for the, so what they did systematically, they went to experts, and then from experts, they got their judgments, and then developed the fragilities in that project. For content fragilities, there are significant restrictions in that report. So I tried highlighting them here on these blue boxes. So the first one is, we really don't care about the structural system for content damage. It says the structure is founded on firm soil, no definition of structure, and such that foundation does not aggravate damage. So this is one of the constraints, limitations. And also it says, that document says, please note that equipment is assumed to be 1, at ground level, and 2, unanchored. So it really puts some constraints for the content fragilities that it is proposing. There are more recent studies, just like Hazes, FEMA, but and there are more complicated, more complete fragilities for content, but they are mostly for single assessed risk assessment. So we couldn't use them for these two projects. And also, I mean, we are in Turkey, buildings are constructed in Turkey, so we have to find something reflecting the construction practice and quality of buildings in Turkey. So those are the major points pushing us to develop our own fragilities, content fragilities that are building sensitive. So before, again, showing you the rest of the study, so these are the definitions, basic definitions of building structural damage and content damage. So DS1, DS2, we have 4 structural damage levels for building, light to very severe. DS4 refers to very severe structural damage. It's almost collapse, actually. And then for content, we have, again, 5 different levels of content damage, starting from slight, which is described by 1, subscript 1, and then very heavy, which is described by subscript 5. Just to give an example, so if it is a very heavy content damage, then it means content damage either demolished or, no, so it should be demolished, essentially, all right? Yeah, there is a typo here. Okay, anyway. So this is the main concept to develop, to generate actually the conditional probability of content given the building damage, all right? So essentially, we have structural damage states from no damage all the way to very severe, and also we have content damage states from slight to very heavy, all right? So say that we have structure with no damage, we assume that the content damage is more likely to be slight, all right? And say, for example, if structure is moderately damaged, then the content damage is more likely to be moderate, but with some considerable possibility to heavy damage and so forth. So there is some sort of transition between structural damage and content damage. And essentially, the next slides, couple of slides, explain the idea here. So say that I have a structural system with no damage, no structural damage, a building with no structural damage. So these are the results of Monte Carlo simulations, essentially, which shows that slight damage having significant probability between, say, 90% to 100%, and then moderate and light damages having probabilities, I mean, say, negligible. It's like 5% to 10%, all right? So essentially, what I say is, most probably, if there is no structural damage, my content is going to experience slight damage with some consideration to others. And this is done like really very simple through Monte Carlo simulations. You can generate many of these probabilities. And then, yeah, this is for, say, moderate structural damage. So you just say, now I have, my structure is experienced moderate structural damage, so more likely I'm going to experience, the content inside is going to experience moderate damage, and then it's going to be followed by heavy damage with some probability, and with some very few, say, probabilities that the structure is going to experience, that the content is going to experience slight or, say, very heavy or light content damage, all right? So I'm not really neglecting the other possibilities, but I'm really giving very small probabilities for their occurrence. So essentially, please note that, so again, another slide here. So say this time the structure is very heavy damaged, so it means it's almost collapsed if not. Then I assume that the content inside the structure is really with very heavy damage, so probably you have to replace them, or with heavy damage, so it means you either have to replace them or make it repair. Please note that this is only for, maybe I forgot to tell you, this is only for building residential content, all right? So it's not for like high technical, because we did different assumptions for high-tech content and so forth. This is only for residential content like furnitures and some simple electrical equipments and so forth. Anyway, so, okay, so I'll start showing you the results of the Monte Carlo simulations. Firstly, I'm going to show you the results of, say, one simple result for building fragility. So each point here is a realization of Monte Carlo. Essentially, you see light damage is described by this cyan color, and then moderate damage is green, and then yellow, severe, and red, very severe. The type of building I'm focusing on is mid-rise, reinforced concrete building constructed after 2000, because we have 15 different types of buildings compiled in the, say, inventory. Low-rise to high-rise, and then with different construction periods and so forth. So, so as I told you, the modeling, so why do we have bands here? Just like, so we have bands. As I indicated, Dr. Özer Ay and Professor Altuğ compiled the fragility functions for different groups, and for each group, the fragilities are not only a single line for a given damage state, but they are bands. So you see, even for some cases, the fragility functions overlap each other, all right? So this is quite common. So this is the modeling uncertainty I'm referring to. So then, to account for that kind of modeling uncertainty, we're running Monte Carlos, which are simple. And then, based on the theory that I explained, for the same type of building, running the whole, say, procedure, we're coming up the content fragilities for 5 different damage states. I apologize for choosing the color. The colors are really, I choose them very badly. So from slight to very heavy damage, all right? From slight, this one is slight, and then this one is really very heavy damage. And essentially, again, from Monte Carlo realizations, each point here is a Monte Carlo realization. So essentially, it says for the residential content, given the building is mid-rise reinforced concrete constructed after 2000, whatever this macroseismic intensity ranging from 5 to 12, I would expect slight damage for sure. And this is the comparison between our findings and ATC 13. We have some sort of agreement for the slight damage. So for slight damage also ATC, the experts would expect slight damage for the entire intensity, ground motion intensity range they consider. Now for the others, of course, there are differences just because of the assumptions we are making and the assumptions made by the experts in ATC 13 project. As you see here, in particular, the probabilities of light damage here and moderate damage is way different than, and also the very heavy damage is way different than the ones given in ATC 13 project. It's because of the building factor we are considering now, all right? It's our buildings, and essentially for macroseismic intensities, very high macroseismic intensities, we say the content inside will be really heavily damaged with some real consideration. All right, so that's what I explained actually. And this is the difference between the effect of different building types here. On the left panel here, what I'm showing is the content fragilities for mid-rise reinforced concrete and constructed after 2000, sort of better quality building because they are constructed after 2000. And this one here is the same type of, say, mid-rise RC building, but constructed before 79. And the major difference here that the probabilities of content damage change significantly. In particular, if you really focus on the very heavy damage, the buildings constructed, the old buildings constructed before 79, the content inside is more likely to be heavily or very heavily damaged. All right. Now, after establishing our, say, building-sensitive content fragilities, we continued with the consequence models. And for consequence models, as I told you, the consequence model is, by the way, it is the replacement cost as a fraction of content value. We used the expert judgments, and then we simply came up with some bands for each level of content damage, all right? From very light content damage to very severe, very heavy content damage. Of course, when the content damage is very heavy or very severe, the replacement cost ratio is really standing to 100%, so full replacement. And then again, with Monte Carlo simulations, we simulated each band for different content damage states. So this is one simple example again, here what I'm showing. So we did thousands of realizations to account for this uncertainty that mainly is due to different expert opinions. And then essentially we came up our loss model. Now, this is just for showing you for the basic example. So this is, again, content is residential content, like furniture, simple electrical equipment. For mid-rise reinforced concrete building constructed after 2000, so rather new buildings. So the gray scale, the gray cloud here is actually, again, the resulting Monte Carlo realizations, all right? Monte Carlo realizations. So there is 10 million there are 10 million Monte Carlo realizations for this. And the blue points here is actually showing the uncertainty associated with let me just explain the red one. The red one is the mean loss curve. And the blue curve is actually the uncertainty associated with about the, say, mean, all right? So in a way, this is something really like a backbone model that the seismic hazard people have been using for a while in their models. In a way, I'm showing you the same thing through Monte Carlo simulations. If you just really neglect all the, say, aleatory variability, the unknowns that you cannot control, if you just think that this is really the uncertainty coming from different modeling assumptions and so forth. So essentially, this is sort of the, say, band about median, and then this could be like the central trend, and so the range and the center. I mean, you can just think it in that way. And then, of course, since we had to run this for many building types and for many different scenarios, we just simplified and we only considered the mean, and then we came up with the average annual loss ratios for different, say, content types, sitting on different building types and so forth. This is only a single, say, sample map, which I prepared by myself. Okay, so as for the conclusions, I think I'm just on time. So essentially, now with these high-tech computers and so forth, and with the knowledge that you have in modeling, you can really start developing very complicated and sophisticated risk models. And then, based on the problem that you are focusing, you are considering, you can do from that complexity, you can start making your simplifications after obtaining the whole picture, and then run your, say, loss assessment, whatever, depending on the problem you are involved in. The only thing that you have to really focus on is that the database you have in terms of, say, buildings, in this case, or fragilities, they should be very well compiled so that you can really make justifiable assumptions in your model. Thank you very much. Any questions? No, thank you very much, because we have to move to Paolo. We can discuss, if you're interested in the talk, later in the lunch break. Please, Paolo.
Thank you, Sinan. Good afternoon. This is the last talk, which has an advantage that I don't have to say a lot of things that have been already said by my colleagues before me, so I think I'll try to concentrate on things that have not been said. I will present some work done by myself and by several of my former and current students, and also in collaboration with the dear colleague Dimitrios Vampatsikos from Athens. I will talk about pricing, but mostly on catastrophe risk modeling results and how they can affect pricing. The objective here is not to undermine your dear friends, the catastrophe risk models that you have been dealing with for the last 25 years, but maybe to make you think more critically about the loss estimates that come out from them. So these, the exceedance probability curves, probably a misnomer, but that's the condensation of the results of any catastrophe risk models. Will give you the usually annual probability or rate of exceedance of losses for portfolio of buildings. Can be cast into return periods, and that's it shouldn't be used, but that's anyway it is used usually. From these exceedance probability curves, which by the way, the loss could be by event or by year. In that case is aggregate loss exceedance probability curves, but that's the standard results. When you from these exceedance probability curves, you can compute the average annual loss. The average annual loss is simply the loss per year over many realization of next year seismicity, not over a long period of time, because we do not assume that the seismicity is necessarily stationary. So the average annual loss is what underpins the pricing of insurance. So the typical users of these models, besides insurance companies, are very many. There are, you can read them over here, rating agencies, governments, corporations, you name it. We concentrate on insurance in this talk. Many are the activities that are underpinned by the catastrophe risk models. We'll concentrate on pricing today. But of course, there are many different others. The CFO of a company may actually be interested in understanding what is the annual probability that a very large loss that can jeopardize the integrity of the company has, and maybe take measure against it. The buying reinsurance is done using these models. Pricing, as we said, underwriting, you can actually get some results from the model and maybe decide whether you want or not to take that risk, underwrite that risk. You can run the model in the aftermath of an event to estimate how many claims you're going to receive, for example. And you can also look at the portfolio optimization, see whether the portfolio you're going to get is going to diversify your risk or not, the volatility of your losses, et cetera, et cetera. But we'll concentrate on pricing here. So pricing is only one element of the underwriting process. There are others that are equally and sometimes more important. Client selection, whether you want to keep that client, is that a good client you want to keep or not, as a factor into the underwriting process. Whether the wording of the policy condition is acceptable. So whether, for example, maybe in the wording there are included many sub-perils that your model maybe does not consider, whether that's acceptable to you or not. Whether that fits in your overall portfolio, whether you have the diversification risk or not. So all those things are elements that you consider during the underwriting process, and then finally the price. And the CAT models will provide what's called the pure premium, which is part of the final price of insurance. So the pricing, the objective is very clear. You want to determine how much you need to charge to cover the cost of a certain product and make a sufficient profit. That's as simple as that. Simplistically, there are different components to the pricing. The expected loss, the average annual loss from the CAT models is certainly the background of all it. But then there are loadings on top of it. Expense loading, how much you put all the costs, the operational costs, fees, taxes, cost of reinsurance, retrocession, cost of capital, et cetera, they're all in there. A profit loading, as I said. But also, and that's where I also want to concentrate the rest of the talk, is what I call here risk loading. So you need to account for maybe a model perils. Let's say your ground motion, your earthquake model includes only ground motion and not maybe landslide losses, maybe not soil failure or things like that. But mostly on unknowns, things that are not in the model and maybe they should be, or maybe the model the model treats them in a simplistic way. And by the way, that's the technical price, which is not necessarily the market price at the end, because there might be some decision to price to that particular client higher or lower than the technical price. But that's not what I'm going to focus on. So you have seen here, those are the modules of any catastrophe risk models. The first part of my talk will be dealing with the vulnerability. Let's see. In all the catastrophe risk models, the vulnerability functions you have seen, fragility plus consequence functions equal to vulnerability functions. They are developed usually in 3 different ways. Expert opinion from a local expert, your favorite local expert. That was state of the art of 1985, more or less. Local experts, of course, are still used, but they are not dictating exactly the final results. The workhorse, believe it or not, of the vulnerability function or the vulnerability curves development, it's still analytical. Because the preferred method, so the empirical data, is often not available, or whether it is available, it's not cleaned. So empirical data is often used just for calibrating the results from analytical studies. But the analytical studies are the workhorse of any vulnerability model for any class of buildings in the models that you're using. When I said that the empirical models are hardly ever used, they are used indeed, but there are not very many cases. This is from Northridge, where we had a wood frame building claims, 34,000. It's as clean as it gets. Okay, and that was not clean. I can talk for half an hour about all the noise that there is in this data, but it hardly gets better than this, okay? So that's why we would like to use empirical data, but often we can't. So given that we use analytical models, and given the analytical models analysis done by our core engineers who hardly talks to seismologists and to engineering seismologists, so if you talk to an engineer and you tell them, look, I have a building, which is your typical building of a certain class, and the vulnerability is the same regardless of where it is, okay? That's what 9 engineers out of 10 will tell you exactly that. Well, that's not really true. It's not true, and we'll show you why. I think Peter this morning said or alluded to that. Our fragility functions and vulnerability functions are hinging on one intensity measure. We throw out a window everything else. That everything else that we throw away is actually important. And it is very important if the intensity measure that we pick is a dumb intensity measure, like it is usually done in this catastrophe risk model, where we pick spectral acceleration at the first fundamental period of the building. That's not a good intensity measure to pick, but it is ubiquitously used everywhere. So if you pick the same building, and everything else we throw away, it depends on the hazard at the site, because the type of earthquakes that affect Istanbul are not the same type of earthquakes in terms of magnitude and location that affect Ankara or Erzincan. So we picked the same 7-story reinforced concrete buildings, and we put it in 3 different places. We used the spectral acceleration at the first fundamental period of the building, 1.6 seconds. These are the hazard curves. And then we computed the fragility curves by doing what Peter discussed this morning. We picked hazard-consistent records for Istanbul, for Ankara, and for Erzincan. So I'm not explaining exactly how we use conditional spectrum, mean multiple stripe analysis. I'm not going into the details, but for what matters here, they are consistent with the hazard. And then we did also what is usually done in the industry. We picked a set of records, maybe those given by FEMA P695, set of records that have been scaled to different levels to estimate the response of the buildings. And then we did also something else that we'll explain in a second. These are the fragility curves. So the fragility curves, as you can see, they are very different. The green one in the middle is what we can call the benchmark. In this case, we had only 3 sites, so we could actually compute the benchmark by a weighted average of the three fragility curves for the 3 sites. But you can see that the same building has very different fragility curves for collapse if it is in Istanbul, in Ankara, or in Erzincan. Oops, sorry. This was unintended. Okay. So the FEMA P695 set of records will give you a fragility curves, which may or may not be relevant to the site that you are using, where that building actually is. So if you are lucky, it is. If you are not lucky, it is not, and you have no idea unless you select the records right, which is, again, hardly ever done. In practice, there is another line close to the benchmark, which is a dotted line, which is an approximation on how you can actually select records in such a way to be somewhat consistent with the hazard on multiple sites at the same time. I don't have the time to discuss the details, but that's possible. Another way of doing the same thing, probably in a smarter way, is to pick a different intensity measure, and that's also what the SERA project is doing. Instead of picking a dumb intensity measure, like a spectral acceleration at T1, maybe you can pick an average SA, which is essentially the average of the spectrum in a range. In this case, we use 20% of T1 to about 2 T1, which is between 0.3 seconds and about 3 seconds. In that case, because the intensity measure is a good one, what you do not consider is not that important. In fact, if you look at all the fragility curves now, they are bundled up very close to the benchmark. So another way, you have to be smart somewhere. Either you are smart in the way you pick the records, if you are not smart in the way you pick your intensity measure, or if you are smart in the way you pick your intensity measure, you can actually be dumb in the way you pick the records. You can pick the FEMA P695 set and be not that far from where you should be. And the hazard for average SA is a piece of cake. You don't need new GMPs, you just need those that are already in existence. So that's one source of possible bias that you should consider, and that's solvable and addressable today. Another one deals with the ground motion intensity calculation, similar to what Peter showed this morning. So here I'm going to go very quickly because you have heard half an hour presentation on ergodic GMPs. What we did here, we developed an ergodic a partially non-ergodic GMPE for 3 sites, and I'll show you what the results are. But conceptually, if for a given scenario, an ergodic, the traditional GMPs where you have essentially a site generic response, it's the black curve, it has a large uncertainty. Instead, your site can respond, certainly as a lot of that uncertainty is systematic, explainable, is not a random variability, randomness. So your site can respond exactly the same on average, and you have the red, more peaky distribution, or it can respond lower than the average or higher than the average. In that case, you have the green or the purple curve. But you don't know, unless you do the analysis, where your site is going to be. And your site could be in a place where you have a lot of concentrated buildings, and therefore you can be systematically wrong. So if you do the hazard for the ergodic case is the black solid one. You have these hazard curves which slope fairly mildly. When you change the median and the uncertainty, then you get the other curves, which again, they are very, very different. So if the hazard is very different, also your risk is going to be very different. How different? We picked 3 sites in Turkey, site 1, 2, and 3. The stars are the sites, the little dots or triangles are all the earthquakes for which we have recordings at those sites. So we have multiple recordings at those sites. We don't have a huge amount of recordings, for certain more than 10. So we were able to develop, at least with some confidence, the site response of those 3 sites. For site 3, for example, you see it on the right, the ergodic GMPs will give you the smooth dotted spectra for those 3 scenarios. The non-ergodic one are the solid ones. So clearly the site 1, the non-ergodic site response is much higher than the ergodic one. And for site 2, I'm not going to show it here, they are more or less the same. Site 1 is the other way around. So site 1, the non-ergodic is actually lower than the ergodic traditional way. So these are the hazard curves performed for the ergodic and using ergodic and non-ergodic GMPs for 3 different spectral accelerations, because we put at each one of those 3 sites 3 buildings with a 0.2 seconds, 0.5 seconds, and 1.0 seconds T1. And so from just looking at this, the difference in this hazard, you can understand that the risk is going to be very different. So for these 3 buildings, here we present the response hazard curves. There are no losses here, it's just the response. So you have ductility on the x-axis and mean annual rate of exceedance on the y-axis. And you see that, for example, if you concentrate on site 3, the one that I showed before, clearly the ergodic results are the dotted lines, and the solid are the non-ergodic, more modern, if you want, results. You see that clearly in that particular case, you would severely underestimate the loss of this particular building. And again, this is a building in a portfolio, but all this can be translated into a portfolio analysis. And if you pick a site 1 where you have the other way around, the ergodic version of your loss estimates for this building will be much higher than the non-ergodic one. And similar, instead of for site 2, things are similar, but also this trend varies from different periods. Structure is not the same. You cannot say that a non-ergodic study will give you a higher or lower estimate of the losses for all buildings at the same site. So it is more interesting than that. So that's coming. We don't have many sites in the world where we have enough recordings to compute a non-ergodic GMPs, but we're getting there. So that's what's coming. The third one is again related to ground motion intensity calculation. Again, Peter this morning mentioned ground motion simulation. It's not completely ready for prime time, but we are getting there. There are many groups of researchers all over the world. They use different methodologies to simulate ground motion. Here there was a video which I cannot show because somewhat it doesn't work, but where you see the wave propagating from the Loma Prieta earthquake. So these models will model the rupture and characteristics of the rupture, and they will model fields of ground motion. So at each site you will have 3-component accelerogram. Why do we need those? We need those because all the GMPs in the world are very poorly constrained at the very low distances because we have few recordings. And also we have a fewer recordings for very large magnitude earthquakes. So the part on top, the shaded part on top, is where we need mostly the contribution of these simulations. Again, once they have been vetted and have been considered ready for being put into use for practical application. But again, we are getting there. So researchers have been working on this for years. A lot of statistical analysis have been done. They are way much better now than they were 10 years ago. So we're getting there, and we're going to get there fast. So we did use the simulated ground motion from the people in Polytechnic of Milan, Paolucci and his group. They use a software called SPEED, and we modeled the 7.2 earthquake on the North Anatolian Fault in front of Istanbul, and we were looking at to do a traditional risk analysis for tall buildings in Istanbul, using ground motion simulated and also using ground motion from the traditional way, so recorded ground motion. I'm only showing here the results for one building. We put to one building, which is the one you see over there, 23-story reinforced concrete building with core shear wall. At those three locations that you see over there, we considered only that particular scenario, the 7.2 scenarios. And the ground motions from speed, so the simulated ground motion, you see them over there, those bundle up kind of wiggly curves. And the red lines are the GMPs. So that's what the GMP will tell you, will predict for that particular scenarios at those three different sites. So you see that the ground motion, simulated ground motions tend to be a little higher, more aggressive than what than the average, than the GMPs predicts for you. So we subjected the buildings to the three sets of ground motions at the top, the simulated ground motion. We have 15 of them, and also we selected 15 real ground motion, and we scaled them up to fit the mean and the uncertainty of these scenarios, as we would do usually in a traditional way. And those are the records at the bottom. And we looked at the risk. So, of course, it's no surprise that the risk in this particular case, where the ground motion simulators are more aggressive, is significantly larger than the one that we would predict in a traditional way. So, is this a source of bias in your model? We don't, for sure, we don't know in general, but clearly the ground motion simulation are telling us certain things, most of all closer to the site, that for which we have no recordings. And so the ground motion prediction equations are usually very, very poorly constrained there. So that's certainly something to keep in mind. We don't have a solution yet for this, but this is coming in your models. The last thing I wanted to say, for which I think we need to pay attention to, is related to earthquake occurrence. So it's the other blob into the hazard module. So it is how many earthquakes we put in our loss estimation model. So this slide presents the SCEC catalog in Southern California from 78 years above magnitude 3.8. You have about 3,000 something events there. And what you see on the right is the decluster catalog. It's the catalog when you remove everything else and you leave the main shock. So from 43 events per year, on average, you get about 11. So you threw away two-thirds, actually 75% of the earthquakes, okay? Well, you say 3.8, so we threw away all the small ones, who cares for loss estimation. Is that really true? I mean, why? First of all, why we are doing the clustering? We are doing the clustering because we inherited that from the early application where we were doing these things to support building codes. So for building codes, it made sense to design for the main shock. Main shock, usually, not always, provides a largest ground motion in a sequence. So if I design a building to be able to still be up and not severely damaged for the main shock, then I'll evacuate the building, and if the aftershocks, et cetera, kill the building, who cares? Nobody's in there, okay? But for loss estimation, I claim that we actually do care, and we should. So what happens? See these two sequences? That's the Emilia earthquake sequence on the left-hand side, and the one in central Italy on the right-hand side, 2012, 2016. So you have in the first one, 2 magnitude 5.9, 9 days distance, and you have 7 magnitude 5+ earthquakes in that sequence. On the right-hand side, you have a more complicated sequence that lasted for many, many months, where you have 1 6.5, but you have 9 events above magnitude 5. So out of all these two sequences, when you do your declustering, for which that you are actually using to compute the rate of future events, which are those that are going to go in your stochastic catalog and those that are going to in your loss event tables, you remove all the events, you can just keep one, okay? Do you feel comfortable with that? I don't, and I will show you why I don't. So there are several things that happens. Damage accumulation is one of them. A lot of research needs to be done to model it properly, but at least we know something about it. Something can be done on this as well. So first of all, you remove a lot of earthquakes. Then you do not account for damage accumulation, and the damage accumulation is important. See, for example, in the Central Italy sequence, you have the damage state from 0, no damage, to 5, collapse. On the right-hand side, the blue bars are after the first event. The red bars are after the entire sequence. Clearly, they are different. So the damage accumulation matters, most of all in the epicentral area. But another thing which we don't consider usually is the fact that when we keep only one ground motion, and if you talk to modelers, they will tell you the mantra is always the same. Oh, well, the sequence is implicitly accounted for because when we calibrate our model, we have the losses for the entire sequence, not just for the main shock. That's what they will tell you. Well, that's not a good answer. And if you squint your eyes, you understand why it's not. This is the shake map of the first event, the one that happened on the 20th of May. The one that you throw away is this one here. So a much larger area. So there are many buildings that didn't feel anything from the first event that were severely damaged by the second one. So if you try to fit or calibrate your damage function for the loss of the entire sequence, that means that you'll calibrate your damage functions too high because you'll never able to get the loss from all the sequence of events by just simulating one event. So that's a bad answer. So your models certainly have a problem there. But this model the models that we use now can be corrected. So there is no reason why we should not be able, in fact, we are able to simulate many realization of next year's seismicity, but all the earthquakes, not just the main shocks, okay? That can be done. We did it using the ETAS model, the epidemic, AT stands for type, academic type, sequence, aftershock, yeah, aftershock sequence. So we used that for, and we picked the Central Italy region. We borrowed the exposure model from this region, from RED, a commercial company, and we simulated many realization of next year's seismicity using simulating all the events, not just the main shock. And also we did it traditionally, just the main shock. And the results are this. So we did it in two cases. On the left side, you see there are many dotted lines and colored lines. Consider just one. Those are variations of whether we include the accumulation of damage or not, whether some parameters of the ETAS model. Those are not important. I don't have time to explain the differences here. But on the left-hand side, what we fed into the model before generating many realization of next year's seismicity was just after the main events of the sequence. So it was a higher than normal seismicity, and therefore that is reflected in a very large difference between the Poissonian model and the exceedance probability curves for all the models, models that include all the events. So that is certainly non-negligible difference. But even in a random year, so a year that has an average seismicity, you see that the difference is non-negligible. So there is really no reason, besides laziness, not to include all the events in the models. If you care about the average annual loss, because we started by looking at pricing, there you have it. On the left-hand side, you see the Poissonian average annual loss is for all the buildings in Umbria is the straight line. And you see all the variation of the models that include all the sequences have average annual loss that are 3, 4, 5 times larger just after the event, and at least 50%, if not more, 80% larger, even in a normal year. So that's certainly a source of concern and a bias in your model. You cannot extrapolate all these results for anywhere in the world. There are places where sequences are more active and more rich than others, but certainly this is a problem in general of all the earthquake models. So in general, we've been using catastrophe risk model for 25 years. They're certainly helping in many decisions, corroborating our decision, giving some quantitative answers for pricing and many other activities in the insurance industry. But we should be certainly aware that there are simplifications in there. One simplification, as I said, was in the development of vulnerability function, because has been traditionally, the people who develop vulnerabilities don't know much about seismology, and therefore what you get is a vulnerability curve that may or may not be okay for where the exposure, the largest exposure of your portfolio really is. And there are ways of overcoming this problem, and I didn't have the time to discuss them here, but they are published. And also, there are issues in the hazard, both in the ground motion prediction equation. I said what's coming is the non-ergodic GMPs and also the simulations, but also on the occurrence of earthquakes. There is really no reason to keep the main shocks. That was a tenable assumption for design. It's not a tenable assumption for loss estimation. Thank you very much.
Thank you. Thank you, Paolo, for being on time. Any questions for Paolo before closing this session?
Must have been really confusing, if I don't know, questions, or very clear, one of the two.
It's also the session is quite long, actually, 3+ hours, something.
Yeah, coffee in the middle, they're waking up the audience.
Okay, thank you very much once again. So this last talk closes the session of the morning session. We heard really nice and impressive talks. Actually, really, the talks resemble the name of the workshop, Advances in Assessment and Modeling of Earthquake Loss. All of them are really cutting edge. Thank you very much for speakers and for all of you. Thank you.
Viewers, the lunch will be Good afternoon. I hope everybody enjoyed the lunch. And we will continue with the new session. I will introduce our speakers one by one. The list has changed a little bit. Mr. Güngör, Mr. İsmet Güngör will join us firstly, and the stage is yours.
Let me put the time, otherwise I talk a lot. Now I understand why Mr. Fuat Bendemurat offered me to change the places. It's difficult after the lunch. Actually, no, thank you for changing. I have a flight to catch, and therefore also I would like to thank all of you again. Really, we are honored to see all those presentation, great works, and we benefited a lot. Thanks a lot. Let me. Actually, when I planned the presentation, I was just thinking to explain how the technical pricing converts into the commercial pricing. But since we have such a esteemed group, we said let's talk about a little bit more about what TCIP does, what projects are going within the TCIP. So a little bit we extend the presentation. Very roughly, this is the TCIP. What are some critical points for the TCIP? One is the operational ratio. It's less than, the cost is less than 2%. And when you think insurance companies are around, the best is 10% and upward. So this ratio actually gives us to accumulate the funds faster. And of course, you see the penetration and other funds and claim payment capability. But what is the one of the unique structure of the TCIP? Turkish Treasury didn't put any single dollar into this fund. Now over 1.5 billion in cash and huge claim reserve within the company. Some money was borrowed from the World Bank, and it was all paid by the payback by the pool itself. So it's a quite reputable model worldwide, I would say. And we have two missions actually, and in most of the conferences we are talking about the left-hand side, about the penetration. Penetration in the net cat is a headache, not only for developing countries or not only for Turkey, but in general, net cat is a penetration is a big problem. So in many conferences we are talking how to increase the penetration rate, and the things that keeps us awake during the night is the cat management, risk management. What if the big one happens in Marmara region? How we are going to manage the operation? That is a really big, huge challenge for us. And there is a vicious circle in the cat management. You know, you need to invest into the business, into technology, etc. And therefore you need to spend money. Then you need to increase the penetration, but you are not able to increase the penetration. However, you have to pay the claim. You need the money for the claim. In order to have the operational excellence, more people, you need to excel in the claim. So on those three pillars, you must excel on three of them. If you are lagging behind in any of them, either on operational excellence, or in the claim, or on the penetration side, the scheme, the system is not working and collapsing. So this is the critical point for us. Cat management, in general, few sentences. Generally, again, the companies, when talking about the cat plans or emergency action plans, sustainability plans, etc., they're looking for the left pillar. However, there is an illusion there. There is a virtual capacity they are all talking about. So when we are talking about the call center capacity, when we are talking about the mobile banking, we say we are going to have the satellite, blah, blah, we are going to have few hundred people outsourced, etc., but all institutions and the capacity, companies actually, they are using the all same resources. So in NetCat, the critical issue before the plan is about do you have enough resources, and do you have enough enough infrastructure to make these resources working on your infrastructure. Those are the critical. Then when you have the resources, when you have the structure, then it's about to have how those all making sense and how they all work together. Yesterday we talked about the complexity. Marco was telling, I guess, I remember. It is mess. It is mess. And let me tell you what in numbers means. See, we are talking about 4 million phone calls for TCIP if there is such an earthquake in Istanbul. Daily we are getting only 2,000 phone calls. And all of a sudden, I'm gonna be facing 4 million phone calls. Adjuster, 3,000. Whole Turkey have only 500 claim adjusters. And what we say is actually, for Turkish industry, these 500 adjusters, just leave it alone the pool. Is it gonna be enough? It's another case, but obviously there is no enough capacity. Claim files, 2.7 million we are gonna have, we estimate. And currently in Turkish market around that we are handling around all companies, all big teams, we are handling around 200,000 claim, 300,000 claim files. Call center agents, 500. How many I have? Only 15 today. Then payments, 2.2 million people needs to receive the payment. How we are gonna do it? This is the puzzle. So when we are talking about the models, in order to manage such a complexity, from insurance and reinsurance perspective, we are saying that with traditional methodologies, with traditional applications, we are not able to run such a complexity. For example, claim adjustments. Since yesterday we've been talking. In insurance, adjusting assessment, then adjusting is so subjective. Okay, auto, leave it alone again, but property, marine, we are falling into the property line. It's so subjective. It depends the experience of that individual claim adjusters. So, and in city of Van, when there was an earthquake in the city of Van, it's so subjective that we had the very senior civil engineers, the claim adjusters, very senior, the most senior guys, and Professor Ilki, we were on the table as well with all adjusters. The adjuster, we were not able to assess, to agree on the loss, whether it's a $2,000 loss, not 2,000, even $1,000 loss, or is it a total loss? Correct? It's difficult. So what we've been telling with the team, with the Professor Ilki's and team, unless we have standardized procedures, methodologies, people will lean to work on their perception or on their experience, but it's not such a field. So that's why we've been working on the methodologies. Still not good enough. Still not good enough. We've been, yes, since especially yesterday, we've been looking at lots of how can I say, models, categorization, damage ratios, etc., etc. Still, when we have to be able to take them down to the field effectively. So that means we need technology. We design the models, we test the models. Models are there, but we have to take them to the technology. The trick is, it's about simplicity. It's about simplicity and experience. So in order to make your projects, methodologies, etc., available to many, the simplification is critical, and to make it onto the technology. So for all supply chain in our claim management, before and after earthquake. We studied in detail, and for each spot, we look at do we have enough resources? Do we have enough infrastructure for that? And we start building up the project. Where we are, claim management's IT structure is there. NetCat management system is there. Mobile is there. First time in this earthquake, we were able to run it fully. And call center is there, and contingency adjusters are there. Now we are working on the all designing how this machine is gonna function. So we said we've been talking about today modeling. Now I'm gonna look at a little bit from different perspective about the modeling. Now first I'm gonna talking about the call center modeling. See, I said 4 million calls I'm gonna have. Yesterday we are talking about the adjuster, you know how we are gonna have it. But before the adjusters, we are not gonna able to get the claims notification. We don't have such a capacity. So when what we did, we started studying the journey. What happens, what's happening, why people are calling us before, after earthquake, what they do, what they need, what they ask, what they wait, what they expect. So all this journey have been studied. What we did actually, how we can meet them, on what basis. Are we gonna put thousands of live call center agents, or how we are gonna take into the digital, how to IVR, how to email, web, email, SMSs, etc. We've been studying that, and also very interestingly, when you look at the psychology, how behave the people after the earthquake, is interesting. You know, there is a belief immediately after the earthquake, insurers should be there with the clients. As a TCIP say, we know, we shouldn't be there. Because there is a mess going on. It's a survival mode, and any additional people who is not in that survival operation, they shouldn't be on the field. However, it doesn't mean we shouldn't do anything. We should immediately start on planning and coordination. So, and also how we see, first week, now yesterday we were talking 10,000 claim files, etc. Within the first week, actually, we don't get very much calls. People are somewhere else, especially the bigger the earthquake, the later they start to make the claim notifications. So after the second week, they start claiming the files. And also, we see the Mondays, whether it's a after holiday or ordinary Monday, or if it's within the earthquake period, Mondays are always busy. So even within the days, there are some cases. So here is the phone. Here is the number of calls we know. We are going to get around 4 million, and we estimate those calls, from where to receive them, and the content of the calls we roughly know. And here is the result. Of these 4 million phone calls, if we consume 70% of them on digital channels, meaning 70% of the calls, no energy agent, no any human being is gonna touch. All of them are gonna be run digitally, meaning IVR, web, SMS, or the others. Just for remaining 30%, we need 500 claim agents. 500. Is it easy? Now, actually, the problem starts here. How am I going to find 500 claim adjusters? It's easy, actually. Call center companies in Turkey, they are very good. There are huge of them. But the problem, we don't know when the earthquake is going to happen. Next year, 10 years, 20 years, 30 years. So we are not able to keep 500 agencies, for 500 agents for a time period that we don't know. So with this scheme, we start working with the call center agencies that they are gonna build up a contingency capacity for the TCIP. Actually, what is the formula? What is the formula? We said them, okay, give us your client list. There are some companies, they are not gonna need call center activities after the earthquake. So what we design actually, what we agreed with those kind, to use that capacity that they are not gonna need after the earthquake, and to allocate them for TCIP. And with basis on this, now we have 3 call centers. One is that we are currently using, and three other are the emergency call centers. And we were able to test them in the first time in this earthquake that happened in 26. See, this is the call center modeling. I explained it very briefly, but this project, it was around 6 months that it took our time. Now, let me see, another challenge, another modeling about claim adjusters. How many claim adjusters I'm gonna need? But it starts with your objective. If you make your system adjustment very complex, and if your ambition is very high to finish it very early, or your ambition is low to finish it in 6 or 9 months, it's very critical. But in our methodology, we say if we are able to finish it in like 40 days, something, how many claim adjusters we are gonna need, relatively simple structure, this is the result. And you know, assumption should be based on the reality. Adjusting process. Adjusting process traditionally is, the event is somewhere else, adjusting process is somewhere else. But in the earthquake, you live within the earthquake area. You are adjusting people, but you don't have the water. Housing is a problem. Your wife, your kids at home, every night they are calling you why you are not coming, why you are not coming. How many days you can spend there? So those are the limitations for this one. And also coming to the modeling, simple modeling. So if it's a rural area, if the houses are quite different than each other, you need different loading. However, if you have a 200 apartments in 2 blocks, it's a different scheme, different models you need to put. So based on all those studies, now we say around we are gonna need 3,000 claim adjusters, and for each village, neighborhood, and for each street, more or less we model the adjusting capacity. Actually, for the future, our aim is not to appoint any claim adjusters to the buildings or to the laws, to make adjuster know before the event which buildings or which streets they are gonna go. So this is our dilemma. This is our project. And loss notification. Insurance is based very much on loss notification. Everything starts with the loss notification. However, what we see, if there is a big earthquake, we assume for Istanbul, if it's above 7, we are not gonna take any loss notification. Because we assume, we are modeling that at least one notification, loss notification, I'm gonna have from each building. That means I have to go and inspect and look at adjust, do some work in each and every building. So why should I suffer? instead of taking all this hassle or to make it, just make the announcement. Just make the announcement, wait, we are gonna come, we are gonna do it. So again, multi-level operation. Yesterday we were talking heavy damage, experienced civil engineers, slight damage, some other people, maybe someone from the neighborhood. But this is also for the big and small earthquake. For big one, we don't need the loss notification. So this is the adjusting part. And for the claim adjusters, actually, yesterday with Japanese colleague, we talked as well. The cooperation, synergy between the institutions about the adjusting is so critical. One institution goes and he says this is a total loss, and he's looking from the sustainability or the sustainability of the building for the future earthquake. But insurance are looking just from the earthquake damage perspective. So this clear understanding within the society is very critical. So with the Ministry of Environment and Urbanization, we have the agreement and to use this contingency capacity, but still not enough. Still not enough. Claim adjustment is a very difficult one. In the past, it used to take 5 days of 1 week of workshop to teach people how to do it. But instead of our new philosophy is, we don't want to teach some civil engineers about the claim adjusting. Instead, based on the Professor Rilke's methodologies, and taking them to the digital, we are going to teach them how to use the tool. So I don't have to go into the insurance law, under insurance, blah, blah, blah, all the stuff. It takes me many years to understand as well. So instead we are going to use them, we are going to teach them only a few hours how to use the tools. This is our adjusting management philosophy, I'll say. Workload. See, this is our heat map, how our portfolio, TCIP's current portfolio accumulates. And this is roughly where the losses are going to come in monetary terms. This map is my workload mapping. See, there are some in Kadıköy region. There are many buildings. Either there are going to be total losses, which are very easy for us, or many small, very slight damages, etc. So all of three of them tells me something. Portfolio management is critical. Our claim capability, claim payment capacity, reinsurance capacity, and the third one is about our workload operational management. So those are another perspective of the modeling in the net cat management from the operational perspective. Professor Rakkar, he was telling about our new pricing model, technicalities. Actually, first study was in 2017. 2016 we started, and since then him and his team been working. But okay, and we have the new hazard map as well. The government has published the central map, and now our new tariff is going to be live on 1st of January. Those are other issues, but from the structural point of view, existing tariff has some difficulties. It's not been working. You know, there are 15 cells, in the structure, but 90% of them is within the only 2 cells. And if you look at the big cities, etc., the tariff is only, of course, it's a hazard map. It's supposed to be that way as well. But when you talk to the commercial arena, is not actually responding. But there are another perspective as well. Now, our existing tariff is a hazard base, and we want to go to the risk base. Okay. Here is I don't want to go into detail, and to make our presentation to look a little bit scientific, I took some some graphs from Mr. Akar's presentation, but those are grids. And AFAD, the new hazard map is the grid basis. There are over 30,000 of them. Now we can build a tariff based on 30,000 grids, and even we can divide them into reinforced concrete, the height of the building, etc., etc. We can have so many, very much detail, truly risk-based tariff. But the question really, the question is really, do we need it? So at the end of the day, Professor Akkar and his team, they provided such a structure. They studied all those, in details they've been telling. So this is the matrix. Now, it's a commercial thing. Do we need to have really new tariff? If we say we are the monopoly, and if we say the financial literacy is low, insurance awareness is low, so I want to have the simple, very simple, pure structure. I may say everywhere, every building is 100 lira. Can I do it? Why not? And another spectrum is to do the pricing for each and every grid. So what is the balance? So then now we are talking about more of a marketing, more about the opinion of psychology of the society. But before then, look, this is the structure. Actually, what this table says, there are somewhere prevailing accumulation, and the lower the building, the cheaper the rate. Higher and older the building is higher the rate. And the conversion, the transition between them is quite, how can I say, very structured. And masonry, I have only few % of the masonry in our portfolio. Really, do we need such a big matrix? It's all commercial decision. So what we aim, it should be simple. The tariff should be talking to the people, should be talking to society. So instead of just providing the matrix, we want to talk with the people to increase their risk awareness. Why risk awareness we want to increase? When we do the psychological analysis, and for every other year we do the opinion surveys, and when we study them, in the past they were complaining our price was expensive. We never increased the price anyway. But they perceive it was expensive. However, when now the latest opinion survey says the value that we provide and the price we ask is not equal. People perceive value is higher than what we ask for it. Okay, the game is now is changing. There is a room for us to move the structure to the risk base. Okay, risk awareness. Risk awareness also says it's not about your models, what your model says. It's about how people perceive. There was the survey, the one before we made, and most of the people in Istanbul thought they are on rock. Their building is on rock. And we did the analysis. We did the analysis. Where is it coming from? And they said most of them, majority, heard from the doorman. Doorman was telling them it was on the rock. So the perception, they are in Istanbul, maybe Zeytinburnu or somewhere, you know, somewhere, but people don't feel that they are under risk. Perception matters. So how we are going to change? We are going to be talking about the risk. So that's why the perception, how we want to do it, we have to change this perception. So we want to talk more about the risk. See, we did the deep analysis with the team. There are anomalies, etc., etc. We look at instead of a normal distribution, we look at the portfolio in deep analysis, all those Excel sheets, you know, and we try to analyze the different path in the result. And also today, colleague has also explained from technical to commercial rating, loading, margins, etc. See, the cost for one single policy, especially printed one, is 3 lira. So 3 lira for the least risk area is like 7-8%, but for the riskier area is around 1-2%. But the acquisition cost is different matter. Of course, those are the only metrics, but there are for each row there are so many items as well. So this is actually the loading part. So at the end, for the concrete, this is our tariff. Actually, the tariff says, okay, tell me what neighborhood you are in, okay? And now afterwards, they start talking. Guy, if you have the apartment, if you are living in the apartment with less than 3 floors, you get discount. If you live in the older apartment, and this is the reality as well, you need to have surcharge and taller as well. So we want to distribute into the community the understanding of risk. But I have a commercial interest in that perception, because when they think that they are under the risk, they start buying the insurance. They start buying the earthquake insurance. So this is the final tariff. But at the end, we show you the whole table of structure. When you use all these simple parametrics, and if you put them onto the table, more or less you are there. So another critical things here is how we structure the columns. In the past we had the 5 zones. Now we have the groups actually. Even with the industry we debated. We discussed how to call it. To call it risk groups, hazard and risk groups, or what? At the end, we said just let's say only group 1. And look at in the past, the left is the only 90% is there, and look at the transition between zone and 1. It's so hard, 70%. So where our average premium is 200 lira, the difference is 70%, which makes 140, 150 lira. But where the premium is low, only around 50 lira, the average is 15 lira. So there is a big confusion in the market. And in the past, this tariff was for the commercial as well, for the property, other property as well. So if your factory was on zone 2 or 1 or 3, for the business owners, it made lots of sense, and they were always fighting. You know, there was always fighting what's going on. So with the tariff, see, the transitions are much smoother, and we expanded the tariff to have this transition the smoother. What is the result? This is the result. Okay, this is the previous map, hazard map, the new one. So this is just one example to the left, but on the right hand you see the risk-based, the distribution of the portfolio. But within the color, it seems a little bit mentioned the hazard map. Also, the colors are very weak, because in that area within the colors, there are very low risk bases neighborhood as well. So now we are going into this structure, and we expect our portfolio with new structure versus the variant is well distributed. And if you look at the regions, now how many 60, 70,000, we have 60, 70,000 of the neighborhoods. See, this is the distribution of the neighborhoods for each group. So it's well diversified from that perspective as well. Of course, there are other analyses which for each village or what the rate, how they are going to fluctuate, etc. But at the end, I can say with this new tariff and the old tariff, the total volume of the pool is not going to be reduced. Between 5 and 7% is gonna go up. Those are the very simple, very quick concerns about how technical pricing goes into the commercial pricing. So lots of marketing, sociology, psychology, lots of public surveys, etc. See, the earthquake happened, and what we did actually in this is the results. Mostly the notifications are coming from the west of the Istanbul, and in Istanbul, each and every building they are geocoded in our system. Look at the mess around you when you are outside. Each of them are geocoded. So as soon as we get the claim notification, either from IVR, either from the web or SMS. SMS, we have only one anyway. If we have SMS, immediately we are able to see which apartments the claim is coming. So we were able to test this structure first, and out of this screen from the left, we are able to run whole operation digital. At the moment, with this incident, actually, end to end, without touching any human, we are able to process the whole chain digitally, starting from the notification till to the payment, without any human touch. What we learned actually, first time we were able to test our digital loss assessment. Professor Zerkol methodology is on the iPad, and adjusters goes with the iPad. You know what's happening? In adjusting how it works, adjusters goes into the site, and they take the notes, photos, etc. And when they go office, then they go to the office, give it to the assistants, etc. And a few weeks later, they submit the report. Now what's happening? As soon as adjusters leaves the building, adjustment is done. We have the report. This is the beauty. Now we give in earthquake of one, we distributed like 150 or claim files to each adjusters, and it took us like more than months, sometimes 2 months to get them back. But we gave around 100, 150, 200 claims to the adjusters, and immediately in next week, all of them replied. So this is the really, now we said 3,000 claim adjusters. It was based on the old assumptions. Now we have to change them. We have to improve them because the game has changed. Now it's improving. And for hours we can talk about it, but also the adjustment is standard. We know whoever goes there, whichever adjusters go there, they are going to take the different same pricing criteria through the tool. This is the beauty of the application. Then there were so many other things that I was going to tell, but some of them I forgot, but let me go to another call center. And I told you we have 3 emergency call centers, and immediately after the earthquake, they were up and running. Now the third one, use of digital communication. First time we open up IVR, web, SMS. I mean, we were not expecting those ratios. We thought people will be willing to talk to live agent, human being. But surprisingly, without any how can I push to them or any advertising or notification information, almost 60% of them start using IVR immediately. Really, we were not expecting. Our target was 70%. We thought it was very ambitious, but we thought we were going to do advertising, sending them email, blah, blah, blah, to push them for the IVR. But we are, without doing anything, is 50%. And 70% of them is through internet. And I don't know yet who is this, but one only from the SMS. And first time, the guy is informing the claim from the top floor, 10-story apartment. But so now what we said actually, every claim adjuster first they need to do the structural assessment of the building, regardless of where they are. So those are the findings, but those are very preliminary, just out of the oven. Still needs to be studied. Still we need to more think about it and work on it. And based on this finding, all our processes needs to be changed as well. So let me cut it. It's already late. Thanks a lot. And if any question, I'm here. Thank you.
And now the floor is for Mr. Fuat Bendimerat for his speech.
Good afternoon. Thanks for the invitation. It's a pleasure to be back to Istanbul. It has been a great adventure for me that started in 1999. So I was actually one point of reference. I was there when TCIP was created. So it's been a long journey. Today, it's a very easy presentation. No equations compared to this morning presentation. Just general concept on why we need insurance in the context of resilience building. You know, resilience is a term that is becoming a buzzword. Everybody's using it for different purposes, but it really has a lot of meanings. First, it takes us away from the word disasters. As soon as you talk about disasters, you kind of having some negative concept or negative intonation. When you talk about resilience, of course, you're talking about something that is positive, that brings something positive to society. Okay. I'm trying to figure out this okay? So this is my outline. I'll talk about what is resilience. How does insurance intervene in resilience? What does resilience matter in, why does insurance matter in building resilience? And the new dynamic in risk financing and innovation in the market, and some concluding thought. For those who do not know, I'm here to representing this organization called EMI, which originally stands for Earthquake and Megacities Initiative. It has been since 1998. Professor Erdick was part of the very first board, funding board. We have 20 years of experience working with cities, mostly big cities, and we adopt a very sectoral approach to resilience. There are very many definitions of resilience. I like this particular one because it's simple. This came from the National Academies of the US, and it says the resilience is the ability to prepare and plan for, absorb, recover from, and more successfully adapt to adverse effects. There are many other ones that are much more complicated, but this one has some keywords which are really important. Prepare and plan. So it means that there is some action before the event, that you anticipate what's going to happen or what may happen. Then absorb is, this is going back. Oh, I'm using this one. Absorb is talking about during the event, the ability to absorb the shock and recover from that shock and hopefully learn something out of it and adapt better, transform better. Okay. So this concept, I can be shown graphically into this. I think one of the authors yesterday or this morning presented something like this. So if you assume that the system is not a binary system, meaning it's either falls or breaks or remains, most systems are fail progressively, then let's say we are at some, any type of system, let's say a water system or a transport system or a financial system, any type of system, it's functioning normally until there is some kind of a perturbation that happens, some shock happens, and when that shock happens, it loses functionality. And it can lose functionality to the point where it reaches a state of emergency, meaning, quote unquote, there is some kind of a disastrous situation, a catastrophic situation that happens. And that can last for a while, depending on how bad that event was and how is the capacity of the system to recover, okay, until it starts recovering back, and it recovers progressively. Oftentimes, it reaches some new state of functionality, and then for some time, and then finally recovers back. And it's really, if that system is successful in learning, it can even recover with some gain. Many times that does not happen, but ideally we would like that to happen, meaning there is some learning process that takes place out of that event. Okay. So this system is really not so good, and the notion of resilience is threefold. One is to reduce this duration of the degradation, meaning make it as short as possible, reduce also this period of stabilization, make it as short as possible, but most importantly, reduce this delta in terms of the loss of functionality to the system. Okay. So this is conceptual, of course, but now let's say, I would say, well, I want some resilience into my system. I want some threshold below. I will not go below that threshold. So I fix that threshold somewhere and say, I know my system. I want, for example, to distribute water to 70% of the population after a major event. That's my threshold. I could not lose more than 30% of my functionality. Okay. Then I have to do something into that process, and I create a new curve here that says, well, okay, here's my target now in terms of system that I would define the system to be functioning, so that's my threshold, and I will define the system to be risk tolerant, meaning there is a capability for that system to take some risk, okay, and lose something, but remain functional to a threshold that I established myself. So there is a way to measure that level if I know my system well. As I explained, for example, if I say, you know, I want to control traffic, you know, on the main thoroughfares of the city, then that's my threshold. I have to keep traffic in some of the major roads. And that's my threshold for resilience. I can afford some other stuff to not be operational, but that has to be operational. And that once I define it, then I can establish goals toward how to accomplish it. Okay. So where do we find the theory behind it? It's really this system theory approach, meaning that I can define any system that I have that I'm studying. So, for example, a complexity of the whole city of Istanbul with its people, its housing, you know, its manufacturing, ports, you know, logistics, all aspects of it as one single system. And that system has different characteristics. First of all, that system is subject to an environment. And that environment is really what creates either inside or outside. They can come either from inside or outside, and what's called, you know, stresses and shocks. Shocks are something that happen in a sudden, and stresses are things that come in, you know, progressively and cause progressive degradation. So this system at one point may experience some shocks or some stresses continuously, and that's its outside environment. And I studied, just like all this discussion we have had the last 2 days, we have scientific approaches to study that environment. We call it hazard, or we call it something else. In general language, in general things, we talk about shocks and stresses. Then the system has, you know, some input that comes in, you know. Input means, you know, financial or any type of aspect of, you know, manufacturing or logistics brings in some resources into the system. And then these resources allow some productivity to take place. And as the system produces, it evolves. It gets stronger or it gets weaker. Okay. It gets more resilient or it gets less resilient. Okay. And it produces some outputs. Okay. So I can identify all those aspects of my system and say, okay, well, you know, I know my system. It has some input and some output. It has some transformation process. And when there is an event, actually, it can either it can affect my evolutionary process and create some damage to that evolutionary process. So what happened to recover from that evolutionary process is I can bring more resources into the process. You know, I can bring more resources, and you know, that where insurance comes in. It comes in right here. Okay. So if there is an event, I cannot sustain what I have, then I have to bring additional resources. But if insurance is already there, it's part of my resources. Okay. So that's the system. The system is resilient, of course, if every single part of it is resilient, but we know that some systems are more critical than others. In the context of, for example, of an environment, maybe your financial system is more critical than other things, or maybe your transportation system is more critical, is one of the critical systems, or maybe your water distribution system is one of the critical systems that you have. So we find, you know, this aspect of explaining resilience as engineers in this system theory very practical in terms of understanding what are the parameters that define how to explain essentially this notion of resilience. And it can be applied to any type of system, either a complex system such as a city or one particular system that is selected. Okay. So how does insurance intervene into this? There are four aspects. One is, as it was explained earlier, it's a cash infusion. Okay. It's a cash infusion that comes into the system. and enables the system to restore property and livelihoods. Okay. I'll talk more about each one of those. It's also a means to finance what's called residual risk. Okay. And again, I'll give some examples on each of those. Insurance also reduces what called stresses, meaning the more extensive risk, things that happen all the time and creates like this stress into the systems itself. Again, I'll explain those. And finally, insurance is necessary for the economy. It builds the confidence so that you can have an economic system that works. Okay, so let me just go very quickly on each one of those. First item I said, restore property and livelihoods after an earthquake. That, of course, is the main reason we have insurance. But the big advantage of this is that compared to government, which takes a long time for it to attribute, allocate resources, budget, give it to which institution of the state should, whether the money is there or not, maybe the money is not there, you need a new business, budget allocation after a major disaster. Insurance can come in and infuse cash directly into the economy very quickly. In fact, the quicker it can do that, the more resilient is the system. The quicker it can bring the cash back into the economy, the more resilience it accomplishes. Okay. So that's the first and most important role of insurance, that is often not, stressed. It's often not, understood. Most of the time, we worry about payments, and we look at it in terms of a claim. But when we look at it in terms of a macro scale, meaning some aspect of the economy as a system, then insurance becomes extremely important, okay? Or risk financing in general. And it goes directly, as intended, in the restoration of property and avoid of interruptions of commercial and industrial activity. So it is an essential resource to resilience, meaning without really resources, without financial resources, I cannot restore my activities, I cannot restore my property. So insurance has to come in, and if cash is there, then, and it comes in very quickly, it's very important. I'll talk more about this later at the end when I give an example. Okay, so people are happy. As you see there, in that picture, they're happy. They restore their activities, they restore their life, they restore their property, and they can be happy. Okay. So residual risk, a lot of you probably understand this notion of residual risk, meaning if I start very simply from 100%, I have a risk that is 100%, I can do a lot of effort, as much effort as I can possible to reduce, risk. And all my effort after 10 years or after some times, I can reduce it by 35%, a big deal, And I can also, or 30%, I can also do preparedness and further reduce my risk. I can do capacity building and further reduce my risk. And I can improve all my emergency management responses and further reduce my risk. But still, with all those reductions, I could never reduce the risk to zero. And that 35% that is left that cannot be further reduced is called residual risk. And how do I take care of residual risk, at least financially, is through insurance or some form of risk financing. Okay. So it's an important measure of resilience because it assumes that everything else has been done. And there is always some residual risk. And finding the financing process by which I can restore property and livelihoods and economic activity through that residual risk can come to a great extent through insurance if it's working properly. Of course, this is an ideal context of insurance. And when I'm talking here about insurance, I'm talking about cat insurance, of course, okay. All right. So this also concept of transaction in the insurance, like the money does not go to some big institution of the government. It goes to the policyholder directly. So the transaction is very effective, meaning that cash can be put back into the economy very quickly. That's a very important concept in resilience, because if the money takes time to arrive into the process, it could really take a long time for recovery. If the money comes in fast, the recovery is much, much faster. Okay. So reduce the impact of stress well, we talked about earthquake, or cat risk and cat insurance, but there are other stuff that happens every day. The type of stuff that pollution and air quality and energy insecurity and a lot of things that create, traffic problems and, of course, climate change. Those are called more stresses, meaning they're not extensive, they're not intensive risk, they're extensive type of risk. And insurance can be like this way to pay those claims, pay those small claims as they go, and therefore it plays a role of like a maintenance. It maintains your system. If it works well, it is one that is maintaining the economic process to work. It's the one that is maintaining the economic activity to work. Okay. So it accumulates to this role that is often not very well emphasized, but it's important. Okay. And finally, the fourth aspect is building confidence in the economic system. Most people, or the common person, does not understand that an economy does not work very well if it doesn't have insurance. Insurance is a necessary aspect of the economic system. Okay. So if I am insured, I have higher priority in terms of attracting investment and in terms of survival, because I can show that if something happens to me, I have the ability to pay back and to restore my activities very quickly. Okay. So with reason actually, like in the US, we established those, and even here, like, TCIP. One of the reasons is to make sure that the insurance is available for commercial activity and for the common person, so that there is actually a way to protect investment and to protect property. So this higher level of confidence provide investment in property, business and industries that are insured, meaning if you are insured, yes, as an investor, I can come in and invest into you. But if you're not insured, then there is less likelihood that I will be investing into you, unless my return is much higher, meaning I have to pay higher prices for the risk. Okay, and then everybody else is happy. Okay, so people are happy, private sector is happy, and then civil society is happy, and and citizens are happy. So that's the ideal system for kind of insurance and what the insurance can bring in this context of resilience, meaning if my system has this additional process as an additional resources, and that works well and is effective, then it can accomplish all this. But then, why do I care? In fact, do I really need insurance for resilience? In this context of the discussion. Well, in most countries, and it's still the case in many countries, and government is the last really insurer for cat risk. The government comes in for many reasons, political reasons, for social reasons, for anything, and they come in and pay the claims. But lately what's happening is that that keeps a problem. That creates a problem because then, the penetration of insurance is very low. The insurers also traditionally did not believe that cat risk was insurable, not until the models really came in. Most insurers would say, I don't want to keep, this cat book of business. If I can find capacity to a reinsurer, I give it away to a reinsurer. So it wasn't like something that insurers like to write. It's something that they really didn't like to write. So most countries, you go and say, I want to insure my property. They say, about what? I want to insure it against earthquakes. They say, we don't have a policy for that. So that keeps the rate of penetration very low in many, many countries. And in fact, before TCIP, the rate for, the penetration rate in Turkey for cat insurance was very small. I remember, I think around 2% or something like this. Okay. Now talking about 65% in Istanbul, that's a major difference. So when you have a 2%, of course, penetration rate, you're not going to have an insurance system that is functioning, and the government intervenes. And this intervention of the government all the time is seen at least by the insurance industry, as being an impediment to increasing the penetration rate. So it has a negative incentive for people to actually go and buy an earthquake policy or cat cat policy. So this is still prevailing around the world. In most developing countries, this is the case. Okay? You know, if you talk to the insurance industry, they would say, well, you know, we can't write insurance business because the government always intervenes and pays. So for those who carry an earthquake policy, why should they pay for an earthquake policy? The government will come in and they will actually pay and maybe pay more. So why should I have an earthquake policy? So it creates this dilemma that really, if you want to have a financial system like insurance that works well, then government should not really intervene, or should not intervene at least for those who can afford it. Maybe the government should limit its role at, you know, looking at people who are poor and cannot afford it. And that's another discussion into these things. All right, so, and then the favorite things, you're like, okay, and it always happened to somebody else, even if it never happens to me. Okay, so, and all my building is earthquake-proof, quote unquote. So don't worry about it. I don't need earthquake insurance because I live in a new building. This is from the last earthquake in Philippines, 6.7 earthquake, and this is a brand new condominium, brand new. Of course, weak story building, and it collapsed. Total loss. Okay. So these things happen, and but this is a perception, okay? So there's other elements why insurance matters is because it's a low-frequency event, at least for earthquakes. For flood, it's a different issue, or for other type of things. But people forget, or they tend to believe that it's not going to happen to me, and it's not going to happen to my life, because the consequences are too big, so I'd rather ignore it. I'd rather say that it's not going to happen to me. It will happen to somebody else. And that's the general perception of people, okay? That it's not going to happen when I am alive. Somebody else will deal with it. And the same thing for the policymakers. You know, they tend to say it's not going to happen during my tenure as 3 years or 4 years when I am mayor or minister or whatever. Okay, so that's an impediment for insurance. And another one is, well, I wasn't affected in the last event. Nothing happened to me. Okay. It doesn't matter that event was 200 kilometers away, you know. But for the people, their perception is they didn't have any damage in the last event. And therefore, they will always be safe. And therefore, they do not need to buy, you know, a policy or to get earthquake insurance. And the reality is, few people understand what cat risk is and what catastrophic insurance is. Most of the common person do not understand how it works. It's still a lot of work we need to do to explain, you know, what is cat insurance? Why do you need it? And how do you have it? And why do you need to carry it? And how does it work? Okay. And at very, very high levels, sometimes policymakers do not understand how it works. Okay. I'm talking in general, I'm not talking here. I'm not talking here specifically in Turkey or in Istanbul, but this is a general thing. And cost. In many, many countries, the population of the poor is a very high population. A very high proportion of the people cannot afford to pay for it. You ask me, I live 300 meters from the Hayward Fault in California. Do I have earthquake insurance? I'm not going to answer that question. I don't. I don't have it. It's a decision I made. Because I think the policy is not good for a person like me. Because I can borrow money at a very low cost. I can access cash at a very low cost. Okay. And I have collateral to access cash at a very low cost. So for me, my premium is too high to make the equation for me to buy, and my deductible is too high. 15% deductible is too high. The CA has 15% deductible, and a ceiling in terms of the content, and a ceiling in terms of how much it pays. And because I'm very close to the fault, and I know my house is very well built because I'm a structural engineer. But it doesn't matter to the insurer. Okay, it's because I'm close to the fault, very close to the fault, and I'm close to the Hayward fault, which is considered to be the next one to, create a big earthquake in California. So there's an issue of cost, of course. That's why we talked about tariffs earlier and how the tariffs are established. The CE has not changed in California since it started. I'm just waiting for them to change and create a new structure. They haven't. Because they're rich now, and something needs to happen in order for them to actually question what they are doing. Yeah. And that's my personal opinion. Okay. So all this have created the new dynamics in cat risk financing. What created the new dynamics is first, now government, before all those financial crises that have happened, they didn't know this notion of contingent liability. Meaning before, government did not care about whether there are some losses that may happen in the future for which they don't have budget for now. Okay. Now, financial institutions, before they give something to the countries, they ask, so what is your contingent liability? And they have to answer that question. And as soon as they answer that question, they ask that, so how much is your potential losses from a major disaster? And who's going to pay for it? So the ministries of finance before did not have to ask this question. Now they have to ask that question. They have to respond to that question when they're asked. Okay. And what happens also is the losses keep increasing and increasing, and events are creating more and more losses because what? Because there's higher value, higher concentration of people. And then government is saying, we can't pay for this. We have other programs. We have education, we have health, we have infrastructure we need to build. We don't have cash available. Borrowing cash costs money. So the best way to do this is to shift the burden to somebody else. The first person is, of course, the citizens. Shift that responsibility toward the citizen. Two, shift it toward the capital market or to some form of risk financing. So there is a new thinking in most ministries of finance, in most governments, that it's not acceptable anymore to be this insurer and reinsurer of last resort, that there must be a mechanism, new mechanism for insuring risk and insuring cat risk. This change in paradigm is now predominant. It wasn't 10 years ago, even 5 years ago it wasn't. It was very difficult to discuss this notion of government should not be responsible for this. They should find ways to shift the burden for paying for major event away from the treasury towards some other aspect. Makes the citizen more responsible. If they can afford it, they buy other things. So why not buy a policy that covers you for earthquakes or other type of hazard? So this new paradigm is really very important in terms of what is happening. Of course, we're talking about urbanization. The world now is irreversibly urban, meaning more and more people are living in cities. And not only that, the wealth is getting higher, meaning the cost of the asset, the price, the value of the asset is getting more and more. So that's why we also see losses that are higher and higher. Okay? And there is also this domino effect. You know, we know more, an event can create another event, can create another event. And what's happening, for example, in Fukushima is very important and very interesting. You know, the government of Japan has been able to build and rebuild everything, and yet people do not want to go back because they don't feel safe from radiation. And the government is having a hard time restoring the economic activity. If you go back, and I went there, and I visited the whole things the last December of last year, you know, everything is rebuilt. New train stations, new malls, new market, new everything. But very few people are living in that area because of the radiation impact. Yeah. So this domino effect is also making people think. You know, the losses can be very high. The losses can, you know, there is no limit in terms of how much a big event can create in terms of loss. We see it increasing and increasing, and that creates fear in the mind of, you know, the ministries of finance and people who are supposed to finance and find the money in terms of where to get it. And then finally, climate change, you know, which definitely has an impact on severity and arguably on frequency. But we see events that are, you know, more and more severe and more losses, and we see them happening. Now, every October we have, you know, wildfires, urban fires in California. Last year, this year, before they would happen in August. So this change also is making people rethink about, and this new paradigm is really what creating a new dynamics. And TCIP was really the early model into this process of shifting the burden of paying for losses from the government into first the citizens. In this case, that's the system of TCIP. So by doing that, you can spread the risk, as it was explained, you know, in the earlier presentation. You can spread the risk among many property owners and reduce the cost. The more you spread, the more you can reduce the cost. So the higher you increase the penetration, the lower the cost is going to be. And you make it more and more affordable to people. So the key then is increase that penetration. Yeah. And that's the strategy of TCIP. You see, the first presentation by the chairman, he said, our objective is to increase penetration by 100%, to come up with 100%. Everybody insured. Yeah. That's the first strategy. Okay, it's the first line of defense of government. It shifts losses toward the property owner and reduces its contingent liability. Now the government can say, okay, well, I can calculate what my contingent liability is, and of course, get a better rating and borrow money at a lower cost. Yeah. TCIP, I remember, struggled at the beginning. They went 2.4, I think something like immediately 2.4 million policies, then it went down to around 1.1 million policies. And for some times, they were maybe not sure even they will survive or not. And then new aspects came in, and new management thought came in, and new management strategies came in. And now TCIP has a lot of money. You know. And why is it important? Yeah. This is 2016. I didn't update the numbers. We heard the numbers a little earlier. But imagine just for the cash that it has, TCIP can put $136 billion into the economy very quickly. No other means can do that so quickly. For government to mobilize $136 billion plus the reinsurance that they have, the capacity in reinsurance, all in a sudden, like $5 billion, and put it into the economy regionally, all in a sudden, is a major contribution to resilience. There's no other way. There's no better way to do it. To do retrofit, it will take 50 years. It's necessary maybe to do it from a standpoint of reducing loss of life. But from the economy standpoint, it doesn't make that much difference. What makes a difference is putting $6 billion into the economy and putting it fast. Yeah. And that is really the evidence of resilience, the contribution of resilience not only to Istanbul, but to all major cities and to the country. And that makes my point. There's more innovation, of course, coming to the market. Thanks to the international financial institutions, the World Bank, the Asia Development Bank pushed hard on this. They go everywhere trying to convince government they should have mechanisms for risk financing. And there have been many different experiences and good after TCIP, which was the first ones. We have the Caribbean, something in Africa about drought. many different type of experiments that are being out there, bringing a lot of innovation to the market. Of course, it's all possible because we have CAT models. Before, it wasn't possible to do all these new transactions. It started with the CAT bonds, and the CAT bonds were the first innovation where the insurance not only had the possibility to reinsure, but to go to the capital market, which of course is much bigger than the reinsurance market. And the capital market was interested. Why? Because it's uncorrelated risk to what they write. You know, I wrote a paper way back there, maybe 15 years ago, that shows that if you have 10 uncorrelated risk, your probability of ruin is almost 0. It's like 10 to the minus 25. Yeah. So adding CAT risk to a portfolio as another derivatives for any kind of fund is an ideal. They're willing to pay for it. So the capital market was very eager to adopt this new form of derivatives that comes from this other type of risk that is not at all correlated to the stock market or to the real estate market. You know, it's strictly CAT risk, different things. Okay. But it's because we have CAT models and we can actually calculate losses and calculate the probabilities, because the price is not based on the expected value, it's based on this distribution or the volatility around that expected value. So there's CAT models enabled new financial products directed toward the capital market, as I said, which was a really an important step in terms of insurance. And that has really improved in terms of providing this possibility for government to shift the burden of loss toward the property owner and toward other agents such as investors. They're willing to take on that risk. So why should the government take it? Government has other obligations with respect to educating people and providing them with health and good living conditions. And that's the primary role of government. Okay. So I give you an example of what I call by innovation. This is a new model, a new product that is being done in the Philippines. It has not been gone to the market yet. Okay. And what it is it's a pool, a city disaster pool, a pool for cities. So what happens is the city can buy an insurance for, let's say, their buildings or their cars. Why can't they buy insurance for losses that can happen from disasters? The Philippines has a very decentralized governance system, meaning cities have a lot of abilities to do their own, do their own budgeting, borrow money, things like this. So this product is worked out between the Ministry of Finance and the Asia Development Bank, and EMI, we did the modeling, the exposure database for it. We use the RMS model, and Willis Tower Worldwide did the pricing for it. Okay. And it's very innovative in the sense that what we have seen is, so it's a city disaster pool, meaning cities come together and they create this insurance mechanism by which they can buy insurance to protect themselves. They don't need to rely on the national government. They can by themselves buy their own insurance. Okay. And the reason is this, as I said, what we have seen by evidence is that when cash is available, the recovery process is much faster. Okay. Every disaster shows that. The cities that have the cash and have access to cash very quickly recover much faster than cities that do not have access to cash, or communities, or governments. Okay, so making cash available very quickly to cities help them recover much faster while waiting for all the apparatus of the budget of the national government to come in. Okay, so this system works that way. So it serves as an additional source, and it only covers the cost of emergency, essentially, and early recovery. It does not cover the reconstruction, because that's a different system. There is another insurance system that is mandatory for government institutions to buy, but that government system does not pay for the immediate cost. So this tool, or this financial product pays for that. Okay? And okay, so I'll skip this. So it works like this. This is called PCDIP. It really has the notion of fast payout. It's an index, a parametric index product, meaning it's not based on indemnity. It doesn't care, you know, an event happens, it passes the threshold, you get paid. And you get paid immediately. Okay. And it's a pool, meaning the cities themselves. As I explained, in the Philippines, there is this GISS, which is a mandatory indemnity insurance program for government institutions, but that doesn't pay. It doesn't pay for these immediate losses. So PCDIP comes in just to pay for the immediate losses, put cash essentially in the hands of cities immediately after an event. Right? I like that part because it's very innovative. It's set up as a special purpose vehicle. Those of you who are in insurance understand that. And it really functions like the cities go into this pool, they pay their premium. The premium is used for reinsurance and create a reserve, just like TCIP, you know, and pays the benefit back to the cities. There were initially 10 cities as a pilot, and all the cities were interested. They were all interested. Okay. But you have to design the system in such a way that it's for tropical cyclones, which is typhoons in the Philippines, and earthquakes. And it's designed in such a way that it pays very fast. It's also flexible in terms of how much you can buy. Cities can buy a certain amount depending on the risk, okay, and pay only that amount. So it gives them the flexibility to choose how much they want to cover and how much they want to, depending on their risk and the possibility for paying the premium, okay. And the benefit of the cities, as I explained, is really simple, it's cost effective, it gives them money immediately, you know, and it's great value, you know, it's low cost, they can choose how much they want to cover themselves for, you know, it creates additional awareness, it makes them accountable and responsible, they don't need to rely on national government, which is always a burden, they can do that on their own. Again, if they are able to buy a policy for their fleet of cars, why can't they buy a policy for covering themselves from an earthquake? You know, it's a simple insurance policy. And if they are pooled, they can all benefit from it, you know, and you can pay them back. It's, as I said, flexible, and what the key there is rapid financing, meaning it quickly pays very quickly. So imagine if you are hit by a major typhoon and you are the mayor and the city council and you're sitting there and say, where are we going to get the money to go and, you know, create shelters or clean up the streets or get people back to their homes? Well, you don't need to ask these questions anymore. You don't need to have a claim adjuster. The money is going to come in. It's written in your policy. So instead of thinking, where am I going to get the money, you're thinking about what I'm going to do. And that's a major change in terms of the mindset, and that's where, you know, resilience comes in. So for a country like the Philippines, get so many earthquakes and so many typhoons every year, about 24 typhoons a year, this is an excellent tool. All right, so lesson learned. No question, insurance and risk financing are important elements in building resilience. The overreaching mission is to protect, of course, the state finances from a standpoint of government, of course, at the micro level. What the government is doing this is already, why do they create TCIP? Is because they want to protect the state finances. But they also want to protect property, they want to protect the economy, they want to protect the productive capacity of the country. But, you know, insurance has a problem, it's regulated. For good reasons, it's regulated. And sometimes innovation is hard to come in. But it's inevitable now. In the global context, it's inevitable that, you know, just like we heard in the last 2 days, and just like we heard in the last presentation, it's inevitable that innovation is going to be there. And many, many people are thinking about it, and new products are coming in. Why is it inevitable? Because the government does not want to hold this contingent liability anymore. There is a change of mindset. Because people are, they ask, how much is your contingent liability? Before they didn't know what it was. As I said, innovation is sustainable. Now for TCIP, I don't want to say anymore. TCIP cannot fail. It's the first experience. It's getting to 65% penetration in Istanbul, which is very good, 50-something in the rest of the country. But in the long term, we heard about these claims and how big that problem is. I understand that maybe it's difficult to have an index parametric process because it's not toward an institution, it's toward an individual, and maybe that's not fair, but at some point, there is no way around it. I think the best way to be efficient, meaning the transaction becomes very efficient, is to go toward the parametric, index parametric model. Exposure database, we know, and I was very pleased to say, they have geocoded every single property. So once you geocode it, you can attach information to it. You can attach the type of buildings, how many people are there, how many units, whatever. All this information can be there. So you can do all this proactive, and that's why TCIP is going into that direction, because they invested in terms of technology. Okay? And so you do your front end, it's your technology, the back end is your expertise. You don't put your expert in the field, you put them to develop those applications. And the front end is the policy holder and the application that he or she has on their phone. So I thank you very much for your attention, and I'm sorry if I took some of your time, Charlie. Thank you so much.
We thank Mr. Bendimaret for his interesting presentation, and we invite Mr. Charles Carlton for his presentation to the stage.
Thank you very much. It's my pleasure to be here this afternoon. I would like to speak to you about the topic of fire following earthquake, but before I do, let me just say that almost to the day, I first came to Istanbul 48 years ago, and I arrived by ship at dawn, and this was the scene that I saw. Later that day, I went to my hotel in Pera, and this was the scene I saw. Now, in San Francisco, we have a song called "I Left My Heart in San Francisco." But I like to come back to Istanbul to visit my heart, because this is just such a wonderful place. I've had a long history of ties with Turkey. Tragically, of course, the Marmara earthquake, I led a U.S. team here when we surveyed that damage. And then also, among other things, I'm an advisor to the World Bank, and I was involved in the development of the original TCIP concepts and modeling. So I am very pleased, and I think I speak for everybody at the World Bank, extremely pleased how TCIP has grown and prospered and has become just a leading model of how to develop a national CAT model program. So the outline of my talk is shown here. I'm going to talk about, why do you care about fire following earthquake, an overview, and how you go about analyzing it. And I'm going to illustrate by case studies for several cities the risk. We'll talk a little bit about mitigation and some recent advances, and make some concluding remarks. So why do you care? Well, because fires can greatly exacerbate and multiply the losses, such as we saw here in 1906, great San Francisco earthquake. And this famous photograph by Arnold Gentha illustrates many things. It shows the fire, of course, down here, but it shows the loss of the facade due to shaking, which changed the fire vulnerability of the building, allowing fire spread to move much faster. And we see many people standing here watching the fire with their hands on their hips. Why? Because there was no water. They had no way of putting the fire out. All they could do was stand there and watch the city burn down. And of course, that's what happened. 28,000 buildings were destroyed in that event. This is not just a unique event. In Tokyo in 1923, we had even a much worse situation. These were people fleeing in the middle of the fire. These are, you can see here, all these people trying to get out, and they were really trapped. And fire whirls developed, fire tornadoes, and the people really had nowhere to go. And 140,000 people were killed in that fire after that earthquake. So it can be a terrible event, not just financially, but in human ways. Of course, Istanbul is no stranger to fires and earthquakes. Hagia Sophia has been damaged by earthquakes several times, and the walls of Istanbul have been damaged by earthquakes. 1894, we see the distributions of damage in the Sultanahmet area, of course, 1999. And it's also no stranger to fires. There have been many fires in Istanbul. I think you know, the London earthquake of 1666 is world famous. But most people don't know that Constantinople had a fire just 6 years earlier than that was even larger. One of the great fires in all history. Many tens of thousands, perhaps 100,000 or more people died, buildings were destroyed in that fire. And of course, more recently, this is the Pera fire of 1870. Also in 1908, great fire, and so on. Why were these fires occurring? Because two reasons. The building fire resistiveness was not very good. While there's a masonry facade on these buildings, the interiors are still wood beams and still very flammable. And the fire service was not up to the job at the time. The buildings haven't changed that much in parts of Istanbul. Much of the outer parts of Istanbul are very modern, like this building, but there are still major parts of both Sultanahmet and Pera where you could have a great conflagration today, especially after an earthquake. You have fires in Istanbul all the time. I think you're familiar with this fire at the train station in 2010. The Polat Tower, 150-meter tall building with a fire in 2012. And just in Taksim last year, major hospital fire. These are individual events. Your fire department can try to cope with these. But if you have many of these, they are completely overwhelmed. So there is a vulnerability here we need to look at. So that's the problem. The problem is fire following earthquake. And there are many events. That was 1906. We have 1964 Alaska earthquake, 1989 San Francisco, 1994. These are all California events, Los Angeles earthquake and fire. And so there's a large body of data. And of course, we have the fire in the Tüpraş refinery, and there were other fires in the 1999 event. The problem is exacerbated today by these high-rise buildings. Any one of these buildings on fire, as you saw a moment ago, consumes the resources of the fire department. And if there are many of these on fire, they just are not going to be able to deal with it. And there are many high-rise building fires. Just very quickly, this is the tallest building in California in 1991. Required virtually all the resources of the Los Angeles Fire Department. And there are many high-rise fires. I could go through and discuss all of these, China, Madrid, and so on. And we've seen, of course, the terrible Grenfell tragedy in London a couple of years ago. And Fukushima, what was it? It was a fire following an earthquake and tsunami. Admittedly, in an industrial facility, TCIP doesn't insure, but it's the world's first trillion-dollar disaster. It was a fire following an earthquake. Okay, so this is the problem. So historically, this bar chart shows time, and it shows some great conflagrations in orange, and then fire after earthquake, 1906, Tokyo, 1948, Fukui, and some of these other events. And the history of the modeling, Freeman wrote a book in 1932 about this, and after World War II, the Japanese started to develop their models, and there was a whole school of development in Japan because it's a great problem in Japan. That was where I studied and learned about this problem, and then following that, I developed some models, and since that time, those models have been used by all the major modeling, cat modeling, and insurance companies. And since that time, we've been in a period of data collection and improvement of the models. And more recently, we've had developments in physics-based fire spread, I'll be talking about a little bit, and work in New Zealand by Cousins and Thomas and all to look at the problem there. This is some of the documentation that's been developed over the years, data collection of American Society of Civil Engineers monograph on the subject. And this is some of the data collection from earthquakes and from non-earthquake fires to study the problem. This shows some of the data collection. This is the 1971 San Fernando earthquake, and it shows the various ignitions here. There were over 100 fires after that earthquake. And this is Morgan Hill, a very small event, still 3 fires. Excuse me, that was Coalinga. This is Morgan Hill. And we have many other events. This is a Whittier earthquake, the San Francisco 1989 Loma Prieta earthquake. And of course, these colors are the isoseismal intensities. And then again, the Northridge earthquake in 1994 with over 100 ignitions. We also had the Tohoku earthquake with over 300 and major fires there. There were 345 fires in that event, and this shows their distribution throughout the area. Many of them, of course, in the Sendai area, but a fair number down in the greater Tokyo Bay area also. So all of this data goes into the modeling. So what is the process? This diagram illustrates it. We see here time. And the earthquake occurs, we'll call it time 0. And with the earthquake, we have a number of ignitions that occur. We've numbered them here, 1, 2, 3, 4, 5, and so on. Many of them occur very soon after the earthquake, but some occur hours later. I will discuss the causes in a moment. But there's a period from each of these, when the ignition occurs, there's a period during which the fire grows, and the width of the red bar shows the size of the fire growing, until it is discovered, and then a period from the discovery to the time it is reported to the fire department. So, and during that time, the fire is growing. Eventually, the fire department arrives. It puts the fire out, so the bar turns from red to blue, and then that engine redirects to another fire. That engine, with other engines, puts that fire out. Then they redirect to another fire, and so on. And they all converge on one or more of these larger fires, and the question is, do the fires grow into conflagration proportions? So that is the process by which fires grow after earthquakes. How do we go about analyzing that? Well, there's a flow chart here. I'm not going to go through all of it. You can read it here. You can see you have the earthquake, the ignition, suppression, and so on. But the key parts I'm going to talk about are shown here. We need to define the earthquakes, and we've spent most of the last day and a half doing that. We'll talk about the assets at risk, the fire department response, the infrastructure, the performance of the infrastructure, and the fire spread. So let me discuss each of those. The sources of ignition are shown here. This is both from Kobe and Northridge earthquakes, and we can see the fractions that were due to electrical equipment, chemicals, and so on and so forth. So we have a fair idea of what's going to be causing these. The fire spread is shown here, and we can model fire spread both empirically and physics-based. The empirical data is shown, for example, in this map here. This is the 1991 East Bay Hills fire, a non-earthquake event, but we can get data on fire spread from that. And in that fire, 3,500 houses were destroyed in about 12 hours. And we have many data on urban fires here, and most people don't appreciate the violence of these fires and how you need really well-equipped, well-trained people to put those fires out who have water. Without that, the violence of these fires is hard to believe. It's unimaginable, and they will just continue to spread if you don't have that. An example of that is shown here from a Philadelphia incident of some time ago, and we have a bunch of row houses here, and for various reasons, the fire department was unable to respond to this, and the fire just, whoops, sorry, let me try and go back here. Yep, the fire, you can see even though you had masonry buildings just like you have in Istanbul, the fire spread around the party walls and would have just continued to spread until finally the fire department was able to arrive and contain it. So we have data here. This shows as a function of wind speed, the total number of buildings that would be burnt, depending upon the density of construction after 20 minutes, for example. And we also have here, and I'm sorry, the bottom is cut off, but this is the probability of crossing fire breaks like streets and major highways as a function of wind speed. So for fire spread, now more recently there's been advances by Himoto and others using physics-based modeling, and this is Himoto's paper, and we can see here also, by the way, modeling ignitions using mechanistic models to try and determine. We saw work before about the fragility of contents. This is basically the fragility of contents in the manner in which they would cause fires. So that fault tree diagram was for that purpose. Fire spread is shown here. This is from work by Lee and Davidson, and we can see here as time goes on, you'll watch over here, the fires are spreading. We're modeling the fires as time goes on and the fire growth. So we can do that. When it comes to water, there's a number of ways to look at it. I'll talk about the performance of water systems in a moment. But one of the things I did at the University of California was to do a survey of water and fire agencies in California. Basically, surveyed the agencies that serve about a third of urbanized California, over 10 million people. And the key findings were that while they see this to be a problem, they see earthquakes to be a key issue, that even where the water departments have knowledge of the vulnerabilities of the system, this is not communicated to the fire departments, and they both expect that the water systems are going to fail, and many water departments are addressing this problem, but the information on when water would be restored is sparse, and some water departments have alternatives given normal water supply, but most fire and water department liaison is not very good. So really, the water systems are going to let the fire departments down. That was the bottom line. Let me illustrate this by some case studies. This is the case study for the for the San Francisco Bay Area. This is San Francisco Bay. The city of San Francisco is here. We have Oakland, Berkeley, and other cities here. There's about 6 million people. Fuad, by the way, and I both live right in this area. This is about 6 million people living here, and it is threatened by two major faults, very similar in many ways to Istanbul. This is the Great San Andreas Fault, analogous to the North Anatolian Fault, and this is basically just a child fault of the San Andreas called the Hayward Fault, which is still capable of magnitude 7. We looked at 4 events for this study. Basically, on this fault, a 6.5, which would have that rupture length, a 7.2, which would have a rupture length of about this length, and then a 7.9, which would extend from, well, somewhere over here to somewhere over there. And then we looked at a magnitude 6.9 on the Hayward Fault. And the probability of this, just like in Istanbul, we're expecting these earthquakes to happen in the very near future. Now, San Francisco, to quote the fire chief, is a city built to burn. This is all wood construction in here, and it's about a 800,000 population city, just the city itself. There's about $200 million in value, excuse me, about $100 billion in value at risk just for the buildings. And 90% of those buildings are wood. Of various configurations, many of which are quite vulnerable. The soft story, this is the 1989 earthquake where these larger buildings were collapsing, and as a matter of fact, where the fires occurred. The values are enormous. Just that, for example, if you take that few blocks, that's $1 billion. And that a fire can easily consume that if it's not fought. So to model the earthquake, we looked at ground motions and so on. We looked at the 4 scenarios. Those are the actual isoseismos within the city. This is just one of them. This would be for 7.9. You can see the fault is running right through this area here. So you can see that the peak ground accelerations are quite high, on the order of approaching 1G. Of course, we know the areas of liquefaction, which caused the failure of the water system in 1906 and in 1989. resulted in pipe breaks there. That was a very young person at that time, these sorts of pipe breaks. And as a result, we had one major fire in that small 1989 event. This shows the initial stages of it, and as it grew, and it became a very large fire. Fortunately, it was only one particularly large fire, and San Francisco was able to respond to it. Those mains were broken. As a matter of fact, there were over 100 breaks in the water system in that area, and the fire department was able to respond to it with their fire boats and contain it and put it out. This shows for the postulated 7.9 event, the breaks that would occur in the ordinary drinking water system just as they occurred in 1906. And because of that, San Francisco has built a special system called the Auxiliary Water Supply System. This is a high-pressure system. It was proposed in 1905 by Chief Sullivan. It was built after the earthquake. It has three basic parts. It's highly redundant, and it's designed to survive the earthquake. And this shows the system here. There's a 40,000-ton reservoir, 10 million gallons in English units, a reservoir at an elevation, well, it's shown right here, at this location, an elevation of about 200 meters. And that's really meant for non-earthquake situations. And for the earthquake, there are two pump stations, pump station number 2 here and pump station number 1 here, each of which can supply 40,000 liters, that's 40 tons a minute, of water into the system. There's over 200 kilometers of high-pressure piping throughout the city. The fire boats can also inject water into the system, and so on. This system was, again, built from 1907 to 1912, and the city is now extending the system and spending hundreds of millions of dollars to improve it. Again, this shows the fire boats here, the pump stations down at the water. And it was ironic that in 1906, San Francisco burned down, even though it's surrounded on 3 sides by the largest body of water on Earth. So as a result of that, they built pump stations here to access that water. To back that system up, so that high-pressure system is a backup to the ordinary drinking water system. But to back that system up, San Francisco has built, has over 200 cisterns, underground water tanks, each of which hold a 1-hour supply for a fire engine. And you can see here a fire engine accessing through a manhole one of those cisterns. That's a cistern under construction. San Francisco continues to build them today. And this shows what you see normally. You just see a circle of bricks telling you and the fire department there's an underground tank there. That's the manhole that they open up and can pump the water out of. And there's over 200 of these in San Francisco. Tokyo, by the way, has 40,000 of these kinds of cisterns, although they're smaller cisterns. So looking at this sort of repeat of 1906, we can see the patterns of ignitions that would occur here, and the shaking losses that would occur in that event represent a loss of somewhere between about $12 to $39 billion, representing that fraction of the value of the building stock, and the fire following earthquake would add about an additional $10 billion to that. So the fire following earthquake losses, on average, represent about equal to perhaps 50% of the total shaking losses. Of course, these losses in the U.S. are totally insured, fire losses, not earthquake. If we have adverse wind conditions, these losses can be much higher. So that's San Francisco. Vancouver, Canada, after the 1989 earthquake, looked at what had happened in San Francisco, and it has, as you can see, a very large collection of high-rise buildings. And their water system, their water comes, the photograph I just showed you, the high-rise buildings are here. This is their water distribution system, and it's supplied by reservoirs across this body of water called Burrard Inlet. And this area is subjected to a major earthquake, subduction zone earthquake called the Cascadia event. Both of these submarine crossings will fail in an earthquake. So to provide fire following earthquake coverage, the city built a dedicated fire protection system similar to San Francisco's. This is built in the 1990s. There's 2 pump stations, one here and one here, and it has this network. Actually, it's been extended since then. And this shows that the pump station 1, pump station 2, and the network protecting the downtown central area. This shows pump station number 1. Well, it was still under construction. This photograph's in 1995. And you can see here they were pumping water just to demonstrate the pumps and how it works. This, by the way, is now a show that's put on every week on Friday night to exercise the pumps and entertain the public. This is pump station number 2. It's unmanned, totally underground, very unobtrusive. And the city did, these pump stations did not cost the city a penny. There were developers who were building major developments in these areas, and as part of their requirements, the city required that they build the pump station in addition to the profit-making high-rise buildings. So that's Vancouver. I'll talk about Los Angeles now. Los Angeles is threatened by magnitude 7.8 earthquake, also on the San Andreas Fault. This is Los Angeles. Although this area is rather far away, it still causes a tremendous amount of damage in Los Angeles. And this was modeled as part of the shakeout funded by the USGS exercise. And this shows the patterns of shaking that are anticipated. You can see very high shaking on the order of MMI 7, 8, and 9 in this area in central Los Angeles. And as a result of that, we anticipate over 1,600 fires will break out. Tremendous number of fires. And again, we'll have failure of the water system. This shows the fire stations in that area, and there's more fires than there are fire stations. This is a detailed close-up in the area. So you can see in certain areas, there's enough fire stations to put out some of these fires, but in other areas, there isn't. This is all reported here. The total area that is calculated to burn, if you added it all up, would represent an area about this size, which is really only a small fraction of Los Angeles. But on the other hand, that loss represents 200 million square feet. That's about 20 million square meters of building floor area with and you can see the density of construction here. That's why the fires will spread. And the result is this area, for example, is $10 million worth of exposure. So the total losses are estimated to be about $65 billion due to fire following an earthquake. Again, all insured in the U.S. Insurance practices in Turkey are perhaps different, so it may not be as insured as it is here, as it is in Los Angeles. So this is a very large loss. I mean, this is a loss that will stress the global insurance industry. So 1,600 ignitions, 1,200 exceed the capacity of the first engine. We will have large fires merged into conflagrations, destroying hundreds of blocks, destroy about 133,000 single-family dwellings, $65 billion in property loss. This is not the worst case. This is the average case. If we have Santa Ana conditions, you've seen what happens in the wildland fires we're having in California. And this study was vetted by top state and county fire officials. And again, it's published. As a result of this, Los Angeles, the mayor of Los Angeles has instituted a program called Resilient Los Angeles. And one of the key questions was, will the firefighting water be available to fight these fires? And as a result of that, I've done recent studies to calculate the various, for different scenario events. This is a magnitude 7 Puente Hills event. These are the isoseismals. And these are the ignitions that would break out in the city. And for each of those, we've calculated the total amount of water that's required according to different wind speeds for the different events and in water per ignition and so on. And Los Angeles Department of Water and Power is now using these numbers to basically design improvements to their water system to provide water following an earthquake. This has all been published by them. I think I've got two more case studies to discuss. One of those is Montreal. Eastern Canada, people don't think of it as having major earthquake risk, but this is the earthquake map of Canada, and this shows Vancouver, which is acknowledged to be very risky, and this is Montreal area over here. And this shows the actual hazard curves, and we can see that for peak ground acceleration, the Montreal and Vancouver events have the same probability of occurrence. This is response spectra. So at various periods, the Montreal risk is somewhat lower than Vancouver, but it's still fairly significant. 2/3 of the Montreal fire stations were built before 1980. This is their oldest stations. It's, It's built in, it's an unreinforced masonry building, built in, I think, 1894. And this is their fire department headquarters. It's an unreinforced masonry building built in 1932. So you can see that they have, the fire department itself has vulnerabilities due to shaking, and they may not be there after the earthquake to fight the fires. This kind of construction, by the way, was outlawed in California in 1933. But it's still there, and the fire department is extremely vulnerable because of that. As a matter of fact, as an example of the vulnerability was the 1988 Saguenay earthquake, a magnitude 5.9 earthquake. This is, Montreal is here. This is about 100 kilometers away, and yet this was the damage that occurred to the Montreal City Hall in that event. So Montreal has a significant earthquake problem and a fire following earthquake problem, which I've just actually been looking at for the city of Montreal. In doing that, with several people, several of the speakers have talked about spatial correlation ground motions. These were taken into account. These are the median ground motions for one of the scenarios, a magnitude 6.5, a direct hit on the downtown area. And these are some of the variations due to spatial correlation that could occur instead of the median event. So all of these were used to model the effects on the water system. And spatial correlation, the context, it was discussed here for an individual site and then for a portfolio of individual sites or a portfolio of buildings. But it was not discussed here, except Peter Stafford very briefly discussed it in the context of a traffic network. If you look at the fire following earthquake problem, spatial correlation has a double whammy effect in the sense that normally you want the demand for water to be less than the capacity. So you want the ratio of the demand due to ignitions to be less than the capacity of the water supply system. This is demand less than capacity is good. But in an earthquake, what happens is the demand goes up because there are many ignitions, damage to the water system drops the capacity, and what we have is the demand far exceeds the capacity due to spatial correlation. As a result of that, and this shows the ignition patterns, actually the ignition patterns that would occur in that study area. This is a report that will actually be released in Montreal in 2 weeks. Oh, sorry. This is something else. But I just want to say that the spatial correlation here has a very strong effect and needs to be calculated and taken into account in all future infrastructure type studies particularly. The last case study I want to talk about is Istanbul. About 10 years ago, the Willis insurance brokers asked me to look at fire following earthquake in Istanbul. Professor Erdek was very helpful on that project, and I want to thank him for that. And the modeling that was done at that time did not take spatial correlation into account. The building inventory was not what we have available today or what we will have in the future due to the good work of Professor Crowley. But this was some of the shaking intensities that we were looking at. We looked at several scenario events. This was the building distribution data that we collected. This is a characterization of that building distribution on a grid basis in terms of masonry, wood, and so on. These are the fire stations in Istanbul. And this is the water system for Istanbul. And we also had the IGDASH gas system data. So we did all of this modeling, calculated the damage to the water system, the number of ignitions that would occur, and so on and so forth, and finally produced what we call a burn ratio map. And what this shows is on a grid basis, given the type of construction, the shaking intensity, damage to the water system, and so on and so forth, what fraction would be lost in each of these grid cells due to fire following an earthquake. And I believe this is being used still today in the insurance industry here in Istanbul. But as I will talk in a moment, in the last decade, many improvements have occurred, physics-based modeling and so on. And we've seen all the improvements that have occurred in ground motion modeling that really could enhance this kind of a study. Mitigating fire following earthquake, there are many examples. San Francisco high pressure system I just talked about, Vancouver and so on. and I'll just talk about a few of these in a moment. If we look at the basic flow chart that I showed earlier of the earthquake, the ignition, the discovery, the report, the fire department response, suppression, and so on, there are opportunities for intervention at every one of these steps. If we can cut off the gas and power by seismic shutoffs, then we reduce the ignitions. If we can have remote sensing detection, then we improve the discovery time. We decrease the delay in recovery. If we have some kind of information communication technology, such as smartphones and so on, we can improve the reporting of the fire. If we have this kind of information, then we can have an improved fire department response. And if we have reliable water, we can improve our suppression of the event. And again, if we have the fire department decision-making is improved, we can reduce the spread and conflagration. So let me discuss these a little bit. In terms of, in San Francisco, for example, we have the neighborhood emergency response teams. So these are citizens, and probably Istanbul has a similar program, where the citizens are trained to do light search and rescue, and to some extent try and identify and report the fires. Seismic shutoff valves are required, for example, in Los Angeles now. After the 1995 Kobe earthquake, Japan replaced all of its gas meters in the entire country with seismic shutoff equipped gas meters. We need that in California, and I don't know the situation here in in Istanbul, but that would be a good thing here. This shows some of the types of gas shutoff valves that were being used in California. The improvements to the water system, this is, for example, in 2010, San Francisco decided by ballot, people approved $400 million to be spent on improving the high-pressure system. So, I mean, real money here. Now, advances. This is the last part of my talk. I'm just going to talk very briefly about things that have occurred recently and are occurring that improve the modeling of fire following earthquake. The first I've talked about already is the spatial correlation in ground motions. Previous estimates, because they neglected spatial correlation, underestimate the number of ignitions and the damage to the water system. I've talked about that double whammy. I'll illustrate that in a moment. We have better data. We've gotten a lot more data from the Tohoku earthquake. We actually have actual building footprints now. Some other speakers showed those briefly. I'll just show that in a moment. We have inventories of urban trees. The vegetation, at least in California, is a very significant part of fire spread, so we have better estimations of fire spread. We have the physics-based modeling of fire spread also. Himoto was the first one to do that. And we have improved modeling of water and other lifelines and their interdependencies, and I'll just very briefly illustrate that. The spatial correlation, I've made this point already, that the double whammy effect that occurs here. And exposure data, this is San Francisco, and modeling I'm doing for the city right now. And you can see we have data on every building footprint, and this is readily available from various sources. This is from the city itself, but as Professor Crowley mentioned, the OpenStreetMaps also can provide this in many places. And we also have the data on the tree inventory. Every tree in San Francisco has been mapped. We know the species, we know the canopy, so we know the fuel from the natural vegetation as well as from all the buildings. And the colors here, by the way, represent different occupancies. And this would be in Istanbul. The same sort of building footprint data is now readily available. And this shows the water system, the blue lines are the water system pipes and the individual buildings, the Grand Bazaar, of course, Topkapi and Hagia Sophia, and so on. So modeling here can be much improved on what was done 10 years ago. And the last point is the interdependent infrastructure modeling. This is, again, work I've been doing in San Francisco. We start with the building density and materials. We take into account the system demands due to fire following earthquake. We have the ground shaking, and due to that, we can estimate the damage to the water system given the peak ground velocities, and also then given the permanent ground displacements. And based on all of that, we can estimate the damage. We then look at the interdependencies due to power and traffic that might affect that system. And we do this in a Monte Carlo. You've heard that term. many times in the last day and a half. And this, in the modeling I've been doing here, I've been doing many thousands of trials to do this entire modeling. The hydraulic analysis of the system actually here takes about 1 second per trial. These are the kinds of things that 10 years ago were not possible, and today are being routinely used in modeling. And with that, I want to thank you very much, and if there are any questions, I'd be happy to respond to those. Thank you. You want to try and take any questions, or I know we're running late. There's a question. Yes, sir. Why don't you? Yes, sir.
Mehmet Ali Özdemir, Anadolu Sigorta Insurance Company. We see post-earthquake fire is one of the non-modeled risks alongside tsunamis for Istanbul and others, liquefaction, etc. And when we tried to assess the risk we have here, we looked at the Izmit earthquake in '99, and we saw that the post-earthquake fire was negligible there, with one significant exception which you alluded to. I have a few questions. One of them is the one that had happened at Tüpraş. How worse could it have developed? Do you have any idea about it? Because it's a huge field of gas storage facilities. Another question, my second question is, it pertains to the infrastructure in Izmit. Today it's mostly, it was also that day, apparently, plastic pipes, both for water and for gas. And as we understand, it resisted the earthquake quite well. Maybe the reason that gas pipes were laid down was not earthquakes in mind, but it resisted quite well. I assume maybe you do not have the updated information about Istanbul's infrastructure, but we assume that we are still using plastic pipes all over the city. So would you agree that this will significantly decrease, again, the post-earthquake fire risk in Istanbul, alongside the fact that now the city is mostly reinforced concrete? Well, due to also the reason that we had so frequent fires in history, and most of our, unfortunately, historical buildings are either burnt down or demolished and replaced by modern buildings. And I have a third question also. Would you like to answer the first two, or should I ask the third one as well?
Let me try and respond. One question you asked was the gas system, and is it in some ways perhaps better
Yes,
than...
and water also, because it is critical as well, as we understand, for fires.
Mustafa, can you help me? I'm having a little trouble understanding him.
Gas and water pipes.
Yes. Yes. Yes. Well, I know the IGDASH system is a relatively new system, and it's better than some of the systems in California, for example, which are older systems. So I agree with you. There weren't that many fires in the 1999 earthquake, aside from Tüpraş. There were some, but not that many. So the ignition rate might be lower in Istanbul. And in the study that we did in 2009, I think it was, I tried to take that into account. But the density of construction you have in Istanbul will still lead to far more fires, I believe, than your fire engines, than your fire department responses. That's the first part of it. And then you mentioned about the reinforced concrete construction, or as opposed to the wood construction in California. And I agree with you. Fire spread, depending upon where you are, will be less in, most likely, will be less in greater Istanbul. And when you get outside of the older parts of Istanbul, it's many mid to 10, 12, 15-story reinforced concrete buildings, or mid-rise masonry buildings. And I think where there are ignitions there, those individual buildings may burn out, but the fire spread building to building will be less. But you have a huge number of high-rise buildings here, and you could easily have 20, 30,000 square meter high-rise building go up in a fire. That's a large loss. So you see that under ordinary conditions, so that if you had, I don't know the number of high-rise buildings in Greater Istanbul off the top of my head, but it must be a few thousand. That's all? Joe, okay. Okay, more than 20 stories high. Okay, thank you. The usual definition of a high-rise building is 7 stories, because that's as high as a fire engine can reach. So anyway, Istanbul is one of the great mega cities of the world, and the whole city is not going to burn up, but the sum of the fires that will occur here will still stress the insurance industry. So I hope that I responded to those first 2 questions. You had a third?
Yes, thank you. Thank you for this. The last question was automatic shut-up system was being discussed as Istanbul's disaster preparedness system is a part of it some time ago. And I don't know how it developed. I know that there are seismometers closer to the fault line than where we are standing now. So that would give us at least a few seconds to shut up gas and electricity systems. Do you know that, if this is still planned, or what's the latest update on it, or does anybody know here?
Yeah, well, why don't I answer that question? The first one, the gas system in Istanbul is pretty well protected. I think it's one of the best in the world. They have one shut-off system, essentially a strong motion recorder that turns off the system when it exceeds certain parameter, on top of the more than 1,000 district regulators. So there are more than 1,000, plus each and every house built, I think, after 1985 has to have a shut-off valve. So I think it's pretty well protected. There's no problem with that. Well, there's obviously an early warning system, but the gas shut-off system does not rely on that. The only thing that relies on that is the 2 systems here. One of them is the Eurasia, and the other one is the Marmaray tunnels. But that's about it. But regarding the gas system, I think it's in pretty good hands. But what you said regarding the tall buildings is very valid. The reason being is that the facades of those buildings are not usually made with granite, other things, but they're made with synthetics, and they can catch fire very easily. And then putting them down is very difficult, because the ladders can only go so much. You may need helicopters or whatnot, but that can apply only to one building. If you have 10 of them going same time, doesn't help.
Yeah. IGDASH, I had some interactions with IGDASH, both following the 1999 earthquake and then in that study. And it's a good system. It's well above average, perhaps the best in the world. As far as the shutoffs go, unless you said post-1985 buildings have individual shutoffs. Pre-1985, you still have residual gas pressure. So even this is a sort of a fallacy. The operators, not necessarily IGDASH, but in California, for example, the operators claim, "Oh, we can shut the system off," but you still have the residual pressure in the gas mains that will feed the fires. And once the fire gets going, it doesn't need the gas anymore. Istanbul is a very different animal, a very different situation than California, and we tried to take that into account in the modeling we did. Your bottom line, your fire risk, post-earthquake fire risk, is the older parts of the city. But you add that up, that's a lot of value and a lot of population. So it's a significant risk.
Well, regarding fire risk, you are right, but regarding ignition,
yes,
it can take place anywhere because of the illegal production facilities under even residential buildings. In the basement, they produce this and that illegally, and they can be explosions and ignitions over there, which you do not have California, obviously, but those are the source of ignitions. Whether it spreads into a fire or not is another question. But
well, I'm thinking of the spread.
Yeah.
The spread, I mean, if you look at the older parts of Istanbul, the fire spread is just inevitable. Yeah. So I hope that answers your questions. Do you have more? Okay. Anybody else? If not, thank you very much.
We thank to our speakers. We'll have a 10 minutes coffee break at the moment, and we will be back with the closing panel in 10 minutes.
Well, I think the coffee break is over, and we are resuming our program. And then what we will have in the program as the end of the session today is a panel session on essentially what we have learned and what's in the future regarding the CAT modeling, earthquake risk and loss modeling. And then I will first make some comments, then I will give the floor to our dear panelist members to introduce themselves, their company, and if they have an introduction, that's fine with me. And during my short presentations, I will have some provocative statements as well, so I would appreciate if you take them lightly and respond to them as well. Well, one thing about this whole conference, presentations, and the panel session, everything that's lacking what's lacking is the gender balance. That's very important for in EU terms, and in that regard, we are glad to have Helen among the presenters, at least to give some gender balance. But apart from that, it's all males. And that's unfortunately the case with the panel as well. I hope that's not the case with the rest of the insurance industry. Let me have my first slide here. That's not my first slide. That's Louis' slide. Well, anyway, we heard all from so far we heard from the academicians, engineers, and experts on loss models. And now it's the time to hear from the vendors, from the brokers, and the reinsurers that actually operate professionally. And then I'm sure that their contribution will be great to the success of this whole session, as well as to what waits us in the future as well. I'm still waiting for my first slide, but there's something wrong probably. I guess as it gets late, we are having to have more problems. Yeah, okay. That's the panel session in very simple terms, and then what we have is well, as the choice of the CAT models, we have the main vendors. The ones that I know is the RMS, AIR, and EQE. AIR is here. RMS is not, well, I think they were invited, but there's some problem with their participation. Then we have the reinsurance company models, and then broker models, and we have Guy Carpenter here as a reinsurance broker. Then there are insurance company modules, and there's also open source models, such as the GEM OpenQuake. The words that underneath, I have actually adapted them from Julian Balmer. What it says, the earthquake loss modeling is now an established area of research. It may, in many groups in research, institutes and universities engaged in the needs of the insurance and reinsurance industries have been met mainly by well-known companies specializing in the CAT modeling, and that's I guess the first three, the main vendors. The ability of the user community to own the code enables much more rapid development, the spotting and removal of bugs, and ultimately produce a better software. And that, I think, proved itself with the development of the OpenQuake. The main benefits associated with open source models are, first, advancing the state-of-the-art of the CAT risk modeling, and second, improved information sharing, and such as the case with the OpenQuake. I think that statement, although it's been stated about probably 6, 7 years ago, is still valid today. What I have is some slides here that I'm sure you can see it. I'm not going to see the vendor model 1 and 2 and 3, and there's the local model. This is the AAL assessments for Turkey based on sub-districts. I don't want to go to the numbers. The distribution of the colors show that there are striking differences between those things, and that's one of the main facets that essentially that there are differences, but we don't know the reasons for those differences. And the reason is that we don't have any means of assessing how they've been assessed, how have they been computed, for one thing. The second thing appears also for Istanbul as well. I've shown 2 vendor models. I'm not going to name them again. There's no need for that. And there's a local model on the right-hand side. Again, we can see some differences in the AL ratios as well as the distribution of their colors. This is the even more striking one. Those are the modeled losses for a given return period. Again, there are 4 vendor models here, and then we can see that they differ a lot, especially for large return periods. I mean, that for some other parts of the world that may be valid, but for Istanbul, I think, or in fact for Turkey, regarding the hazards, more is known than the other parts of the world, and such big differences are really disturbing. And then it is also difficult for the receiving agency, in this case TCIP, how to manage them. Essentially what they do, they try to choose the lowest one and then try to negotiate with the reinsurer whether they accept it or not. But that shouldn't be the way. I think there should be some more scientific ways of comparing them and taking their average or taking their weighted average, whatever comes to my mind. But I'm looking at things as an academician, not as a practitioner or a professional. So we have the panelists here. Mr. Luis Souza, that's the Senior Research Associate from AIR, one of the leading vendors. And then we have Matthew Eagle from Guy Carpenter. He's the head of the Global Model Solution Advisory. Guy Carpenter is the leading, probably, reinsurance broker of the world. And we have 2 of the largest reinsurance companies of the world. One of them is the Munich Re, the other one is Swiss Re. Munich Re is represented by Professor Martin Kezer. He's the senior consultant in the geophysical risk unit and earthquake expert. And from Swiss Re, we have Nicholas Georgi. He's the director, head property threat underwriting South Europe, Middle East, and Africa. So what I will do now, I would like to hear from all of you, of you, just to introduce yourself, what you do, introduce your company, and if you have some slides to share with us, we'll be happy to hear them. And in the meantime, if you can answer some of the issues that I have raised, I'll be more than happy, but then maybe we'll go for more questions and discussions, and then hopefully we'll have an excellent panel session. Thank you for the time being.
Thank you.
Yeah, go ahead, please. Bu arkadaşın şeyini alalım, deminki ilk koyduğunuzu.
Good afternoon, everyone. Thanks for the introduction. Thanks for sticking till the end. And thanks for the opportunity to be here and contribute to the panel and to this workshop. I think it's a great opportunity to just bridge the gap between industry and academia. And I'll try to contribute to that with a short presentation. First of all, my name is Luis Souza. I'm a senior research associate at AIR worldwide in London. As I believe everybody knows, AIR is a CAT model vendor. We serve more than 400 institutions in corporate, insurance, reinsurance, government fields. And for today's presentation, I tried to essentially wrap up the day with a bit of context of what CAT models can actually provide in terms of information. I mean, in the morning, there were amazing presentations about advances in research, and this is more to show you how that research is sort of packaged into a way that can be used in mainly insurance and reinsurance. So in the context of today's topic, I decided to give you a brief overview of different insurance funds throughout the world. Of course, I'll include TCIP here as well, and I'll show you in a couple of slides what I mean by that. But before, I'll give you just a brief introduction about the 4 examples that I'm going to talk about today. The first one is, of course, TCIP. The second one is the Earthquake Commission in New Zealand, or EQC. The third one is the insurance program against natural disasters, or insurance pool, sorry, against natural disasters in Romania. And the final one is the Taiwan Residential Earthquake Insurance Fund. So TCIP, I will not describe in any detail because we had several presentations about it, and I wouldn't be qualified to do so in any case. But I'll give just a couple of words about each of the other 3 examples. EQC, I believe, is fairly well known. It started in 1945, at the time was the Earthquake and War Commission, War Damage Commission. Then in 1993, it was reincorporated as EQC and now manages the earthquake insurance program in the country. Similarly, PAID is a similar sort of fund or program. It actually started much more recently in 2009 as through the effort of 12 insurance companies. And again, since then, manages the local mandatory residential insurance system. And in terms of penetration, it reaches around 20% of the total residential portfolio. And finally, we have the Taiwan example, which is very similar to the others. And in common to EQC, they have an interesting fact, which is the way they actually provide this coverage, which is by automatically providing earthquake insurance to all policies that are covered for fire. And in terms of penetration, we're talking about 30% since 2018, I believe. In this table, I'm summarizing essentially the key takeaways in terms of policy conditions. They all cover building damage. EQC also covers land damage. And the Taiwan example covers also contents and living expenses. In terms of perils, they all, of course, cover earthquake shake. And then they have different combinations for all of them except the Taiwan example, which only covers shake. And then in terms of deductibles, TCIP has a 2% deductible. The EQC and the Romanian case both cover first loss, meaning that there's no deductible. And finally, the Taiwanese example is kind of a peculiar one because there's essentially no deductible, but there's also no coverage if the damage ratio is below 50%, meaning if the cost to repair is lower than 50% of cost to replace, then there's no coverage provided. If it is above 50%, then there is a coverage provided up to the limit that I'm showing on the third to last column. The limits, they vary per country, of course, and I'm not going to compare them here. I'll try to give you a bit more context when I'll show you the results of the analysis we ran to show you today. And before I actually show you the results, I'm going to explain exactly what we've done. So we've done our catastrophe models, in this case earthquake models, for these 4 countries on our residential exposure database and produced loss exceedance curves for what we call the gross loss, in this case the loss that is covered by each of these insurance funds or insurance programs versus the total loss or the insurable loss. In terms of perils, in order to be consistent, because you see here that they actually insure different perils, we used the only common one, which is earthquake shake, and we considered also only damage to buildings, what in insurance terms it's known as coverage A. And finally, we use these results to compute this ratio, which I'm going to show in the next slide, which is the ratio of loss to the pool with respect to the total loss, so the insurable loss for a given return period. I hope that's clear enough to everyone. And just a final topic I want to highlight is that we used or consider only the part of the exposure that is insured. So I'm not including this analysis essentially the percentage of the residential portfolio that is not insured. So only the part that already has access to each of these insurance schemes. So this is the first plot I'll show you, and actually what I'll show you now till my last slide are iterations of this plot. And what we show on the horizontal axis are the return periods of exceedance of the different losses from 1 year to, in this case, 10,000 years. On the vertical axis, we have, I should actually have a pointer here, no? Oh, there you have. On the vertical axis, we have the ratio I was talking about, so loss to the pool versus total loss. And The first thing that you probably have already noticed is that for Turkey, or TCIP, and I actually forgot to mention that, for Turkey, the results are shown in red, for New Zealand in blue, Romania is yellowish, and Taiwan in green. So now I actually sort of grayed out this, all of them except for Turkey to focus on this. And you can see that the ratio is almost 100%. And that has to do with the policy conditions, at least according to the information we have in our industry exposure database. We tend to see that the total insured loss tends not to exceed the limits, and that's why the pool is enough to overcome most, or at least bear most of the loss. In the case of New Zealand and Taiwan, I'm showing them in the same slide because they're sort of symmetric, and I'll try to explain why. So we see that for New Zealand, for frequent and smaller losses, there's almost 100% coverage, and that's because there's no deductible. So it will take first loss. That's why for smaller losses and more frequent events, the loss to the pool is almost 100%, meaning that most of the loss is covered by the pool itself. The Taiwan example is on the opposite side of the spectrum. So there's actually no coverage below 50% damage ratio. So for low losses and more frequent losses, most of the loss is not taken by the insurance pool, which is why you see this opposite effect. But then as the return period increases and the losses increase with it, then we start seeing a reduction on the contribution of the pool in New Zealand, and that's because losses are increasing, so they are progressively exceeding the limits. That's why the contribution to the pool starts to decrease. And in the opposite direction, we have the case of Taiwan. Now we have exactly the opposite case. So now losses start to exceed the threshold of 50% damage ratio, so the pool starts to take in a good percentage of the loss. And finally, this is just my last slide. I'm just going to talk very briefly about the case of Romania. It's very similar to New Zealand, again, for the same reason. It has no deductible, so it will take first loss, which means that, again, for a return period till, let's say, more or less around 10 years, it'll take almost 100% of the loss. As the return period increases and losses increase, then the limit starts to be exceeded. So, of course, the contribution or the portion of the loss that is actually accounted for by the pool starts to decrease, and in this case actually stabilizes around, let's say, 60% of, again, this is loss that is taken by the pool versus the total loss to the portfolio. And this is actually my last slide. I hope this was informative to everyone, and if there's any questions, I'm happy to answer.
Good afternoon. I've got the microphone. We decided that you've had a lot of slides coming at you today, so in the rest of the panel discussion, we're just going to sit in our comfortable chairs and make some points on the day's proceedings and try and get to some of the questions and discussion that Ms. Erdek has alluded to. I'm Matthew Eagle. I look after global model solutions at Advisory at Guy Carpenter's, really all of our catastrophe risk advisory services, building models, evaluating models. I've been in reinsurance analytics and cat modeling for about 25 years and had a long-standing history with the Turkish market. I think my first sort of observation on today is certainly a commend this, the huge amount of research that's going on within the local academic research community and also more broadly from the number of the other research groups we've heard from. And what's encouraging is that we bring ourselves closer together in terms of the way academic institutions look at understanding risk and the way we have to translate that into the financial and insurance world. For example, things like consequence functions. Before we'd access research, one would end at fragility curves and damage states. Now we talk about how do we translate that to functions. And also when you look at seismologists would talk about probabilistic seismic hazard assessment at individual locations, worried about building design. And we have to think about how do we model portfolios of risk, how do we handle the footprints, the correlation of damage that people were talking about earlier on this morning. So I think we've come a long way to sort of bridge that gap, and I think we can start to feel the benefits of that with some of the work that DASK and TCIP are supporting. I think we look for more agility in the way we can incorporate some of this in the models, and this is a bit of a trade-off. Some of the models we use, in our opinion, we'd say are now out of date, that if you look at the US hurricane, they get updated every couple of years. Some of the other bigger models every 3 or 4 years, but some of the others maybe only every 5 to 10 years, and over time they become dated. How do we incorporate new views of risk like the latest hazard maps into models before we wait for vendors to do that themselves? But there's a trade-off, because the reinsurance market, insurance market also requires some kind of stability, if you like, reference view in how often we look at that. I think probably one of the biggest failings of our community is dealing with and communicating around uncertainty. We heard a lot about that this morning. And I think, the scenario modeling and certainly bringing it back away from an overdependence on loss exceedance curves is going to help us, hopefully, in that regard. I think computing power is certainly helping in terms of being able to tackle things like modeling and capturing some of the uncertainties. Paolo, I think, who's had to leave, talked a lot about the aftershock sequences. That was a trade-off between run times of models and how many events you could effectively capture, whether you do 10,000 or 50,000, 100,000, and within those years, how many events you capture. Now, with enhanced computing power, we potentially have the ability to do a better job at capturing that. So I think, that's certainly helping. But, Mustafa, when you looked at the difference in the curves, and we get it, that's the challenge we have, and increasingly we want to try and understand those differences. But, if I was the audience, if we had a magnitude 7.4 on the Princess Island segment fault, and that's all new, but you had some information about building stock, you had access to the research you're doing and the OpenQuake stuff on fragility curves and design codes, what range of estimates would we get for what you think the actual economic insurance loss? And I think you'd get someone say 50 billion, someone else would say 30, someone else say 70. So already in there, you've got a loss estimate plus or minus, 20, 30, 40%, just from one event, and asking people to translate that into loss. So I think this morning we alluded to the number of aspects that do that, and what we try and do with the modeling is capture that uncertainty, but we do kind of end up with the best estimate. And I guess that's, when we look at how we then translate it to our insurance world, just remembering what it is we use models for. There's certain people building models have a responsibility to government to protect society, for example, having to take a certain view on what that extreme risk might look like. When you're pricing original policies insurance, or when you're trading with reinsurance partners, reinsurance, what we're trying to aim at is what we call a fair view of risk, that it's a view of risk on which we can all agree there's uncertainty, but we're trying to arrive at a view of risk that we're happy to trade on each side of the equation. So, we have to, in the end, bring all this uncertainty down some numbers that we can actually make the business decisions on. And, that's when we start looking at all the science that goes to the model, but what's some of the final outputs? If I can phrase this correctly and maybe ask my colleagues here, we talked about return period and exceedance probability, but let's talk about a 2-year return period. What's the loss amount in euros or in Turkish lira, the loss amount in euros that you think the total Turkish insurance market should see a loss of that size or more every 2 years? So, once on average, every 2 years, we should see a loss of X amount or more. Any guesses in the audience of what sort of size number insurance, and take the insurance as maybe, I don't know, half of the economic loss in Turkey. Well, I'll jump to it then, because in the interest of time. The vendor models we use suggest that the Turkish insurance market should exceed a loss of 70 million euros, about 500 million Turkish lira, on average once every 2 years. And since 1999, I would say Van, if you inflate it to today's money, close. The recent earthquake we've had, probably not quite there. Nothing else in that 20-year history. So something's gone haywire, in our view, in the calibration of, and yes, it's most important to focus, capital's at risk and solvency of companies and protection of life. We do need to focus on what's going to happen with the 7.4s or the 7.5s in Marmara. But when we're trying to trade risk, we also need to have a view on the right shape of curve for all the layers of the reinsurance program. And I think there's a discrepancy. I mean, the models will say we're going to get 1 billion euros once every 10 years. 400 million euros every 5 years, and I'm not sure that, you know, that. So what we do at Guy Company, we do what we call model suitability analysis. We'll compare components of the models against reference data in the science. You know, we are an advisory member of GEM. We have access to all of the GEM work in OpenQuake. We're starting to do the work on the latest seismic hazard map, but we've worked with Candeli before and reference against Share and some of Gruntal's work, where we compared zone by zone the frequency and severity of the vendor model of different magnitudes against these reference data sets. And we found clear discrepancies, and we ended up developing, as I say, rather than waiting for the vendors to change models, we developed an adjustment of our own to those models that we applied within the market. You talked about open source modeling. Just to say, we are a big supporter. We see a lot of value. We've been a founding member of Oasis. It's the platform we're using for all of our models going forward. It's a convenience because we can put our models on there, but we can also consume third-party models on the same platform, and that makes our life much more efficient. So we certainly are active in that space and do see value in that going forward. I'll stop there in the interest of time.
Thank you.
So my name is Martin Käser. I'm working at Munich Re since 2011 and basically responsible for our in-house earthquake models. I'm a geophysicist by education, and I spent basically now almost 20 years in earthquake modeling. So the first 10 years in academic research, doing basically ground motion modeling with more or less complicated 3D numerical algorithms. Then when I changed to Munich Re, I became basically a probabilistic seismic hazard modeler. And by now, as I said, basically responsible for the entire risk modeling in the company. And what I would take from these last 2 days here is that, and that basically was also in line with my personal opinion so far, that we definitely have to do still a lot of work in the vulnerability assessment. Maybe I'm biased in the sense that I'm coming from seismology, so I, by default, maybe feel more comfortable with the hazard part, so I have the feeling that this is what I have more under control, and definitely there is much more information around where you could calibrate your hazard model. There are projects like GEM that at least give you a handle or give you almost like a reference, I would say, what is potentially the right view of hazard, because there are so many international researchers working on this issue that we try with our in-house models to be as close as possible. We basically start from the same data that GEM is providing, but as we have our in-house modeling code, of course there will be differences in the hazard. But then once it comes to the vulnerability assessment and the transfer from hazard to risk, it becomes much more difficult. And my personal opinion is that what I've seen yesterday and what we have seen today, there's a big problem in the sense that even though there are many people working on this issue in the academic world, I have my doubts that we will get very close to what we need in the insurance industry. Because the problem is that people in the academic world, they don't have access to the actual portfolios that are insured, and they don't have access to the actual losses that occurred. And the second part is a really difficult one, because even as a reinsurer and maybe as a vendor or as a broker who has his own models, you might agree, it's difficult to get usable loss data. Unfortunately, Paolo Bazzuro, who gave a talk this morning, already left, but you might remember one of his slides that he showed where he said, we got this earthquake loss data, I think it was from the Loma Prieta earthquake, and he said it's ugly data. And the problem is that even if it's ugly data, we need to work on it, and this ugly data is basically not arriving at the academic world. And therefore, lots of energy which is spent in the academic world, in my opinion, is basically working on vulnerability estimations that might be useful, what we've seen in the talk by Helen, to get maybe an estimate of general economic losses, ground-up losses. But this is not really what is needed, I think, in the insurance world. We would have to work on the real loss data, which has to have a certain quality, let's say, in the sense of geographical resolution, but then also what is extremely important as well, and maybe not at all known in the academic world, is the financial terms that basically go on top of these losses. Because sometimes it happens that we have a client that provides us extremely detailed data after an event, but then it's unclear how much of the financial terms have already interacted with this data. So he might have certain types of deductibles, which means TSI deductibles, it might be loss deductibles. There's all sorts of deductibles and limits. Then you have an interplay of location financial terms. They go up to a policy level. Then there's several policies grouped into an account. And you have, in theory, it's not difficult math. It's just subtractions and taking minimum and maximum of certain numbers. But their interplay makes the thing complex. And that's what I just can repeat. That's something that will never reach the academic world. And we had, we tried to set up projects between academia and Munich Re to actually work on these issues. But in basically all of the cases that I'm aware of, it was turned down by our clients due to data confidentiality. And so I have little hope that this will improve soon, but I think this is really the point where we have to put our energy in. Because otherwise, I have my doubts that the vulnerability estimation is getting that much better. It's really, in my personal opinion, it's pretty much focused on empirical methods to get the vulnerabilities right. And another point that I want to mention that was already mentioned by Matthew. We have seen that there's so much uncertainty in the entire modeling process, starting from incomplete data, going through the hazard uncertainties, then coming to the vulnerability, that we definitely have to put much more effort in so-called sensitivity analysis. And I remember, I think 2 years ago, I was invited by Guy Carpenter to London, and I think it's called the Method Sensibility Analysis Project that you were working or still working on. And I think this is exactly the way we have to go. It means it's a lot of tedious work and try to systematically figure out how particular parameters will influence our loss frequency results. And as you already mentioned as well, is that with the computational power that we have available at the moment, I think this is doable, but it requires a lot of effort. And at the end, the target must be that we will not reduce really the uncertainties, but we will at least find out what are the main drivers of uncertainty, and then maybe give a range of possible solutions. And what you've just showed, the 4 loss frequency curves of 4 different vendor models, nobody wants to be the outlier. So that's what we also do. We compare our model results with vendor model results. And if we would be far off because we maybe produced an earthquake risk model from scratch, then you don't, well, you feel uneasy, let's put it that way. And so you're trying to figure out why are we so different from the others, if the others are close to each other. That's also not always the case. So that's why I think this sensitivity analysis work is really definitely something that we have to work on. And then we have to communicate not only maybe to our underwriters that at the end have to do the business, but also maybe directly to the clients where these uncertainties come in, what are the potential ranges, and why at the end we believe that this is, let's say, a fair or risk adequate view of risk that we are presenting them. And maybe as a very last point, we just started a cooperation with one of our clients where we actually develop a completely new earthquake model from scratch. And it's basically a pool as well, I would say. And so we started cooperating with this client from the very beginning, putting basically the cards very openly on the table. And that makes, at the end, also the underwriting process much more easy, because the client was involved from the beginning, knows where the critical points are, and we try to explain why we put some of our assumptions into the model. So I think that's maybe the right way of going in the future. That's, at least for the moment, everything I wanted to say.
Please. Thank you. Here I will be the voice a little bit of the user. And I'm an underwriter. I work for Swiss Re. I'm responsible for South Europe, Middle East, and Africa for the property treaty. And what I see over the last 2 days is impressive and scary. It's how much we don't know, how much the unknown compared to the known. And I'm the consumer of these models, and at the end, I commit shareholder money to this business. And that is, it can be scary when you spend 2 days and you see that, in fact, we don't know. So it's important that we use all model, all view, but it's also very important to know what are the limitations of all these models. Because at the end, and it was one of the presentation, in Swiss Re, we aim to make the world more resilient. So to be able to have this fast flow of money post-event, you need reinsurance. Insurance will not be by the nature of just being in one country. You need to spread the risk. You need to have a global partner to do that. And a country cannot be also that risk. So again, you need a global perspective and sharing the risk. And to be able to do that, we need, and I will look a little bit more a financial guy than I am, you need to bring capital to it. And one thing that capital doesn't like too much is uncertainty. Or they bear uncertainty as long as the return is higher than what you get without risk. So, and here as a user, it's really important that I understand the gaps and I understand my decision based on these gaps. It can be the input data, as it was mentioned. It can be all other differences. And at Swiss Re, we also have our own model. And if you speak to the modeler, they will call me as a difficult person because I'm the first one to challenge. I will challenge model, but we accept challenge, and we accept challenge from other model. I think it's important, as you mentioned also, is why are we so cheap? Why are we so expensive? It can go both ways. And it's a challenge, and more information we know. And I think now I work as an underwriter for about 20 years, and I work across the globe. It's impressive when something happens, how we discover how much we didn't know. I think there is non-event, a large event that we didn't discover something we didn't know at the time of the event. So it's an ongoing process, and hopefully we will bridge the gap of the uncertainty. But at the end, I think, as my colleague just said before, there will still remain large uncertainty because the model, the physical model, is only one part of the equation.
Well, thank you. As I understand from the discussions is that obviously there's the difference between different models acknowledged. The reason, part of the reason is uncertainty, which is well known, but the other reason, as Professor Kezer put down, is the difference in the vulnerabilities, that you have to work more But then again, what I cannot understand, say in the case of Turkey, there is the Kocaeli earthquake, last earthquake. The models can always be verified against that. I'm sure that those models are verified and still those differences exist, which is fine, but then the client is in a position to choose one of them. Obviously, he can consult with the broker, but then again, there is really not much to do. I mean, whether you take the average, you choose this one or that one, and then what are the, from the broker side, I mean, what are the suggestions that you give to the client as to which one to choose? Because, I mean, not going to the reasons of that difference, it's difficult to make a choice.
Yeah, I mean, and that's what we use our model suitability analysis to try and help us dig into is what's really, there's uncertainty, there are differences, trying to understand what's driving those differences. If you through the analysis you feel you've got a reason for seeing a miscalibration or an anomaly in one model, you may gravitate to the other, but you may equally end up with what you believe are two credible models. You know, if you look at the science they've employed, if you look at the people behind those, there may be two credible models, but they differ by a certain percentage. And you know, in the old days, I think I come as a statistical background, you think, why not just blend models and things? I think the regulatory environment, particularly in Europe and Solvency II, the amount of emphasis they put on people to really understand the model they're using and the amount of validation they had to do, actually what's happened is people have gravitated towards a single model that they really think they understand, and then, you know, using the other models as a reference. There's a few differences to that, but we are trying to do that. But you know, where I would say is uncertainty. You know, when you say capital doesn't like uncertainty, I mean, if we had no uncertainty, we wouldn't need the capital. In a way, we'd have no downside. So, in a way, uncertainty really creates opportunity, and it's really understanding whether you think you're being compensated enough, you're getting a good enough return on the risk you're taking to, you know, underwrite that uncertainty. But I think we clearly have a lot of areas of, you know, things more unknowns than knowns. But I think we should be absolutely honest with ourselves about those uncertainties, unknowns. But we should embrace it in the sense that it creates opportunity. And I think, you know, the onus is on us to try and understand those differences and tail risk the challenges out there. And then, you know, in the end, we broke on behalf of our clients, to my two colleagues on the left. We're trying to come up with a situation where our clients can decide what risk to retain and what risk it's beneficial for them to spread that to a global reinsurance market, with the view that ideally that global reinsurer is also getting an adequate return on the capital they're putting up. But yeah, you've got to get down to what is really driving the differences in the models. Are there some major reasons that you disagree with, or, you know, are there some credibility but some uncertainty that's reflected in that range?
Well, thank you. Just out of curiosity, do such differences exist in hurricane models, or they are intrinsic to earthquake?
I think the one thing you have in hurricane models and flood is you do have more claims data to some extent. You know, you haven't always had the regularity of, so you know, the data you're using in some of your work is from fairly small size earthquakes. You know, a lot of the population wasn't insured back in 1999. You can't draw on that much claims data. Whereas with hurricane and some of the wind, you do get access to more data. Certainly in very highly regulated markets like Florida for US hurricane, there's, as you say, you look at other models, you know, there's some sense that people gravitate together. I don't know, I can't remember the differences in US hurricane models from the major vendors, but it's probably of the magnitude of 10-20% at, let's say, 100-year or 200 years. So there are still significant differences.
So, but less than the earthquakes.
But probably less than earthquake in the tail.
I think the big difference is that in other perils like flood or wind, I mean, due to the fact that they have just a much higher occurrence frequency, I mean, you can basically validate your loss frequency. You can basically validate your loss frequency curve in the frequency range much better. So it would be, I mean, as the example that you gave at the beginning, that we would see, or we should see a certain damage every 2 years in Turkey that we don't see. Yeah. I mean, that's an obvious fact that maybe your model is highly overestimating the risk at the moment.
Well, the high frequency.
Well,
Exactly.
It doesn't mean on the
exactly.
Provided that our buildings didn't get any better, you know. That's
But I mean, at least that's the big advantage of the other pairs, because they have a much higher occurrence frequency. So in earthquake, we will, in my opinion, we will not get around that problem of having the uncertainties, and that's why, I mean, I'm thinking really more in long terms. I mean, you mentioned also ACES. I mean, they tried to establish a platform where things, let's say, are getting unified. I mean, they also... Okay. So I have to repeat everything that I said. No, I was just mentioning also the OASIS platform. So that was an effort where the insurance industry is trying to unify at least parts of the risk modeling workflow. And they also created something like their own exposure data standard, so the OED, which is something that also Munich Re basically now adapted. So we are trying to, or we are basically transforming all our client data into this, what is it standing for? Open exposure data format, exactly. Because that's also, let's say, has an influence on the uncertainty, because depending on from which client and for which particular vendor model you get the exposure, there might be already differences because the formats are different. And in my opinion, it would be great to introduce something like this also in the future for loss data, because this is much more messy, as we heard today, the so-called ugly data. So if we would be able to organize also getting this loss data, even if it's very infrequent in the earthquake case, but we could start maybe with flood or wind, getting such a kind of standard for loss data, in the long run, I'm sure we would reduce the uncertainty, at least in the high frequency range. I mean, the high return period range, that will remain uncertain for quite a while, I guess.
Thank you. Well, Matthew actually asked the question as to what would be the expected losses for Turkey in the next 2 years. That's difficult for Turkey, but for Istanbul, it's not that difficult, because we know that the quote-unquote Istanbul earthquake has a probability of 2–3% per year. So you compute the losses and take it 2.5%. That should be the annual losses in that case. Anyway, now the floor is open for questions from the audience. I have other questions, but we would like to hear from you as well. No, there's a mic coming.
Thank you again. A very interesting session, and I have a comment and then a request, because we are on different. So the comment is when you were discussing about vulnerability, Mark, right? Totally agree. I had the experience in New Zealand to be able, after the earthquake, to sign up a very special agreement with an insurer for comparing and checking our loss calculation with the quote for repairing for a few hundred buildings in the CBD. After a while, someone from the high level, I received an email saying that the higher power to be are very concerned about leakage of information. And the agreement was we would have sent a squad to their own computer to work on their own computer. So this is a huge issue. Solution, because I totally agree, we need it, you need it. If you can unstrip the confidentiality and making these buildings becoming skeleton, we have done an exercise with Marco Di Ludovico, which is actually published in Earthquake Spectra, where we were taking 4 case study real buildings in L'Aquila, of which we knew everything. Of course, we did not mention who they were. Of course, we did not mention where they were specifically located. And yet, we presented the building case study, and we checked the best modeling, the best losses, and my gosh, the scatter was significant on the single building. If we could match in tune on single case studies, that would be fantastic. So, suggestion from your side. Could you get together few hundreds or few examples for case study classifications, taxonomy, that are naked, and so there will be no confidentiality issues, and provide some information? University will be very happy to work on a project on that. And then I have 2 things which are the other conveners were suggesting. One is, have you thought about adjusting the premiums, you know where I'm going, based on retrofit. What does it mean? You're concerned about uncertainties, we are. The more we improve the bad guys, the less uncertainty we have. You have an incentive to go for less uncertainties, we have an incentive to do it, the community have it. So could you please make a very tangible and explicit effort in showing us such an advantage in premium reduction so that there will be a way from the government for the private person to top up and see why the advantage of my own top-up to enter in that business, I will be reducing my uncertainties, you will be reducing the uncertainties, you are going to make more money, okay? Everyone will be making more money because the government will not be able, in Turkey or everywhere else, to sustain a war effort after the disaster to try to do everything else. So the question is, have you thought about an adjusting premium based on retrofit? And then you were discussing, Erdik, you were saying, how can I choose as a user from different portfolios? Totally agree. So the thing is, do you have, which I can buy, a tailor-made insurance premium? I'm a big guy. I think my house is the most important of for whatever. I want to have a tailor-made insurance premium for my house, which is basically, from a structural engineering point of view, is to do a very refined calculation with a very refined, tuned, calibrated loss modeling approach. So can you provide a tailor-based insurance premium? One is adjusted premium based on retrofit, and the other one is tailor-based. Single building, single owner, single building, not assets, single building based.
Perhaps just on the very tailor-made insurance price. I will perhaps go a little bit outside earthquake, but take the flood. I can, even if we could make an insurance price tailor-made to the risk of the exact house, it will become non-affordable because the person who will buy is the one who has the risk. If I'm living on the 5th floor, I don't want a flood insurance. So, of course, you can think it's perfect to have the exact price, but then you end up with having insurance that's become non-affordable.
Stay with me. Emilia earthquake 2012, precast industrial buildings with Parmesan Reggiane inside or other things. These required a tailor-made which was not made because the content cost for that precast concrete buildings is very clear for me. The logistic of an Amazon buildings is very clearly different from another, while the insurer were just looking at precast buildings, concrete. So completely different business schemes. So I agree. House in a flood, but we are talking about earthquake. I'm talking about earthquake is what I know. Yeah. And so there are very specific business plan which includes the downtime. New Zealand went in trouble because there was a 1 year only coverage for downtime. 1 year was not enough. The cordon stayed there much more. If people had known, had thought about it, then they would be adjusting themselves in a higher downtime recoverage business-wise rather than whatever, some other deductible. So the suggestion is, let's discuss on a case by case because there will be option where, as you're right, there will be no absolutely opportunity to do a tailor-based. That would be nonsense. But other where would be absolutely feasible.
So maybe also one comment to the first part of your statement concerning the loss data from the insurance industry. I mean, it sounds like we went through the same experience because we also tried to anonymize the data, modify it to a certain extent so that we still can use it, but it's definitely not the exact data that we receive, that we at the end didn't receive, or we were not able to use it for cooperation with the university, let's say. So at the moment I have to disappoint you, so we don't have data that we could commonly work on. But, I mean, I'm absolutely with you, we shouldn't give up. I mean, there have been situations where we maybe talked to the right people or from the client side, and then just basically on the day where we actually wanted to start the project, there was the no coming basically from higher management. So that's also maybe an issue that people that, you know, have to do that decision, they might not maybe be aware of the importance of working on such data sets for the future. But this is the current situation, I would say, and it's really difficult to get such projects going.
I think just one other comment on the difference of your bespoke thing. We have to remember personal lines or residential and commercial industrial, because I think in the commercial industrial space, that kind of bespoke modeling and risk underwriting is happening. I mean, there are large global insurance companies that for risks over a certain amount, they will put them through CAT models and do lots of surveys, if you like, to gather all that detailed data and try and do their best job, even given the uncertainties to do that. But on homeowners, there's a flip side, which is people, the premiums, the size of premiums, so people are more worried about operational cost and expense ratios. And increasingly, I mean, Helen was talking a lot about the data, and I know that's in a way more to help us on the big picture, but ultimately where it's heading is, at the moment, it's quite expensive to get third-party data, but with some of these satellite and artificial intelligence initiatives going on, ultimately there are people, insurance companies writing policies where they only ask for 5 simple questions, and all the other information about the risk of the home that they're insuring comes from some third-party data source. So you'd like to make it bespoke, but actually, they're looking for ways to try and automate it, if you like, or make that more efficient to do in underwriting.
Okay.
And sorry, there are companies that, by internally, in their capital allocation to their subsidiaries, apply data load. So, if a certain subsidiary's data quality is not great, they actually get a load on their PML, and therefore a slightly higher capital allocation. I know that's internal within the company, but that sort of concept, which is what you were sort of looking at, the benefit of if we provide better data, could we get an adjusted premium? It kind of happens implicitly within some of these large companies.
Yes.
Two-part question. I looked at the curves that Professor Ardik shown us at the beginning, damage versus return periods. It looked like, to me, quite similar to the trajectory of a space rocket, so a little bit scary. And what we don't see is if we magnify the lower parts of the curves, they indicate, most of them indicate quite high losses for return periods such as beginning with 5 years, 10, 20. Now we have seismograms in Istanbul installed since the last 100 years at least, I think, if I'm not mistaken. And we don't also observe, personally don't observe these destructive, frequent earthquakes. So we know some brokers are working on adjusted curves. I think Matthew's company also invested in such a project. Why aren't these corrected? And also one of the I think the blue one, Company Blue's curve was more in line with what our own experience here. So for us, they should have looked more like an S curve rather than this steep rise. This is the first part of the question. The second part is related to the top end. There, of course, we don't have observations for thousands of years of return periods, but we have very old buildings in Istanbul. St. Sophia being one, built 4th century after Christ, Common Era. So that withstood many earthquakes during its lifetime. Yes, we have seen also pictures shown to us by Professor Scouthorn that it was also damaged, but it wasn't demolished completely. So can we put an upper cap also to the magnitude? Are there such paleoseismological studies that rules out a magnitude 8 earthquake within 50 kilometers of radius from St. Sophia, or 500 years return period from Blue Mosque or Istanbul's walls, etc. Is it possible? Is it done? Thank you.
Well, let me answer a question regarding the Hagia Sophia. Hagia Sophia has seen major earthquakes and has seen major damage. the dome was totally destroyed in the 5th century, then partly destroyed in the 10th and 14th centuries, and rebuilt totally. And then all the abutments about the building were built there just to hold it together. So, I mean, it doesn't mean that it hasn't suffered any damage. It has suffered great damage from earthquakes.
But not total loss.
Well, I mean, yeah, I mean, if the dome goes, that's a total loss. And that's a building that's essentially built by Justinian with huge amounts of money, with such good quality bricks and everything, that the bricks that are used in the dome can float on the water. So lightweight, so well constructed, because the builders had their necks, essentially, if they cannot build something correctly. But that's out of discussion. But Hagia Sophia is good because we can see trace of the earthquakes of, it's well defined. But from the response of Hagia Sophia to the earthquakes, we cannot go anywhere. Yeah. Now, please.
I was just commenting on your last part of the question. Can we rule out, if I understood it correctly, can we rule out the magnitude 8 earthquake affecting Istanbul?
As an example, can we put an upper cap to it by looking at the currently standing monuments? Because they withstood to so many earthquakes during their lifetimes.
Well, most of them collapsed. In fact, the ones that you see around are the ones that are really well built. I mean, if you just look at the ones that are standing around and saying that they were very built, that's fine. But together with the ones that are standing around, there is at least a huge number of that collapsed during earthquakes. We have to look at the whole inventory to answer that question.
Can I just make a comment? Yeah. Again, on the shape of the curves, I mean, we talk about uncertainty and frequency of like very frequent events. I think we still need to perhaps remind ourselves these are exceedance probability curves of losses, not of events. And if we're talking about Turkey and Istanbul, where it's probably more governed by less frequent, bigger events, then we're probably not going to see a loss of whatever it be, 70 million or 100 million every 2 years, but we might see that, let's say, 10 times that in 10 times the time, in time interval, let's say. And that's what we need to contextualize when we're thinking about average annual losses or average 2-year worth of losses. Is it a place governed by very, let's say, moderate magnitude kind of events, 5 to 6 on a even yearly basis, or is it a place where it's governed by larger events on a much larger time span? And that again comes back to the understanding what the EP curves actually give you, and this sometimes confusion of thinking, okay, is this a 2-year event? No, it's a 2-year loss, which needs to be understood on the context of the type of event that can generate a loss that can, on average, be exceeded in 2 years, but we actually may need a period of 50 years to see that average actually materialize. I don't know if I'm making myself understand completely.
At least for the user, yes. Now, but perhaps also on the point on the different curve. They are different, but if you look, and that's what I look also as an underwriter, if you look at the annual expected loss, a lot of models are not too far to each other. If you take just, then is the question how you spread that along the curve. And that is the big difference, I would say, and again, speaking of my work as a reinsurer, as an insurer using model, important to know how much you need to charge annually to recover the potential losses. As a reinsurer, and that is our nature and why we are here for, we're taking the tail of the risk. And of course, a change make a bigger difference. But usually, and even if, I don't know if you did on this 4 curve, if you calculated the annual expected loss for this 4 curve, they might not be that different.
I think, I think we have to remember the 20-year history of catastrophe models within reinsurance. Really, the initial focus was on reinsurance and tail risk. But of course, then you build out these event sets, and then people start using the AALs, average annual loss. We saw some presentations on how one might build that into pricing. And anecdotally, we had a global insurance company insuring commercial industrial around the world, and happen to be an RMS user. I think that in Turkey they'd get a similar result with AR. And they did a calculation where they looked country by country at their premium to AL ratio and tried to identify areas where they should be concerned. And when you look at the numbers in Turkey, the conclusion should have been we should pull out of Turkey because against the average annual loss, we're not getting enough premium. But the underwriters, underwriting the business in Turkey had a different view. They felt this was good business that they were underwriting. They understood the risk things. And, it's back to my point about, it's difficult because we've had use of the models in a certain context. And I know your point about loss, but I do think we are now trying to apply models, for risk pricing at individual level. And therefore, one has to work a bit harder to try and calibrate and, justify the curve across the whole piece.
No, sorry, if I may. No, I do understand that at the end of the day, if you have 50 years worth of data, and if your average annual loss still doesn't match very well, then you certainly have a problem. I mean, I'm not trying. Well, I'm trying to defend the honor a little bit of CAD models because that's my role here. But at the end of the day, I also recognize there's a way to go, and there's still a lot to learn. But that being said, we should also remember that CAD models appeared for a reason, because people realized that using just historical record was not enough. I mean, clearly people started seeing things and events that hadn't happened before, and that's why CAD models came into existence. Now, can we do a better job into understanding what kind of events can happen? I'm going back to the comment of the magnitude 8. Just to give the example of the Tohoku event in New Zealand, it was at the time thought that it was not possible. So it was out of the range even of CAD models and the own models of the institutions in New Zealand. Now, because that happened, we also understand better the type of event that can be generated in California, for instance. So the maximum magnitude was revised there after what happened in Tohoku. So there's always a continuous growth in understanding with, again, going back to your comment. So every time something happens, we learn something new, and we just keep on improving, and that's the way we need to go.
I'm sure you want to move off the bottom of the curve. Just, I don't want to come across, because I've picked up on the bottom of the curve as a model basher. If anything, we've built models, fully understand the challenges, and if anything, I think we get these throwaway phrases that people put out there, all models are wrong, and it's such easy, to have a go, and when we get these live event estimates, I just think, yeah, models are not always correct, but they still have a very strong use within our community, and I think we shouldn't forget that.
Well, for insurance pricing, it's fine, but when it comes to reinsurance, I think for TCIP, the reinsurance is controlled by the so-called quote-unquote Istanbul earthquake and the damage in the Marmara region. Now, wouldn't it be better to give the insurance needs in terms of the distribution of losses if such an earthquake happens, instead of giving it just for 200 years? I mean, 200 years does not have any relevance in this case. I mean, it may be industry practice, but for Istanbul, what is needed that you need reinsurance to cover the costs that would arise from the losses that would arise from the Istanbul earthquake, and you would like to see distribution of that. Is there anything wrong with that? Or still we should continue with the 200 years?
I think there's a lot to be said for what your approach there, but in the end, there's a few rating agencies were one of the first ones to bring in these return periods. They wanted some measure on which to fix capital adequacy of companies, and they chose 250-year for earthquake and 100-year for US hurricane, and that just became a benchmark for stress testing the adequacy. The European Union introduced Solvency II with a 0.5% probability of insolvency or failure, so 1 in 200. These just became, in some ways, arbitrary benchmarks of it's impossible to reinsure yourself or hold enough capital for the worst case scenario out there. So these were sort of reasonable to make it not so unaffordable for the Joe public to buy a policy in the system that companies would have a certain level of solvency requirement, and those 200 years and 250s. And I think we're going to find it hard to move away from that altogether. But as you say, I think we've got lost behind these curves, and we've forgotten what really is what a 1 in 200. And we'd be much more well-informed if we translate that to what are these events that are driving 1 in 100 or 1 in 200 type losses, and do we really understand the uncertainty and distribution of losses around those?
Well, I mean, anyway, I don't want to go into that much discussion on that. That will take us a long time, but I still think that the earthquake hazard in this region is just governed by one fault. There could be several versions of the several scenarios, just one fault. And that fault has characteristic earthquakes. No matter what you do, you cannot change it that much. And then at the end of the day, if you are a company here that are getting yourself prepared for the losses in case of a large earthquake, you should be able to see what would happen if such an earthquake happens. It's not a 200-year earthquake. Okay, any more questions from the audience? Yes, yeah.
So I actually also agree with Professor Kasser. I mean, we have to put more emphasis on the vulnerability part. And as a matter of fact, in seismic hazard, you know, there are very well established regulations. And I mean, if you are really dealing with a very specific, say, industrial facility or a very important structural system, then for seismic hazard, you even can start implementing the shack level process where you have very specific, say, regulations for each shack level. My question is going to be quite general. So we have been discussing about the modeling uncertainties, the differences between the loss curves and stuff like that. So as some representatives of this industry, the insurance, reinsurance industry, do you have plans in the future to come together and bring some standards, at least, I mean, in terms of facilitating the review process or improving the quality of the products, to establish some standards for risk assessment, in particular, for example, the development of fragility functions and so forth? Do you have such kind of platform thought in the near future for risk assessment, just like it's been done for hazard assessment?
So, not to my knowledge that we would really have that plan in the very near future. I mean, it would be a good idea, but I think there's nothing around. And correct me if I'm wrong, but
I think, I mean, the one place people are starting, and it's more, you know, where the areas where it's silly that we're all doing the same thing, and one is in interoperability and data standards. So there's quite a lot going on in the community about trying to take that one away, if you like, so we can. And the reason is the overheads, if you like, to spin up and run lots of different models becomes quite onerous for companies to do. So people end up not looking at multiple views of risk. But if we can get data standards sorted so that we can move much more easily between models, you can bring new vendors. I think. I mean, it's tough for the commercial vendors because, and you can speak for yourself, Lewis, but I mean, there is got to be, at some point, there's some intellectual property in terms of how you've built a model, and if you open it completely up, someone will just replicate it. But, you know, we are moving. I mean, OASIS is not a panacea in itself, but it creates an environment. A lot of the research we've seen today, and people write, you know, you've got OpenQuake and other tools to test a lot of the, and you ran simulations of your own, but OASIS provides an environment that you can start to test these models in a reinsurance and insurance context, and that opens up to new providers, and therefore, you know, a much wider level of scrutiny of how, and some of those new providers don't necessarily have, you know, the same, they may be more open and transparent around some of those assumptions. I think, you know, we've pushed our MSA approach, and I think the vendors' own validation of their models has gone up, you know, hugely over the last 10 years. But it's, in terms of the work they do and what they document and provide to their clients, but they provide it to their clients and not necessarily public. I mean, I'm sure they might choose, but to get that out there in a more of an academic risk validation, I'm not sure we're quite there yet.
As a future, say, I would say, thinking, I know that the insurance industry, reinsurance industry have some sort of confidentiality, which is okay, which is understandable, but to ease the, say, review process or improve the, say, techniques being used for risk assessment, I mean, you may really consider putting some sorts of rules that cannot be that are out of question.
Yeah.
So each one of those modelers should have to implement them. Anyway, thank you.
If I can just respond to that for a second. There are ASTM and ISO standards for risk analysis and for individual site problem maximum loss calculations. And there is one for a portfolio under development. These are being led, the modeling companies and the insurance companies are not in the regulation business. And ASTM standards and ISO standards are typically developed by the professions. And that's who's developing those. But they don't have wide industry support. Matter of fact, these gentlemen probably don't even know about them. But there are some of these things out there.
Thank you.
Especially for PML, especially for Charlie. Yeah.
PML's been around for 10 years.
Yes.
But the portfolio's been in gestation.
Yes, Fuad.
Yes, I wish we had a regulator here to answer this question in terms of, I mean, in Florida they have this group of people that qualify vendors in terms of their model, and they go through the due diligence and they have to respond to a specific set of, standards and questions, and they get, certified every year essentially to go through that process. So it's really the prerogative of the regulators to establish a system if they want to say, we see too much variability into these models. We want something a little more things. Let's look at them in details. Let's open the black box and answer questions. You could do that. I don't know what the position of the regulators are in Turkey. The insurance itself could self-regulate, and say, we want better quality we know a lot. So we want better quality, and you come from the outside, you want to do business here, there are some rules to do business. And so, you can't bag it on the other side. You could take the initiative yourself and say, we want to establish our own standard. I mean, you want to work here, welcome to work here, but we want some quality of work.
If I may, I mean, that already exists. Well, to a degree, maybe not an earthquake, but for instance, like the Florida Commission actually reviews models, and vendor models cannot be used in Florida unless they are approved by the Florida Commission. And the way they evaluate the models is not to say this is better than that one. I think at the end of the day, that's the job or the role of the people that are making business decisions out of those. Their role is to say this seems scientifically sound, and it was used based on all the available information out there in a non-biased way. And that's I think, at least to my understanding, that's the degree to which they go. So, I mean, whereas you think a regulator should go above and beyond that, I'm not the person to answer. But from my perspective, there's already, of course, a lot of validation work that every vendor model, not only AIR, does. And regulators wouldn't necessarily bring anything above that. At least based on this example that I just gave.
In any aspect, you have a consumer, and in this case, if it is a knowledgeable consumer and has a knowledge about something, and it serves the purpose of the general public, and they're saying, well, we want better quality, we want to know better, we want better answers. So
I completely. I'm not against it, by the way. Just to make sure I'm clear, I'm not against that. I think it would be welcome. I'm just saying that potentially wouldn't bring anything above what already is the scrutiny, like the level of scrutiny that is taken.
Why wouldn't it?
Just based on the examples that are out
would
there.
Bring better quality for me.
What is better quality? If I may ask, what is better quality?
I mean, more accuracy, more representation.
Well, you can have a very accuracy. Yes, but sometimes there's accuracy versus precision. Sometimes it's a bit confused, and you can have very, very precise error. So it's all very. I think we start to walk on a very thin line when it gets to this stage. And I definitely would agree that, I mean, more regulation wouldn't be necessarily bad. My point is, it also wouldn't necessarily bring anything above what is already in place.
Well, I'm not talking necessarily about regulation. What I'm talking about is a process for improving knowledge, improving transparency in terms of, you know, I used to work for a modeler for many years, and I know the models very well. But I'm taking another position now just to add to the discussion in terms of, well, should we expect the industry or some representative of the industry to set up some standards for, you know, bringing more confidence into the models in terms of, you know, what they predict, or should we just take, you know, our own because we are knowledgeable and we say, okay, we want this type of quality, we want this type of disclosure into the models. And, if you want to do business here, and you're welcome to do business here, we're not saying you shouldn't. We say it's good for you and it's good for us that we have those standards, and you know, they will improve everybody's understanding and everybody's trust into the process.
That I agree completely. I mean, improving the disclosure for sure. I mean, but drawing a line for what the quality is, I think that will be tricky.
I mean, that's exactly the problem, that there is no definition of what is good and what is bad. I mean, it's difficult to say my model has now a better quality.
Yeah. But how can you stand? So if you have 3 models with 3 different values, how do you say which one is correct? What's the standard?
I don't think
none of those might be correct. What Fuad has been trying to point out is that if you have some minimums for different levels of complexity, then the way you justify your modeling approach would be easier. That's the point. Yes. I mean, you understand? So because in a way, when you go and present your results, if you refer to some standards that are out of question, really they should be there. And then the way how you handle it, it could be confidential, or it could be explained in in that closed room. But then still there is some sort of transparency, because most of the time, my understanding and my experience is the consumers, I would say, or the client tends to accept what you give. So it's going to be a kind of questioning mechanism.
Yeah, I think, as you say, it's not about saying which one's right or wrong. It's a process where you ask the right questions and you challenge and you make sure people have been through that. And I think regulators in Europe have been through a slightly tricky, because they've been very careful not to endorse any one model. They kind of have, in a sort of unofficial way, brought in some of that, because they meet the vendors and they do check, but only because they want to know as much as they can, so that when entities come with their capital model approval process, the regulators have some knowledge. But, you know, in the case of Florida, you do then have to some extent, you have to think about, you have to staff up the Florida Hurricane Commission. Actually, you end up, because if you have to go through that process every 2 years, it's quite onerous. You actually end up with only some big commercial companies bothering to do that, because it's quite a process. So you do have to think a little bit about the funding of the process. You know, how do you go through it to make sure, you know, to not discourage participants and not to add cost to the industry as a whole. But in principle, I think the idea of having more of a process of checking some of the right questions as you go on, without ever getting to a point that, you know, I mean, Florida Hurricane Commission, as you say, doesn't endorse any one model over another, but they do endorse the model that is rigorous enough. And so it's still hard to say where you draw the line, but I think in principle the idea of more scrutiny or more sort of review is a good one. It's just a question of how you fund it, who does it, and at what level.
Other questions? I guess we are, I don't see much action from the audience. I have one last question, and then we can call it quits probably. My question is that there is something called loss amplification, which I know that you know well, and then you do all the sophisticated analysis, all the finesse and everything, and after that you said that that's multiplied by 1.5, 1.4, and with not much behind it. I'm sure that there are political reasons for loss amplification, you know, demand and supply, all those things, but they are not well quantified. So I would like just to hear your opinion on those factors.
Who's starting?
Can I say? I can start as a non-modeler. We know it's happened, and we observe it. Quantification, I still don't know, but it's happened. We observe it. So the only thing that is immediately wrong for me is not putting that in the model, not taking at least consideration of it is wrong. How much? I can ask the modeler, but saying it's not happening or it's modeled wrong, not taking it will be a sure mistake.
So I think it's, to be honest, it's to a certain degree, it's a subjective decision. I mean, there were cases like the storms that we had in the Caribbean last year, where definitely due to the fact that there were basically the losses on islands made like economic demand surge much more of an issue because it was difficult to bring, let's say, new building material into the country, things like that. Claims inflation would be one of the components of post-loss amplification as well. There's basically a rating system, at least in our company, where we say, how do we rate different countries in the sense of probability of claims inflation? So how many people might send in a claim claiming that it was coming from the earthquake, even if it was not. So it's subjective, I would say. There's little data, but on the other hand, it's really funny because this particular issue with the post-loss amplification is always asked for. So it's, I remember our old earthquake models, they didn't have that feature at all. And at a certain point, the decision was maybe also due to the pressure coming from underwriting, coming from vendor models, coming from who, I don't know who, but there was the pressure, oh, your model doesn't have PLA. So in some cases, we put PLA, which is basically not really modifying the curve significantly, I would say. Many models, to my knowledge, have typically the problem that they slightly overestimate what you just heard a few minutes ago, overestimate the frequency range. So if you assume that the observed losses that you had in the past already have some fraction of post-loss amplification in it, that means that all the smaller events should have basically a post-loss amplification factor smaller than 1. And it's an easy tool, I would say, to fine-tune your loss frequency curve. But I agree, there's not too much data behind.
Yeah, I think really good question. I mean, you know, we're into one of those what unknowns. I think Paolo was talking about, do you load for? Charles done a great job of, you know, sort of highlighting potential of one of those, the 5 following, and post-loss amplification up there. Interestingly, you know, we talk about what's the PLA at a 1 in 200 or one of these big events. If you look around the world, all the, you know, a lot of the global catastrophe we've had, and you think, where did the losses sit on the loss curve? Most of them are 1 in 30, 50, 100-year events. Only Christchurch that actually modeled out as being beyond a 1 in 200. So some of these events we're trying to talk about and quantify post-loss amplification for are events that are, you know, haven't happened, and really knowing exactly what those impacts might be is tricky. Now, I think the vendor's done a great job at sort of bringing it back to, there's demand surge on building materials and labor. There's claims inflation that insurance companies are just swamped and they can't manage the claims and end up paying a bit more than they might otherwise. And there's what we call the kind of super cat big event where infrastructure in a town or city starts getting impacted and it has a knock-on effect. But it's really hard, as you say, to put a number. And, you know, let's be honest, in the Turkish insurance, reinsurance market, on behalf of our clients, you know, we do go out to the market with modeled curves with no PLA. And it's not because we don't think there's any PLA. We know, you know, in the case of a really big event, we've seen it around the world, there are going to be impacts. But we were concerned that how that had been estimated in some of the models, that a lot of the experience came from things like Florida hurricane, where you clearly had demand to get up and fix roofs before the rain caused any more damage. Whereas if you look at some of the Italy experience, some of the buildings stay, unrebuilt or unfixed for a number of times. So you haven't necessarily built up the demand surge on building materials and labor. So our concern was really not that it doesn't exist, but about the quantification, which begs the question in a way is why even give the option of with or without? Why not just build a model to say that's our best view on what it is, and then we wouldn't have the question.
I mean, from our perspective, we modeled a part of PLA, which is the demand surge part, so the increase in price because of the demand on materials and labor. And again, I mean, we do have, our view is that it does exist, so we do model it where we believe we have enough data to do so, and you might imagine where is the US. And everywhere else, we don't endorse one particular demand surge function, as we call it, but give the ability of our users to import their own factors if they want to. If they have more information than we do. We don't feel that outside of the US, we don't feel we have enough information to endorse a particular view on that.
Are there any more questions? Well, I think everybody's looking at me to close the session. Well, with this, I would like to close the panel and thank all the participants. They have really traveled a lot and spent at least 2 days in Istanbul. We are highly pleased that you are here, and getting your professional views was very important. And then I would like to thank every one of you. Thank you. With this, I will invite Musabe maybe to close the workshop as well, Yeah.
Distinguished guests, thank you, each of you, for these 2 very busy and productive days. We believe that we have had an event where experience sharing is very intense. And we wish to be together again in the continuation of these international workshops, which we have organized for the first time this year. Thank you again to all of you. Maybe we can have a closing photo of today. Well, maybe everybody should come closer to the stage.
We should also thank TCIP for all the preparations and for this beautiful workshop as well. Thank you. So where do we take the picture? Here or where? Just here?
Here.
Okay.
Everybody should come closer to the stage, please. I don't say on the stage because it may not be good, but we should be more on the front. Please, should you come closer, please? And maybe ladies would like to be on the stage.
Hadi bir konuşma yapıver.